Don't make me feel sick. Okay, good morning, everyone. Please take your seats. We are going to start in like 10 seconds. So welcome, everyone, for the second day of the school. I hope you're still full of energy and that you enjoyed yesterday's talks and also the drinks last night. So for today, we have again a full day with some amazing talks. So we'll have in the morning from with Peter Riktarik, federated learning. Then we will have a full day with RL. So we'll have Dojna Prekup first, and then Mikal Valko, the second lecture, and then we'll have the tutorial session on RL with Omar. And tonight we will have the first poster session in parallel with dinner and sponsor booths as well. So for the session tonight, please install your poster. Those who are presenting posters, install them during the afternoon breaks according to the assignment that you received, so either today or tomorrow. So please don't install your poster today if you're presenting tomorrow. And please take the time to visit the partner and sponsor booths to learn more about their projects and to see they have also job opportunities, and yeah, in general to get to know the people working in those companies. You might find useful connections. And in parallel with the posters and sponsor booths, we will have the dinner served there at the library. So you will be shown by the volunteers and organizers how to get there. Okay, so for the partners, you will see them advertised tonight. So ESET, of course, big thank you to our main partner this year. And then Tuke and AI Slovakia, they will also be there. And actually this morning we will hear about Tuke more, and tomorrow morning you'll hear more about AI Slovakia. For sponsors that you can visit tonight, so DeepMind, Innovatrix, our diamond sponsors, and then the gold sponsors, Visage Technologies, DTS, part of Xperi, Okin, and US Steel Košice. So please give a big round of applause again for our partners and sponsors. So just a note on Slido. So you've been, I hope you've discovered that you know where it is. You can send the questions for the lectures or ask the questions directly in the room if you're here in person. But I just wanted to point out that in Slido there are several rooms, and you can actually send questions in advance for some of the sessions. For example, we will have some panel discussions. So we'll have a career panel tomorrow. We'll have a talk by Joshua Benjo on safe and ethical AI. We'll have startups panel and security panel. So if you wish, you can send already your questions for those panels or talks. And you can also upvote existing questions. So Use the Q&A room to send questions for the ongoing lecture, but you can use those extra rooms in Slido to send questions already for other sessions. And yeah, don't be shy, ask questions in the room as well. I mentioned yesterday the team projects, so we really encourage everyone to take part in such teams, to brainstorm on project ideas, find colleagues, like 4 to 7 participants from different countries, use the projects channel on Slack to propose or join other project ideas. Optionally, find a mentor from the speakers that are around or experts that are around for different topics. And as outcome, we expect you to come up with a project plan. So the steps that you need to take, the kind of models you would use, the data that you would need to use, and put together a pitch that you would present at the end of the school. And optionally, you can commit to work together after the school to actually implement that project. And for the promising project ideas, we can help you find a mentor as well, like for a longer term. Okay, so I think this is all for me, and I will pass now to Jaroslav Poruban from Tuke, who is the Vice Rector, to tell us about the university here. Thank you so much, Vice Rector, for hosting us here. This is a wonderful venue. Thank you.
So, good morning, everybody. I'm glad meeting you at the Technical University of Košice. I'm Jaroslav Poruban, as you already heard. I'm the Vice Rector for Development and External Relations. But at the same time, I'm the head of the Department of Computer Science, the largest IT department at the university in Slovakia with more than 1,000 students studying toward bachelor, master, and PhD degree. I'm also the teacher, the researcher, but most of all, I like to be software engineer and IT architect. It's my hobby, it's my pleasure, and fortunately, it's also my work, so I'm in love with zeros and ones. By the way, let me thank all the partners, organizers, speakers, and to all of you that such wonderful event is happening at our university. So I hope you are enjoying that. I heard that yesterday was quite tough, and evening even tougher. So I'm here to start it in the morning, and later much wonderful things will happen. So let me tell you a few words about the Technical University of Košice. We are one of the largest universities in Slovakia and probably the largest technical university in Slovakia with more than 11,000 of students. We are located in Košice as well as in another city, Prešov. We have almost 900 teachers and researchers and 1,000 of students. We are the most international university in Slovakia, because we have almost 40% of foreign students coming from 32 countries. We are also proud to have 9 faculties from very variety of disciplines, ranging from classical technical ones like civil engineering, mining, ecology, mechanical engineering, and electrical engineering. But we also have disciplines like IT, business, and art. It's pretty well mixtures of these things, which helps us to develop different kind of thinking, not just reading the technical or technology skills, but also the economy or business behind that, as well as the design and the art. So at the university, it's a great mixture, which give us really opportunity to define, I think, modern new age products. I hope that TUK is well recognized in Europe, because we have a partnership with a lot of universities. We are really proud that we are a member of European University Alliance called Ulysses. In that University Alliance, we are the leader of challenge-driven education and research, and at the same time, we are the home of digitalization. That's probably also why such a wonderful event is happening here in Košice. In our Ulysses University, there is more than 150,000 students traveling along all the way. The part of our alliance are University of SAY from Spain, Haga Helia University of Applied Sciences from Finland, University of Genoa, Italy, University Côte d'Azur from France, and then Entrepreneurship School from Austria. So it's great pleasure for us that students travel across the Europe. Every year we are visiting or hosting a lot of students, and we are building together double-degree diplomas and stuff like that. We are also well recognized in the industry. On the last expo in Dubai, I think our products or prototypes were one of the major parts of our exhibition. If you visited the Dubai expo, we hosted or we presented there very special things, like shown on the picture. So we produced hydrogen cars and buses, by the way, with cooperation with our industry. I think we are also recognized in the region. We have a lot of partners from the industry and from regional ecosystem. We are in very close cooperation with different kind of organization. We are a member of Košice DAY2 Valley. It's a cluster of universities, schools, as well as companies. It helps us to sketch the future of the region. We believe in IT, we believe in AI, and today Košice are the city, or is the city changing from heavy industry to IT industry. Almost 15,000 of employees are working in the field of IT in Košice. So we have a lot of students, we have a lot of experience, and we believe that it's our future. We are also the member of AI Slovakia, and tomorrow we will learn or listen about the, I think, success story of AI Slovakia. At our university, computer science and artificial intelligence had a very long tradition. We offer courses in bachelor, master, and PhD degree, very classical one like computer science or software engineering, also cybersecurity, but very popular is intelligent and the business informatics, intelligent systems. We also believe that the world is changing around us, and we have to do the same. So we are trying to find a way how to teach better, how to speak with students, how to work on the real use case projects. So we are moving a little bit from the theory to innovation education, or innovation steering education. What does it mean? It means that throughout many of courses, we are not defining the content in the terms of theory, but we're defining the content of achievements or challenges. At the end, we also almost see the different kinds of prototypes. We are really proud that there is a mixture of different disciplines we could teach, and it means that we help our students to understand, develop, and build comprehensive products or prototypes ranging from very low-level hardware. Behind the hardware is also physical principles. So we build smart meters, light controls, and sensor kit to high-level, to very high-level cloud services using data analyzers, synthesis enrichment, data enrichment, machine supporting predictions, and natural computer interactions. But what we never leave behind us is deep understanding of our customer. So if you are thinking about the academy, if you are thinking about the industry, there is one major player, and is the customer. So while in the industry, customer is the main motivation. At the university, we usually lack that, and that's why we are heavily search for our customer at the university, and that's why we are trying to always incorporate the customer, the real customer, into our educational system. Let me speak a few words about what we do in the research in the field of computer science and AI. I think it's a very, very, very classical disciplines like data science, data mining, data analysis. I think we are pretty strong in cybersecurity at our university. Of course, the artificial intelligence, a long tradition at the university. I mostly work in the field of software engineering and product design and IT, as an IT architect. Of course, we do the research in the distributed and cloud computing system, in the field of software integration, or in general, enterprise integration. We do the research in the field of cognitive networks and smart devices, and in the field of human-computer interaction. And by the way, I see also AI as a very important part of human-computer interaction. We understand that it's at the university, it's not just about the education, it's not just about the research, it's also about making the theoretical themes come true. That's why we established University Science Park Technicum, which offers services to the public. It means to our teachers, to our students, and through employees within the region. The Technicum enables technology development and innovation. We hope to accelerate the technology transfer. For us, it's creative space to support the implementation of applied research and development. There is multiple startups and spin-off located in our Technicum, which they are growing from very seeds of the idea to really, I think, successful companies. And we also help our spin-offs and startups with intellectual rights properties. So we see at the university that science, research, education, and cooperation with the industry could come together to bring in our region really new ideas, opportunities, and of course, we hope that it will help us to sketch our future of our region. So, finally, if you look at the last 30 years, I think IT technologies, including AI, dramatically change our society. You are here because you want to hear more about that. Honestly, today I couldn't imagine a product built without IT support, including artificial intelligence. So today, if you would like to sell candies, I couldn't imagine it could be done without IT or AI support. Probably we find a QR code, it's bringing you to a web page, and on that web page, you see a lot of things you can chat with the bot and a lot of stuff like that. So, yeah, I'm thinking that you are at the good place, that in the following days and even yesterday, you will find a lot of different experience and it will help out your future. Personally, I'm not scared about the artificial intelligence, hope you too, but I'm scared about how AI questions the humanity. That's why also you are here, to understand the AI and to understand the questions behind the humanity, behind the challenges which is behind us because of AI and machine learning. I hope that during this amazing week you will find all the answers to your questions about AI, about its importance, about opportunities, but mostly of all, I hope that you find new friends because it's very essential in life. I'm pretty sure that a lot of new challenges is behind you, but together with the knowledge, experience, and of course with your new friends, you can quite easily face them. So thank you very much for coming and enjoy the next week.
Welcome back to the content part of the school. So it's my pleasure to introduce to you Peter Richterik, who will be the course in federated learning. Peter is from Slovakia, so very local here as well. He did PhD in he did master in mathematics in Comenius University. Then he studied operation research as a PhD in Cornell. Did postdoc with Yuri Nesterov, one of the godfathers of optimizations. Then he was a professor in University of Edinburgh, and then now he's a professor and leading his own lab in KAUST University in Saudi Arabia. What's amazing about Peter also, he gives a lot of a lot of back to Slovakia. He took a lot of Slovak people as his PhD student and trained them to be a successful scientist. He's making a list of known Slovak scientists of the web. He spent several summers in Slovakia going a lot of lectures. So we are very happy that he gives, and he's a big treasure for Slovakia. And today he will tell us about the topic that he's passionate about, maybe too passionate about. He's leading a world seminar on this topic. It's called Federated Learning. Here's Peter.
Thank you very much. Is this working? Okay. Thanks for the very nice introduction. How many of you know about federated learning? All right. How much do you know? I have 1 hour, 10 minutes to talk about this. Hopefully you don't know all of this. So I'm a professor at KAUST, which is a university in Saudi Arabia, established in 2009. It's a very young university. So this is how it looks like. There's some few photos of this. The gecko is on the windshield of my car. And I'll talk about research which we've done over the last year and a half, roughly, on what I call the 5th generation of federated learning methods, or local training methods. And this joint work with a bunch of really amazing people. Almost everybody here is a member of my team, except for Sebastian Stick, who's a collaborator. And at least one of these people is in the audience. Ivan, where are you? Over there. So there'll be something on at least one slide, which is a collaboration with Ivan. So Laurent Conda, he's a research scientist on my team. Konstantin Mishenka, a former PhD student, now research scientist at Samsung AI Cambridge. Michal Gruzien is intern, and so on and so forth. So I'll first talk about something which is an introduction, which are these points 1 and 2. Just asking the question, what is federated learning, to answer it for those of you who have not heard of this. And then I'll review the idea of so-called local training, which is a key algorithmic component behind federated learning. In fact, I was surprised to see those hundreds or thousands of papers written on the topic of federated learning, conflating federated learning with local training. So I would see papers which have federated learning in the title, and the only reason why they would put federated in the title is because there was some local training going on. So in many of these papers, it's really the same thing. And then I'll review history of federated learning from a certain point of view. Of course, I won't be able to talk about everything, but a certain aspect of it. And in this way, I'll get to this part 4 on the 5th generation of local training methods and explain what that is about. And this is the stuff that we've been really busy with over the last year and a half or so. And then I'll have time, I'm pretty sure, to talk about ProSkip algorithm, which was the first method in this 5th generation of local training methods. And then I don't think I will have time to talk about GraphSkip and RandProx. That's why these are grayed out. In case you happen not to be engaging with me, I like the audience to ask me questions throughout, then I might be able to get at least to one of these. So we'll see. So what is federated learning? So it's really massively distributed machine learning over many, many devices. And typically, these could be mobile devices such as phones. And the idea is that we're collecting data at edge devices, and the data is collected there in the first place and stored there in a private fashion. And not all of this data is pushed into some centralized location where it's processed. And the idea is maybe we should process the data or train machine learning models without taking the data first from those devices. Let's keep them there and think of this collection of, let's say, millions of mobile phones as one big supercomputer, where the super has to be understood very carefully, because the computer is not really a standard supercomputer. It's amazing in many ways, because there's many of those phones, but then it's very weak and very strange and very rough in many other ways, because some phones are different from others. They have less memory, they're less fast, they have worse connection, and so on and so forth. So it's a very heterogeneous system, and it's not that easy to do computations on that system. The first application that was shipped, federated learning application, is this next word prediction, Gboard. So this is it. And as you can imagine, if you wish to train a next word prediction model on your phone, probably the data that is stored on your phone is not going to be good enough for you to train a powerful enough model. But if you collect all the data stored across millions of phones, then maybe the model is going to be powerful enough to be useful. All right, so federated learning started for me roughly in 2016, maybe 2014-15, and this was a joint effort of my team at the University of Edinburgh, where I was at that point, and a Google team led by Brandon McMahon. Jakub Konečný was supported by Google Fellowship, and then he worked at Google for many years, and he was in many ways spearheading the effort on federated learning at that point in time. And Konstantin Mishenka is behind the first paper, the Proxkip paper, in this 5th generation of local training methods. This is why I'm highlighting their names here. So here is a Google AI blog from 2017, from April 2017. This was when I moved from Edinburgh to KAUST, which announced federated learning to the world. So it's not such an old technology, 6 years or so. So this is it. And it mentions 4 papers. These are the 4 foundational papers of that field, and 2 of these are collaboration between my team and Google. And as you can imagine, these are the most impactful papers that I've written with the most citations. Federated learning has been of interest to industry. It was very interesting for me to observe that as I was attending conferences. I would see different companies being very interested in this technology and starting up labs. So there was Meta Lab, and companies were started such as Okin. We have some people from Okin here, FedML, and so on and so forth. So very recently, this was just in May this year, the US announced its National Artificial Intelligence Research and Development Strategy, and it mentions in Strategy 1, federated learning is one of those areas of machine learning they want to focus on. So I'm mentioning all of this just to explain that federated learning is of interest, and the reason why it is of interest to industry is precisely because the wealth of data we'll have in the future will mostly be actually collected at edge devices, and it will not be stored in a centralized location. If you want to train machine learning models on it, you have to do this in a massively distributed way, and this is what federated learning is about. Now, federated learning faces many, many, many challenges, and there are many tricks, algorithmic or software, hardware, and so on, tricks which help us to design methods that can deal with all of these challenges, and I don't have time to go through all of these. I could have chosen a style of presentation where I just go through all of these and tell you a little bit about each of them. This is not what I've done. Instead, I'll tell you more about one of them, just for a different taste of what these lectures are about. But I can tell you, while I'm on this slide, what some of these other ones are about. So compression in communication complexity really refers to the idea that when you have a distributed system and you wish to train a machine learning model, then these nodes, these workers, these clients need to communicate, obviously, right? Because they have part of the training data set. None of the workers has the full description of the problem, so none of the workers can solve the problem on its own. But together, when they pool resources and the data, they can solve the problem, but this is not possible without communication. However, communication over internet, weak links, is going to be very expensive, and the idea is to compress the communication. The compression that is used at the moment is a massively lossy compression. So you would throw away most of the information you want to send, and it turns out the algorithms still can do what you want them to do, and in fact, they can do this even more efficiently than if you didn't compress. And they can do this even provably more efficiently. So there's mathematics behind this, which says you should compress. If you don't, you have a less efficient algorithm. This is what the compression is about. Maybe I'll mention one more. Partial participation in the device heterogeneity box. So that's the idea that if you have these millions of phones which collaborate in training one massive federated learning model, then not all of them will be available at all times to do work, because these phones will be on battery, and those we will not touch. We're not going to be training any model on a phone that somebody's using. However, if the person is sleeping and the phone is on charge, and when they bought the phone, they clicked on the right buttons, agreeing to federated learning actually happening on the phone, then maybe some rounds of federated learning are going to happen. So the idea of partial participation is that only few of those, maybe 10,000 instead of million, of those phones will collaborate in any given communication round, and then another communication round, another 10,000 phones will work, and so on and so forth. So I'll focus on this idea of local training, which I believe is one of the most crucial aspects of federated learning. And this stopped working for some reason. Should I press the arrow? Is that, or this is not the right thing to do? Okay, now it works again. Good. Okay. So, local training. What is local training? I wish to first formalize the problem, and it's going to be very simple formalism at this point in the talk, which is we just want to minimize the average of a huge bunch of functions. So there's the mathematical formalism. Why do we have huge number of functions? Because each function corresponds to the loss of machine learning model parameterized by vector x, which is d-dimensional, on the data stored on the client I. So Fix is the loss of model parameterized by vector x based on data stored on client I. And now when we average all of these losses, this is the empirical risk, or the average loss of the model across all the data. So we want to train a single model which does well on average on everybody's data. So this is standard formalism of empirical risk minimization. There are other approaches to federated learning where you would want to personalize these models to different clients or different clusters of clients, and I'm not going to talk about this. This is one of those things I actually mentioned here in this box. Personalization is mentioned in the data heterogeneity box. Okay, so this is the formalization. And unlike vast majority of papers on federated learning, which for historical reasons had to assume some level of homogeneity of the data, I'm not going to assume anything about homogeneity of the data. So the data can be arbitrarily heterogeneous across these clients in this talk. So here, the notation expectation over DI just means I take all the data that I have, I call it DI, and I take expected loss over the local data, and that's what Fix is. All right, so what is the dumbest possible algorithm you can think of when given the task of solving this problem? So the dumbest one would be gradient descent. And at the same time, it's the smartest one because it's really the basis of all the currently used efficient methods that we use in machine learning in general and federated learning in particular. However, nobody would use it without some changes, bells and whistles, and so on. So I'll start with gradient descent. And I call it distributed gradient descent, not because this is a different algorithm, the same algorithm, but because I want to explain to you how it's implemented in a distributed fashion. And it's going to be trivial, but let's go through those steps anyway, because it helps us to go through the next slide, where I'll introduce the idea of local training. So let's assume we have 3 workers. For simplicity, obviously, we'd have millions of workers in practice, but here we have 3 workers. Each worker has this function, F1, F2, F3. And we want to minimize the average of these 3 functions. That's it. Very simple problem. There's a server, and the server's role in this case will be just to facilitate communication. So no of these workers on its own can minimize the average because none of them owns all of these 3 functions, right? Each owns a part of the problem description. None of them can solve the problem without talking to the other. So the server will be communication hub. That's all. Whether this is actual server or whether this is just an abstraction and the workers can communicate in a peer-to-peer fashion, that doesn't matter for the rest of the talk. Okay, so everybody now receives a copy of current model or parameters of current model xt from the server. That's at time t. What they do then they pretend they're going to train a model based on their data only. Okay, so worker 1 will make copy of a copy called x1t of the model xt, and will take one gradient step from x1t based on the gradient of function f1 with some learning rate gamma. The fact that it doesn't change in time doesn't matter here for this talk. So notice that these steps are identical except for the fact that there are different gradients taken here. So gradient with respect to f1, gradients with respect to f2, gradient with respect to f3. Now, once this is done, these orange models, or the vectors which parameterize the models, are shipped to the server. And this is going to be very heavy, because these are d-dimensional models. We assume d is going to be in the millions or billions. It's going to be a large model. Typically, we work with over-parameterized models. So this could be, let's say, 10 times as much as we have data. So d is going to be 10 times bigger than the number of data points, let's say, in practice. So this is the bottleneck. Now, what a server does, it just averages the parameters of the model. Very, very simple thing. And now if you just do the algebra and you plug in for those three expressions, what you get is just a gradient step. So you can just do this very quickly on a piece of paper. So this is nothing else than just writing gradient descent for the minimization of the average of three functions in a distributed fashion. And now this model xt plus 1 is broadcast back to the workers, and the process is repeated. This is it. So this is distributed gradient descent. Now, do you think this is an amazing method? I said it was not. Why is it not? Any ideas? What is a key problem with this method? There are many, many problems, obviously, so anything you say is going to be true. Okay, so Hrash says that maybe this is not going to find the minimum of the problem. Well, that is true if the functions are non-convex. A gradient descent is a local method. It is kind of attracted to local minima, or maybe to saddle points, but not necessarily the global minima. So let's ignore this, and this is clearly an issue with gradient descent. And if you want to globalize it, and if you want to push it towards a global solution, maybe you need to, after you maybe stabilize in some local basin, maybe you need to add some noise again so that you escape, and so on and so forth. So this is an issue, but is not really the key issue, because this will be an issue with any gradient-based method. But with this particular method, there's another really, really important issue. Okay, there is an idea. Right. Communication bottleneck, one issue, yes. Okay, so that's a very good idea. So if nodes fail, this may affect the average. In fact, there is a whole subfield of distributed training called training with Byzantine workers. And the idea that some workers may actually try to actively damage this training process, and they only pretend they have some data and they just send some nonsense to the server. They can send a huge vector, whatever, in order to damage the average. In such case, this method will definitely fail, and there is a way to fix it. So there are Byzantine versions of distributed gradient descent, Byzantine tolerant versions, and I'm not going to talk about those, but those of you who are interested, definitely happy to talk about this. But that's another issue, and what you said before is also an issue, which is the communication bottleneck, and that's the one that I wanted to really get to, so I will not take any further questions on this slide. So the idea is that communication costs a lot of time, but maybe the one gradient step took very little time. So maybe a minute. It depends on the number of data points that you have on each worker. But think of communication being so expensive that this may take, let's say, a day, while the computation takes 5 minutes. If that is the case, this is clearly a bad algorithm, right? So what can you do? So what practitioners came up with roughly 10 years ago, depending on how you count, you can go 30 years ago if you close one eye, but let's say 10 years ago, is a very, very simple hack, which gets you out of this. A very, very simple hack. What is the hack? That's the hack having to do with taking local gradient steps. So distributed local gradient descent. This is a different method. It's almost the same as distributed gradient descent, except for one change. And the change is, when you take this first gradient step, you're not going to be satisfied because it took 5 minutes. And then you take another gradient step. Takes 5 more minutes. Now you're 10 minutes doing some work, right? And then you do 5 more minutes of work, and so on and so forth. And maybe you take capital K local gradient steps, and this may take, let's say, a day, and then you do communication for a day, and then it feels like, okay, I'm doing the same amount of communication and computation. Maybe that's a good thing, okay? Waving your hands, okay? So that's the idea. But now this is no longer the original method. This is a different method. It might actually not work at all. However, what people found out when they did experiments with this very simple idea is that the method is 10 to 100 times faster than the original method, if you choose the capital K right. And the question that has been on people's minds ever since this idea was introduced was, why does it work? What's going on? Are we just lucky? Maybe the data sets are simple. Maybe the problems are simple, the models are too simple, and so on. It might be a fluke. Oftentimes, in machine learning and deep learning, you discover something, you think this is a phenomenon, and it's a fluke. Actually, I think that's most of what's going on. But some small portion of things, these are real phenomena. So at that point in time, this could have been just a fluke, a coincidence, right? Lucky day for those researchers. And that's what this talk is about. So I'm going to now review briefly the idea of local training. But maybe if you have any questions about this, because this is really the key slide here. Yeah. Absolutely. So I'll go back to this. So the question was, is all of this information useful, or should each worker maybe just take 10 elements of what? Of the data? Of the local data? To communicate. All right. So then that's actually the, okay, then I'm not going to go back. So the answer is no. You can do communication compression. So instead of sending the d-dimensional vectors one way or the other way, or both ways, you can compress, and you can compress heavily in a lossy manner, and you get a better algorithm. And that's another story, which I don't have time for today. It's a very interesting history, and it turns out compressing is better than not compressing, even mathematically, and in practice, definitely, and the difference is huge. But I'm going to talk about the idea of what happens, why communication acceleration happens through local gradient steps.
Question from Slido.
Yeah.
How commonly federated learning is used in the industry, other than Gboard?
Well, not all that commonly. So this started just those 6 years ago, and companies have sprouted ever since, I would say exponentially, and it's an increasing observance of mine that I see that some companies are using this for some practical uses, but this is still very much in the early days of the field, and it's very interesting to be working on both the underlying methods, theory, algorithms, and applications. So for instance, Okin, I don't know who's here from Okin, they work on medical applications. Right. There's a question?
Yes, please. I just wanted to ask, how does this local learning compare to just a batch descent? If you just do a batch descent for...
Right, so that's a very different idea. So, okay, I have several interpretations of what the question meant. It's not entirely clear to me. But one version of this is that you do gradient descent. You don't take local steps, but you subsample data on each worker and take one SGD step. This is just mini-batch SGD. It's a different method. There's no huge number of local steps. There's just one step, but it's a mini-batch step with respect to the data. It's a different method. This is also used, and it can be used in combination with this method. If every worker contains many data points, then it's a good idea not to take gradient steps, but SGD steps instead. So these are orthogonal ideas which combine for better algorithm. So in fact, this algorithm can be improved by doing SGD steps instead of GD steps. However, I don't want to go into SGD right away before I explain what's going on with GD, because that's even a more fundamental problem. Yeah. Right. So that's a good observation. So here, the gamma is the same just because I don't want you to focus attention on it. It could be different. In fact, we have some extensions of these methods where not only the learning rates are different, but the number of local training steps is different on each client, and even the algorithms that everybody uses is different. But it took us some time to realize we can do something like this, and that this doesn't damage the algorithm. And I'll get back to that at some point.
No more questions? Good. Oh, there's one.
Hello. So.
And now this stopped working again.
So you assume that the data is heterogeneous in nature. So what if there is distribution shifts in the data itself?
Okay, so that I know nothing about. I don't know any research on distribution shift with federated learning with some theoretical guarantees. I've seen some very few works which try to adjust the federated learning algorithms with respect to distribution shift, but I'm not going to touch that topic. And I'm sure everybody can now criticize something about this method because obviously it's not something you would want to use. But you would want to throw in maybe adaptive learning rates, you would want to throw in momentum, you would want to throw in subsampling of clients, subsampling of data, you would want to throw in maybe differential privacy, noise, and so on and so forth. So there's many things you can throw on this, but now I want to really zoom in on the idea of local training and what it does.
Okay. I asked this because you are trying to minimize the risk over the data, so I was just curious.
Right. Yeah. So this is over fixed data, not over evolving data. Okay. So, so the idea that we had for reviewing the history of local training methods was outlined in this paper of mine that I wrote with two students, Grigory Malinovsky and Kai. And we took a very particular point of view at the history and looked at the last 7 or 10 years of research in this area and clustered into 5 generations. So let me go through these generations. So the first generation goes back to at least 2014. You can go back to 1995 if you really want to work off all the Mangasarian, but I don't want to attribute these ideas because they're not exactly the same. They're almost the same, but not exactly the same. So at least to this work of Daniel Povey and co-authors, where what they looked at was parallel training of deep neural networks with parameter averaging, and the idea of parameter averaging is the averaging at the end, after the communication. So they said, don't average the parameter after each mini-batch SGD step, but take more of these steps and then do the averaging. So that's the idea, right? So this is a fully computational paper. There's no theory in it. There's this work roughly 1 year later by Moritz, Nishihara, Jon Stojka, and Michael Jordan, where they observe the same thing. And then there's this very famous paper, one of those 4 papers that I mentioned are the founding papers of federated learning by Brandon McMahon and other Google co-authors. So all of these papers, they contain this key idea of local training. None of them contain any theory, but this idea really meant that, wow, we can maybe now train in a massively distributed fashion much, much, much faster. This automatically means that maybe we should really be doing it and we shouldn't be shy from doing something like this. Now, why does it work from a computational perspective? So this is what you might see if you try to code it up in a very simple environment. So by simple, I mean this is just L2 regularized logistic regression. So this is not only a convex problem, this is a strongly convex problem. I'm going to shy away from non-convexity in this talk. And you work with gradient descent as the local solver and not with any stochasticity anywhere. However, what I'm going to vary is k, the number of local training steps. So if I have 1 local training steps, this is just distributed gradient descent. And what you see is linear convergence rate. So you have a semi-logarithmic plot, and you see this blue line. Well, it's a line, and that means it's linear convergence or exponential decay of the error. However, you can see as you start increasing the number of local training steps, the method gets better and worse at the same time. Right? So the method gets better because you decrease the loss much faster initially, right? However, the more local training steps you take, the sooner the method just stops working completely, right? So if you max it out and go with, let's say, 32 local training steps, you get a very fast method which gets to the error of roughly 10 to the power minus 2 or minus 3 very, very quickly, probably the fastest from all of these other methods, but then it cannot achieve higher accuracy than 10 to the power minus 3. Which could be fine for your application, but if it's not, then that's not the right method. So there is at least 2 problems with this plot. One problem is, why do these methods converge so much faster than the blue one, than gradient descent? Why? There's no explanation for this. This is a purely empirical plot. We don't know why that decrease is so steep. We don't know that. And then we don't know, I'm pretending we don't know, I'm 7 years back, right? So we know now, but at the moment of looking at the slide, we don't know. And we don't know why the method stops working. Why does it just not continue decreasing the loss? And those were the problems that the community was tackling with after this initial work was released. So the first idea people got how to do any kind of analysis, how to do any kind of understanding, again, any kind of understanding of local training as a phenomenon, was to assume that you're almost in the perfect scenario where you don't actually need communication at all. So what's the scenario? The scenario is, imagine that all the loss functions, FIs, all of those, they're the same across all the nodes. Exactly the same. If they're exactly the same, what K should you choose? Does anybody have any idea? K is the number of local training steps. If all the functions are exactly the same, what is the ideal choice for the number of local training steps? What does your intuition tell you? 1 is one option. What did you say? Total number, so all of them. Okay, any other ideas? So do we need to communicate if all the functions FIs are the same? We don't, because then the average is the same, which means everybody really contains all the data, so there's no need for federated learning at all. There's no need for communication, right? So all of the workers have the same problem description, they can just work alone. They don't need to talk to anybody, right? So what then happens is that you should just take K, capital K, to be as large as you want, and you should never communicate for parameter averaging, because that way you'll avoid all the communication, which is costly, right? So based on this intuition, what the researchers thought at that point in time was that, okay, if the functions are not entirely maybe the same, but not very far away from being the same, maybe K, which is large enough, would be good. Okay, so that's a very simple idea. And that's what these people have done. And they've made various assumptions of what the similarity might mean. And one of them is this bounded gradient diversity called strong growth, where when C is equal to 1 in this inequality, then what this roughly means that the functions are the same because the gradients are really the same at every point. Because gradient of f is the average of the gradients, so the average of the gradient squared is related to the gradient square, so to the square norm of the average of the gradients. So C1 is the ideal case of identical functions, and if you go with C from 1 to infinity, you get less and less similarity, and if C is very, very large, these functions are arbitrarily dissimilar, and then maybe the things won't work. And if you look at the theory in these papers, the prediction will also be if C is very big, or if you have a lot of dissimilarity, the method just doesn't work at all. Now that is a problem because it does work. So similarity and homogeneity is not an explanation for why local training works, because you can run the method with arbitrary dissimilar functions and it's still going to work well. So this was not an explanation for what's going on. And the other problem is that in practice, the data is not homogeneous. It's very far from homogeneous. If you have a phone and you collect data of certain type, and somebody else collects data of very different type, the loss functions be very, very different.
Do you want to take a question from Slido?
Yeah, absolutely.
Would it be possible to solve the problem in a random forest fashion, training each model on the local server or local data, even overfitting them, collect the answers, and then averaging on those instead of the parameters, maybe introducing a weighted average based on a similarity measure on the data?
So everything I'm talking about is model agnostic. I'm not really talking about what the parameters represent. So this could be any model you want. This could be a neural network. It doesn't have to be. It could be super vector machine, could be random forest, could be anything. So all of this is model agnostic. Now, if you know something about the model, you can take advantage of it, and maybe you can do something better, but the phenomenon is model agnostic. Okay, so at generation 3, people ask this question. Can we actually remove the assumption of homogeneity of the functions or of the data, and can we get some kind of understanding of the convergence of this method? Is it possible, or is it not? If the answer is no, then this is a heuristic, and it might just fail terribly if the data is different, right? And we want to really apply it to heterogeneous data scenarios, which federated learning really is about. So then it would mean we need some better ideas because the method can terribly fail. The answer is no, it still works. And this is something we've contributed to with my former intern, Ahmed Khalid, and former PhD student, Konstantin Mishenko. So one of these papers is called First Analysis of Local Gradient Descent on Heterogeneous Data, and that's exactly what we've done there. However, while we're happy that we managed to do some mathematical analysis, and I'm not going to tell you what it is, this is not that important right now, we're very disappointed at the same time that we got a result which said that the method was worse than even gradient descent. So what does it mean? Okay, so we have advanced in theory, so now we know the method will work, it will converge if you set the parameters right, but the optimal number of local training steps is actually 1. You should not take more than 1 local training steps, you get the worst method. It will still work, but it will perform worse. So that's not what we wanted to get, and definitely not what practical experiments were showing. So you can see we're closing the gap between theory and practice, but the gap is not closed. You just progress towards closing the gap. All right, so, and this stopped working again. Yeah, so I guess I wait till this starts working. All right, so now it works again. So the 4th generation, and this is the last before the final one, which I'm going to talk about soon, is the generation where people try to resolve exactly this problem. Can we make the method as fast, at least, as gradient descent? Okay, not make it worse, but at least as fast. Some changes to the method were necessary, and this is what this generation 4 of methods really does. And the most famous algorithm is the scaffold algorithm by Sai Praneeth, Karim Reddy, Satya and Kale, and other co-authors from Google. And we've done something like this a little bit later, a year later, with different algorithms with my team, and some other people done something similar a little bit later. So what you get when you look at methods of this type is that these methods just never stop decreasing the loss. So we don't see these flat lines, and the linear convergence just keeps going. However, the method is not faster than gradient descent. So it's still, we're closing the gap a little bit more, but we're still not satisfied because we don't see the benefit over just taking 1 local gradient step. Okay, so that's the problem with this. And this 4th generation brought into federal learning the idea of so-called drift reduction. So the technology, the algorithmic innovation behind generation 4 of these methods, behind the fact that we can stop that flatlining and continue, resolve that flatlining is called drift reduction. And now I can move finally to the 5th generation of local training methods, which we call the accelerated generation. The idea there is, in practice, we really see that taking these local training steps can massively accelerate communication efficiency by factors of 10 to 100, could be even larger. However, there's no theory behind this, and this still could be just a fluke phenomenon, not real phenomenon. We can be just lucky because the data is nice, model is nice, or something like that. And the question is there a phenomenon behind this? There's been already almost 10 years of research on local training methods, and not a single paper was able to show that taking more than 1 local training steps is better. In theory. In practice, yes, but in theory, no. Okay, so it's clearly an interesting problem to think about. So the resolution to that problem, which I'll talk about soon, the high-level idea you should have is this. Local training steps indeed mathematically and provably accelerate communication. And they do so in the following way. If you have gradient descent method or distributed gradient descent method and it converges in L over mu times log 1 over epsilon steps, okay, what is L? L over mu is going to be some kind of a condition number associated with the data and with the problem. L would be something like Lipschitz constant of the gradient, and mu would be something like strong convexity constant, but don't worry about this. So if L over mu is big, it just means you need many, many steps, many communication rounds. Then with local training done properly, you get square root of that. So instead of, let's say, 1,000,000 communication rounds, you just need 1,000 communication rounds. So this is really, really massive improvement, and this is where this factor 10 to 100 really comes from, because the condition numbers maybe were square of that, right? 100 or 10,000. Okay, so that's really the idea. And the first paper which managed to show this is a paper that we've written with my team members and amazing collaborator Sebastian Stick. And this is the first paper that I've co-authored, which has 3 exclamation marks in the title. So I should apologize for that, but we're quite excited because we thought about this for quite a while. We also have a scholarly subtitle in the footnote for those of you who hate exclamation marks in the titles. Okay, so what's really going on here? Once we came up with the idea how to do this, and I'll talk about it a little bit later, we're immediately inspired to think about other things, because in my team and in other teams, all those things that work on federated learning, there are other tricks that we can use to enhance gradient descent in order to come up with a better method. So communication compression is one of them. Client sampling is another one. Differential privacy, another one. Or maybe you can do training in a peer-to-peer fashion where the nodes are connected through some connected network, and there's not necessarily a single hub through which communication happens. So can you do the training in a decentralized fashion on a connected graph? And so on and so forth. So we ask all of these questions, and we were busy writing papers with all of these extensions and improvements and so on and so forth. So those of you who are interested in these 5th-generation local training methods, so these are some of the works that we worked on in the last year and a half. And now I'll stop here at this slide where I want to give you an overview of all of these works so that you get a big idea of what's really going on here. Now, I don't have any hopes that I'll go through all of this. I just want to highlight a few of these things, but I'm pretty sure this should be useful for you to understand what these works are really about. So there's a question?
There is a question, you can see it, but I'll read it for everybody. Do you think that big numbers of users will allow to use their sensitive data from the smartphones to be used for training the global model?
I'm not sure I understand the question. So I read it. Okay. Okay. Well, yes, that's happening. I mean, if you buy an iPhone and you click on, do you want to share data, analytics, whatnot, you're actually allowing federated learning to happen, for instance. So yes, big numbers of users actually do it.
Any question from the audience? Yes, you have a question? Yep.
But the data never leaves the phones, so the data does not, it's protected. So this is actually a secure way of training on those phones. The data doesn't leave the phones.
So you said something before, like if all the functions are the same, then you can wait, blah blah. Like, and then you said, okay, but if the functions are different, then we can still prove something. Like, but what kind of condition? I guess it's not with arbitrary functions, right? What kind of?
It is. The difference between the functions can be arbitrary. So the phenomenon of going from condition number to square root of condition number works for any smooth, strongly convex function. And in that class of functions, the functions can be arbitrarily different. But they need to be in that class. They cannot be you cannot just come up with a different function from outside of that class. Yeah.
You don't require something like, I don't know, the gradient is bounded.
No. That's one of the advantages. So many papers in federated learning, they assume these kinds of things, but they don't have to. And they assume it because of legacy reasons, because that was the best we knew at that time. Our understanding progresses, and we're resolving these issues, removing barriers and assumptions, and revealing more of the underlying phenomenon, and you don't need those assumptions. Yes, there's a question over there.
Okay, so considering that the data does not leave the phone, I suppose that we do not have access to the true labels of the data. So apart from next word prediction, what kind of applications can we apply this?
So this is all supervised learning, what I'm talking about. So recently people were thinking of doing other things in a federated fashion, such as federated analytics, self-supervised learning, and so on. But what I'm talking about is supervised learning for the purpose of this talk. And that's what 99% of all the research on federated learning really is. I just made up that statistic, but it's roughly like that. And while we do not have access to the data or the labels, the phone has access. The person who owns the phone has access. So the training happens on the phone, and the raw data does not leave the phone. And there are technologies, some ideas how you could protect the data. Differential privacy is one of them. You can do homomorphic encryption. You can use some trusted execution environments. There's lots of other things you can throw at this, which I'm not talking about because it's not the topic of this talk. So if you run the algorithm I'm going to describe here, it will not be a secure and private way of training on the data. You would need to enhance it. Yeah.
And what is your best intuition regarding the fact that it can be faster than gradient descent?
Well, so I'm going to talk about this. I'm going to explain it. Yeah. So I'll give an answer to the question.
There's a question in the back.
I was wondering, what is the relationship between the number of clients and the number of communication rounds? Do the performance improve with more clients?
There's not necessarily any relationship. You can have any number of clients, and things can go worse or better. It really depends on the condition number. So you can imagine situations where the condition number, OK, I'm not going to go back, I guess, because this gets stuck again. You can imagine a situation where the number of clients increases, but the data on those clients is so different from everybody else because they happen to be outliers that the condition number increases so much that the square root increases. That can happen in principle because the clients can be very, very different. But if you have already many clients, the chances, if you add more clients, that they'll contain massively different data go down intuitively. So what should happen then is that the efficiency improves because the condition number is unchanged. It's a hand-waving answer to your question. OK, so now I'll go through some parts of this table to explain what's going on. So the algorithm I'm going to talk about is the proxkib algorithm. That's the first row in this table. And the very first entry is this O square root of condition number times log 1 or epsilon, where epsilon is the error tolerance. So that's the number of communication runs to solve the problem to epsilon accuracy. And as you see, the local training trick does the square root, turns the non-square root into square root, and that's finally now we know what local training does. We don't know yet how. I mean, we in the room, because I didn't tell you what the algorithm does, but I hope you believe me, I'm not a liar, it really does it. So the local optimizer is just gradient descent in this case, and it turns out that the number of local training steps, we have a formula for it. So before, this was heuristic, this was a hyperparameter, and people had to choose K to be small, large, they had to fine-tune it in order to figure out the best performance. But now we know what it is. It should be the square root of the condition number. That's the optimal number of local training steps. If you take more local training steps, you get worse performance. If you take fewer, for instance 1, which is what distributed gradient descent does, you get worse performance. This algorithm doesn't do any client sampling. All the nodes, all the workers, all the clients have to be available and give you the gradients at all times in all communication rounds. In fact, when we were writing this paper, we did not know how to resolve this issue. It may look as a simple thing, simple extension possibly, just allow for some client sampling. We couldn't do it. We couldn't do it without destroying the acceleration communication nature of the algorithm at that time. So the algorithm doesn't do any communication compression. When it communicates full d-dimensional vectors. So if d is a billion and you send 32 bits per every entry, 32 billion bits you're sending both ways in each communication round. And it actually supports decentralized setup, so you can run it also in a peer-to-peer fashion on an arbitrary connected graph, and the communication only happens along the edges of the graph. And I'm not going to really talk about that. So once we figured this out, we had questions. One question is, can you replace the local optimizer, which is gradient descent, by something else? What will happen? Will you get better method or will you get worse method? In practice and in theory. And in some of these papers, you can see that instead of GD, what is written there is any. And this any just means you can work with any local optimizer and the theory will go through. So the fact that we're using gradient descent as a local optimizer, it doesn't mean that you have to do gradient descent. You can use something else. You can use Adam, for instance. In some of these, you can see we use VRSGD. This is the variance reduced SGD methods. It turns out that if you do that, if you do SGD, and it's variance reduced, whatever that means, I'm not going to talk about variance reduction, then you will need more local training steps, but those local training steps will touch fewer data points in totality. So you'll have a method which bothers the clients less, okay? Because you subsample certain number of data points in each local training step. You take more of these local training steps, but not so many more that you would take more runs over the local training data. So the idea of doing SGD actually leads to a more efficient algorithm from that point of view. Okay, so one thing maybe I can mention here is this method 5GCS and Tamuna in the last two rows, which are the only ones which do any kind of client sampling. So we tried to solve this problem for quite a bit of time, and we couldn't, but in the end, we found these algorithms which can also combine communication acceleration through local training steps and to be able to work with a sampled number of clients, and everything works fine in theory and also in practice. And one of them, Tamuna, also supports communication compression, and the communication compression provably improves the complexity of the method, and in practice it is massively better. So there's really underlying phenomenon, mathematical phenomenon behind this, that you can accelerate the algorithm both through communication compression and through local training steps and through the proper choice of local training method. And so maybe that's about this, and this is also one of the papers co-authored by Ivan in the audience. Okay, any questions you might have about this table? I didn't go through all of this, and maybe I'll mention one or two more things depending on demand. So I can see a question here on Slido. The question is, did I remember correctly that L in the square root of condition number had something to do with Lipschitz continuity? Yes. So L is the Lipschitz constant of the gradient of the function. So you look at the gradient as a mapping from RD to RD. If the mapping is Lipschitz, L is the Lipschitz constant of the mapping, and mu is strong convexity constant of function f. And I'll even mention the definitions a little bit later on in whatever time I have left.
There's also a second question. Could you tell us specific use case where the federated learning is used? For example, in that iPhones, what are they learning and from which data? I think you already answered that partially.
So one of those is the Hey Siri. So you don't want the voice to actually go to Apple servers, but you want your voice to be recognizable. And the way this is trained is through a massive system, which also involves federated learning as one of the components. Yes?
So federated learning, at least quite recently, it seems to be more and more popular in the medical domains, because usually hospitals do not want to share the patient data and so on. But one of the problems is that usually it's quite difficult to agree on the same data structures because the data is from different machines in different hospitals. So when you're mentioning the sampling of the data, we could look from the outlines or anomalies point of view. And if there's some algorithms on identifying those really bad samples, so we could identify that way. Maybe, for example, this hospital is providing bad data, and you should somehow modify it to the unified structure.
So there is bad data and bad data. The bad data you're talking about is the data you would like to throw out, and I have nothing intelligent to say about that. But there could be bad data of the type that it's true data, you could train on the data, but it's just not going to improve your model much. And if you would want to identify that kind of data and not touch the data much because it's not very useful, then we have a solution, and the solution is this grad skip algorithm. And the idea is this. Imagine that on your phone, you have just 3 data points, and that's not going to influence anybody's model, right? And I have 1 million data points and everybody has 1 million, but you're lazy, you don't take photos, whatever, okay? And we want to train collaboratively in a federated learning fashion. The proskip algorithm requires every single phone, including yours, to take square root of condition number local training steps. Could be 1,000. But why should you, who has 3 data points, do that? The Kraskip algorithm is able to identify those clients who have not important data, and they allow them to take fewer local training steps. And in this way, the entire algorithm is going to be more efficient, and the overall communication complexity is unchanged. That's a different notion of good and bad data. OK, so now I'll...
Sorry.
Yep.
I'm sorry to ask a similar question again, but for the example of Hey Siri...
Over there, OK.
Yeah. For the example of Hey Siri, if we do not have access to the data, how do we label the exact moment? So from what I know, in order to detect the keyword that we want to detect, for example, Hey Siri, we have to label the exact moment in the recording.
I don't know. I don't work for Apple.
Okay.
I just don't know how exactly they do it, unfortunately.
Okay, that's what I was thinking, because I didn't know how we could get the training, like the supervised data for the model to be trained.
Yeah, we can ask them. OK.
Okay, thank you.
All right.
There is one slide question if you have time.
OK.
How the research works address differences between full model training in contrast to fine-tuning the part of the model.
Right. So all of this is about training a single model that is going to fit everybody's needs. But it may be the case that such a model doesn't exist, and you would want to think of the model that you train as a maybe meta model that you need to further fine-tune, and there are personalization, fine-tuning methods on top of this, which could be used. And again, I could give a talk on this. We've written some works on that. I'm familiar with the literature, but it's just not going to be something I will have time to talk about. OK, so let me move on to part 5, which is the Proskip algorithm. And I'll try to explain to you, at least at a high level, how it works. And how high level that's going to be exactly depends on how we interact. So here is, again, an overview of a few generations of local training methods, starting with generation 3, generation 4, and this generation 5. And you can see that generation 3 has this complexity. The number of rounds involves this g squared divided by blah, blah, blah. And there's also epsilon in the denominator. And that means the complexity depends not logarithmically on 1 over epsilon, but just linearly on 1 over epsilon. That means sublinear convergence rate. That's what I was talking about before. Generation 4, they have O tilde kappa, where kappa is the condition number, and the O tilde hides log 1 over epsilon. So this is linear convergence, as I was telling you back then. And generation 5 has in this second row square root of kappa. So that's the accelerated communication complexity. So, generation 5, as I mentioned, is the only one that is actually better than gradient descent. So how does this work when you implement things? And I'll implement them in a way which, in some way, some of you will be very unhappy about the way I implemented this, and some of you will be very happy about the way I implemented it. So all of these methods are implemented exactly as analyzed mathematically in those papers. That's how they implement it, which clearly means we're not fine-tuning any hyperparameters. We use the hyperparameters as the theory in the paper suggests they should be chosen, which might be very suboptimal. That's why we do hyperparameter tuning. That's why we tune training, learning rates, and whatnot, right? So if you do that, then our method, the red one, SCAFNU, which is another name for Proskip, because Proskip happens to be a more general method than method which solves federated learning problems. When we apply it to federated learning, we just renamed it to SCAFNU, and the reason is because it's similar to another method which is called scaffold, and we'll playing this name game there. OK, so you can see there's many orders of magnitude difference between the methods. So one way you can think of this is that the gap is really huge, and this is why communication acceleration through local training could be really, really useful. Now, if you look at this plot on the left, what you see is the same experiment, except we fine-tune certain hyperparameters, such as learning rate, number of local training steps, and so on. So we run each experiment multiple times with different hyperparameters, and we report the best. So that's kind of cheating, because you do maybe 10 times or 100 times more work, and then you report the best result. But OK, what would happen if you did that? Well, in that case, some of these methods become almost identical, and one of them almost identical to our method. So one way then you can interpret our method is that it's a good method, but these other methods are maybe also good, these generation 4 methods, except the theory is bad, and the hyperparameters in those papers shouldn't be used. So you can think of our theory and our algorithm as a way of providing formulas for these hyperparameters so that you don't have to do hyperparameter tuning. That's another way you can think of it. Okay. So I mentioned that the method works with stochastic gradient as well. Here are some plots which show that you can do that. That's why you get the little wiggling around. Those of you who are familiar with Nestor of acceleration or momentum, how many of you have heard of this? You may wonder, how does the method compare to that? Because Nestor of acceleration is a different acceleration mechanism, which also goes from condition number to square root of condition number in a very different way. If you run these methods side by side, you'll see that Proskip can do quite a bit better than Nestor of acceleration, which is why we believe it's more useful. And now I'll go through a few slides where I'll try to give an introduction into how the method was actually discovered. Okay, or one way how it could have been discovered. It's maybe not entirely true that it was discovered this way, but it could have been discovered that way. So we start with the original problem of minimizing the average of functions. And the first thing we do, we complicate the hell out of it. Okay, so I apologize for that. So sometimes, in order to resolve a problem, it's good to make it even into a more difficult problem, because maybe then you can see something you couldn't see if you were narrowing down your point of view. So what we do, we lift everything from d-dimensional space into n times d-dimensional space, where n is the number of clients and d is the number of parameters. So this is a massively larger dimensional space. And what we do, we give freedom to every single client, I, and every single client is able to train their own model xi. Before there was just one x. Now every client I has xi. Okay? However, we immediately take the freedom away by throwing in the penalty, psi, which is 0 if all the models are the same, and plus infinity if they're different. So this is mathematically completely the same problem, because if you want to minimize the function, you better stay away from the infinity, and the only way to stay away from the infinity is for all the models to be identical. Okay? All right. However, this trick turns out to be very useful, and it's not our trick. It's a trick which is quite often used in certain areas of optimization, but it was not really used in federated learning before. Now we go one step further, and we notice that this particular function, which is 0 if all of the models are the same and infinity otherwise, it happens to be a convex function. And it's not only a convex function, it's a function which is not always equal to infinity, clearly. There's at least, there's many ways how this can be equal to 0. And its epigraph is a closed set, which means it's a closed function. So in fact, we can generalize this to replacing this penalty by any proper closed convex function. Okay, so this is another generalization. So in fact, what we're thinking of is this formalism, where we forget about the fact we live in this n-dimensional space, and we just think about the problem of minimizing sum of two functions. And this f function will be this one, average of fi's. But now we can just call it f, okay? It can have any structure. And this function is going to be L smooth and mu convex, and this is the answer to one of the Slido questions of what L is, what is mu. So L is the constant L appearing on the right-hand side of this inequality. Mu is constant mu appearing on the left-hand side of the inequality, where dfxy is the Bregman divergence of function f, which is some kind of a distance-like function. Okay, so if you've never seen this before, don't worry about it. L and mu are just some parameters which tell you something about how good your function is. And if L is very different from mu, the function is difficult to minimize. If L is very close to mu, it's easier to minimize. Okay, that's how you should think of it. The ratio matters. And this regularizer, psi, is a proper closed convex function, as I mentioned before. And the key example to keep in mind is the zero infinity function on the previous slide. On top of this, and if you don't want to, you don't have to worry about what closeness, convexity, and so on mean, but if you do, you can read it in the upper right corner. We'll also assume the function is proximable, which means you can compute the proximity operator of this function. Now, what is this proximity operator? It's defined here. If you've never seen this, don't worry about it. It's some kind of operation on top of the function, and you should be able to compute it easily. Now, why am I talking about proximity operator? It's because whatever this proximity operator is, if you look at this particular function, the zero infinity function, this one, and you compute the proximity operator, all that it does, it takes all of the xi's and it averages them. Okay, just keep in mind, applying proximity operator to the zero infinity function just averages the xi's. But what does averaging xi's means? If x1 lives on client 1, x2 lives on client 2, and so on, averaging xi's just means we need to average information across the clients, which involves communication. So evaluation of the proximity operator will precisely represent the communication step when averaging needs to happen. So that's what you should keep in mind. All the other things and aspects of this are not important right now. Okay, so that's this. Now, there turns out to be an algorithm which is very well known. This is textbook content for solving a problem of this type, which is a generalization of the well-known gradient descent method, and it's called the proximal gradient descent method, or the forward-backward algorithm. So what it does, it first pretends that this difficult psi function doesn't exist at all. You pretend, I'm not worrying about it at all. I take a gradient step like this. Okay? I don't worry about psi. However, since the psi is there, you need to worry about it at some point. After you take the gradient step, you take the proximity operator step. Exactly like this. And that's your iteration. It turns out that under some assumptions, this algorithm called proximal gradient descent can solve the optimization problem. And here is a basic theory, which is textbook content, which says if the number of iterations is at least condition number times log 1 over epsilon, and this is just a reminder what the L and mu is, then you have found a model xt, which is epsilon closed from x star, which is the optimal model. So this is a proper mathematical statement, which says, yes, in log 1 of epsilon times condition number of steps, I solve the problem. Okay, so now I mentioned that the evaluation of this proximity operator in the case of federated learning means communication, right? So now you've probably forgotten what I wanted to talk about through all of this mathematics, but keep in mind what I wanted to talk about is I want to understand local training. I want to understand why should I not communicate at every communication round, just like distributed gradient descent, why should I take these local training steps and only communicate after a certain number of local training steps? Well, if you look at this proximal gradient descent method, it turns out you can get an idea how to modify it in order to get the method which takes local gradient steps. And the way to modify it is don't take the prox, don't take it. If you don't do the prox, it will mean all the clients just keep taking gradient steps over and over and over. And at some point, after a certain number of such gradient steps, you take the prox, and then the averaging happens. So the idea is take the prox, but not every iteration, but only every certain number of iterations. So skip the prox, and that's why we call it prox skip algorithm. Okay, so there's the basic idea. And now I'll give you some intuition into how this works. I'll talk about two approaches, and I have 3 minutes for this. So the first one, I'll skip all the prox evaluations. The method is completely useless from a practical point of view, but it's super interesting from the point of view that we can solve the issue why it's useless and make it into a useful method. And that's the approach 2. So approach 1 is this. There is a way to completely remove the psi from the problem, completely. So you can solve the problem in minimizing the sum of f and psi by completely forgetting about the psi. But what you need to do, you need to minimize this function, which is a linear perturbation of function f with a very particular magical gradient h star, which depends on psi. Okay? So this looks very strange. It turns out if you do this, then you have solved the problem. You can minimize this function, you have solved the problem. The problem is you don't know h star. Nobody knows h star. You can only compute h star by solving the original problem, minimizing f plus psi. So the whole idea of prox skip is to let's find this h star iteratively. And we can only do it by at least every now and then computing the proximity operator of function psi. So if you apply gradient descent to this linear perturbation of f, then what is the gradient of this function? Is the gradient of f minus h star, because h star is the gradient of the linear function. So gradient descent applied to that reformulation looks like this. And this is actually almost what proxskip looks like. So the difference from proxskip is that we will not be able to do this iteration because we don't know h star, but we're going to replace h star by some ht which we learn on the way. And the ht will converge to h star. And that's actually how proxskip works. So I have one last minute. So maybe I'll show you the proxskip method, and I stop at this slide. So this is how it looks like. If ht is replaced by h star, that's the idealized method that I mentioned before. But we have ht here. At this point, we flip a coin. And with some very high probability, we just do nothing, which means we remove the head from xt plus 1, and we keep the h vector unchanged. Which just means you keep taking local training steps of gradient type. However, with very small probability, all the clients will communicate because we take the proximity operator, and that involves averaging of the xi's, as I was telling you. So that involves communication. At that point, we change the vector h, and we change the vector x. This is exactly the proxskip algorithm, and the only thing I'm not telling you are these 3 question marks. You can find what these 3 question marks are here. And once you implement this algorithm, you get the method that I talk about. Thank you very much.
Thank you. Let's thank Peter. Peter gave us all 30 minutes for the coffee break, so that's very nice of him. But maybe we can still take some questions. We have 3 on Slido, but we'll alternate.
Hi, I have a very general question. Like modern models usually are very large. They have millions of parameters and potentially take up gigabytes of space. So I can imagine it's hard to store them on millions of devices, especially if they are like mobile devices. So my question is it true that the federated learning is mainly useful for smaller models? And the second question is there some research on maybe that it's possible to somehow break up the model in smaller parts?
Right. So yeah. So the answer is this. Here in most of the research on federated learning, you assume the number of clients is huge. I mean, it could be small, but you allow any number, could be huge. But the model cannot be so large that you cannot store it on all of these devices. And most of the research is on that paradigm. However, there's also a lot of research on so-called vertical federated learning, or federated learning where you also break down not just the data, but also the model. And you can do it in various ways. So there is work on that topic. So for instance, you can think of a setup where you have a neural network and a certain number of layers. Only the first few layers are stored on the device, and further layers are stored on the client. On the server. Or you can imagine a setup where you also distribute the parameters among some of the clients. Or you can imagine a setup where the parameters are divided into 2 parts. One part is the personalized part, which is unique to each client, and the part which is only maintained by the server, which is the same for everybody. So there are approaches to resolving this kind of a question, but you're absolutely right that if the model is large enough, you also have to break down the model. And what I have been talking about does not address that. Yeah.
Next question is from Slido. There is a research on data recovery from gradients, gradient inversion. How do you plan to adapt your approach?
Well, I don't plan to do it, but others already have done it. So you need to implement some formal privacy mechanisms in order to be able to defend against stuff of that type. So for instance, differential privacy or encryption and so on. So you have to do something on top of what I talk about to protect the data. Without this, obviously, you can do any kind of attack of this type and you can recover something.
Thank you very much for the talk. Understand that we're trying to get bounds for supervised algorithms.
Right.
My intuition, however, tells me that if you used a non-parametric model with a distributed setting, you would, correct me if I'm wrong, but you'd probably need less synchronization because you don't have to send back the weights or something. Is there any interest in this, or can you think of any useful case?
So there is this, as I mentioned, there's this field of federated analytics as a super field of even federated learning, which aims to do federated anything, even unsupervised learning and so on and so forth. So there is research on that, but it's fairly recent, maybe 2-3 years and not 7 or 10. So it's definitely interesting. What I talk about definitely doesn't apply to it, but one can think of trying to extend in the direction.
Sorry, is the intuition correct that you need less synchronization for this?
I don't know, and I don't think so. But I don't have that intuition. I don't see the reason for that.
What is the state of the art of federated learning for non-convex functions?
I would need another hour and a half for this.
So he knows.
So
talk to him.
I can talk about this, so I'm familiar with it. We've contributed to that too. So for instance, you can look up algorithms such as Marina, Dasha. We like to give names like this to algorithms. Or you can look at an algorithm called two-direction, which compresses in both directions. So these are methods that also work in non-convex setup, have at the moment the best theoretical guarantees there are for communication complexity under non-convex setup, smooth non-convex setup, but there are also limitations, obviously, and this is why we have job as researchers, we try to remove those limitations. So for instance, at the moment, they don't work with non-smooth, non-convex optimization, and many models actually are at least partially non-smooth. They don't work with adaptive learning rates, such as ADAM and so on, etc. Yeah.
Usually, you use the proximal operator to apply some regularizer to your parameters. What is that in your case?
So here, I use it because the proximity operator applied to the zero infinity function exactly means communication. If you write down what the proximity operator does, it means averaging of the local models. So the proximity operator in this case has that interpretation. But the proxy algorithm is more general and works with any proper closed convex function, but the application to keep in mind is federated learning. However, this could be, you can have application for general constraint optimization, where the constraint is encapsulated inside the function psi, the proper closed convex function. And in that case, proximal gradient descent turns out to be projected gradient descent, where you take a gradient step and project back onto the constraint set. In this case, what we do, if the projection is complicated, the proxy algorithm avoids most of the projections and becomes more efficient because of that.
How do you select the learning rates for each worker?
We have a formula for that, and it's actually the same formula as you would have just for gradient descent. It turns out, in all prior works, the formula is that the learning rate has to be k times smaller than the learning rate if you were training alone, where k is the number of local training steps. And this is the reason why all the methods had bad theory, because the learning rate had to be decreased by the number of local training steps. So you take 1,000 local training steps with 1,000 times smaller step size. This is roughly equivalent of just taking 1 local training steps. But it's not that those people were stupid and didn't know not to do it. They just couldn't do it otherwise. So the theory wouldn't work otherwise at that point in time.
Thanks for the talk. It seems that this kind of stuff might be similar to something like distributed computing or like voting.
Absolutely. This is massively distributed computing in the world.
Like, are there kind of a relationship in the research with something like, okay, each worker can kind of do some kind of computation on a specific problem that the server has, and how they communicate in this sort of
I thought of this once. I would be really interested in thinking of this direction. So all of this is related to optimization, but maybe there's a more general stuff to be discovered behind this. And a former student of mine, without me, with his student, they discovered something of this type, so they can solve so-called variation inequalities, which is a more complicated problem than optimization, using the same proxy idea, and they can do it. But maybe there are other distributed non-optimization problems that could be solved with this kind of a trick. Yeah.
In ProcSkip, I understand probability P is global and propagated from the main server to the clients for each training step. I had to do this my own question, but I'm also curious, could you have the props keep every worker each own probability and send it and so completely asynchronously update the gradients?
No, we don't know how to do it. If you can figure it out, you can write a paper. But what we did figure out is that if somebody has less important local training data, you can take fewer local training steps, and the way that actually works is through everybody having their own probability and flipping their own coin depending on the quality of their own data, and they can then communicate sooner. But we only have this in this Gradsky paper, which was in the table.
And they communicate sooner, and then the global...
They can communicate sooner because they can be done in fewer steps, but then the server needs to wait for everybody. So it's not a fully asynchronous method.
We have a final question. What is the intuition behind the fact that the compressing data improves the performance of the method? This idea seems a bit counterintuitive.
It's the same answer that I would give. So if you ask me a question, I'm going to say a few words and everybody understands, right? We communicate in a compressed fashion. Language is compressed communication. We know what the words mean. I say a few words and all of you know what I mean. I'm not going to give you a whole essay and book around just to answer a question. It's the same reason. So we evolved language because it's more optimal than communicating without language. And it's compressed communication. And in the same way, compressed communication in optimization algorithms is actually more optimal, even theoretically, than non-compressed communication.
This philosophical finish is perfect for a coffee break. Let's see each other in 11.
Do you hear me?
Yes.
Okay. Okay.
Can you hear me okay?
Yeah, we can hear you.
All right.
Cool. Perfect. Yeah, so we're still waiting for people to get into the room.
Sounds good.
Where did I? Aha. Okay. Okay, so I think we're gonna start. So welcome back from the break, everyone. It's my greatest pleasure to introduce our next speaker. So we have Dojna Prikop. I'm pretty sure everyone heard the name. She did her PhD with Rich Sutton. She's now a professor at McGill University and Mila, and also at Google DeepMind, Montreal. She's probably best known for her work on options in RL. And since 2018, we've co-organized EML together, and she definitely is a mentor for me. When I started DeepMind, I did not know anything about RL, and so getting into that was an experience, and having people like her around definitely helped a lot. And with that, yeah, I'll leave it to Dojna to do an introduction on RL. Thank you.
Thank you very much, Razvan, for the kind introduction, and hello, everyone. I'm sorry that I cannot be with you physically in Košice, but I'm very happy that you are attending the school, and I hope you're enjoying the week. I will talk today about reinforcement learning, and this will be followed up by Michal with another lecture on the topic, and also with a tutorial later on today. So what is reinforcement learning? It's a way of learning for intelligent agents that interact with an environment. And its inspiration has come a lot from psychology and animal learning theory, where you might have an animal like this little mouse here, who's in an environment, gets perceptions from that environment, can take actions in the environment, and as a feedback signal, receives a numerical a reward. So in the case of the mouse, maybe this is food. In the case of an automated agent, like the ones that we're going to talk about, this would be positive and negative numbers. And the goal of the agent is to maximize the cumulative signal of reward over time. And there are two important characteristics of reinforcement learning compared to other types of learning. One is that the agent is never told the right thing to do. Instead, it has to try things out in the environment and learn from the reward feedback. So it's a trial and error learning. And secondarily, the reward is often delayed compared to the time where good or bad actions might have happened. And this leads to an interesting problem of doing credit assignment over time, figuring out which of the agent's actions has actually been good or bad. And so this is just a little example from the DeepMind work on AlphaGo and later on AlphaZero, where there are agents that are trained to play games. In this case, there's the game of Go, which is a complex strategy game. There is a board with black and white pieces, and so you can think of the agent's perception as the state of the board. And the actions in this case would be the legal moves that the agent can do, but the reward is only received at the end of the game, and the reward might be +1 if the agent wins the game and -1 if the agent loses the game. And so you might imagine that the agent might have taken some, for example, some really good actions in the middle of the game or even at the beginning of the game that set it up for victory. But this link between the end reward and these actions needs to be made. And so in order to do that, very often these agents need a lot of data in order to sort of notice the correlations between particular states or perceptions that the agent had, actions that the agent took, and this final reward. Now, how do we get an agent to do well in a game like this? Well, we're going to talk about two components of the agent's knowledge. One is a policy. The policy is a way of acting. It maps perceptions into actions. And this might be done through, for example, a deep network that outputs the probability of an action given the agent's current state. So this is called the policy network here. And then in order to sort of figure out how to take these actions, we're going to use a guiding signal that is called the value function. And the value is essentially the expected return or the agent's guess at the expected return. That means the agent's guess about the probability of winning given a particular situation on the board. And so this might be represented also by a deep network. So we're going to talk about policies and value functions and about various methods for learning policies and value functions from the agent's interaction with the environment. Now, in the case of a game like Go, the agent has to play against someone. And so, in fact, in this case, the agent is trained by playing games against a copy of itself. And this is interesting because it means we can generate lots and lots of data, experience-based data. Obviously, the agent has to have some randomized way of choosing actions in order to explore the possible space of actions. But the advantage of using this kind of setup is that we don't have many preconceived notions about how things should be done. And instead, the agent is free to invent new ways of playing. And in some cases, like, for example, in AlphaGo, these ways of playing can be superior to knowledge that people had before. And so that is very exciting because it gives these agents perhaps a way to go beyond the level of play of people and in general to be able to attack problems in ways that were not known before. Now, there's been a lot of applications of RL. This is just a sort of historical list, starting with backgammon, which is work by Jerry Tessaro at IBM back in the early 90s, and which has actually a lot of the ingredients that we're going to talk about, including the use of neural networks in order to represent value functions. There's been applications in the physical domain, like helicopter control, in ad placement, in language models and various dialogue systems, starting with the work on Jeopardy, and of course continuing these days with a lot of reinforcement learning from human feedback. And in all of these cases, performance that was obtained by these RL agents was better than what could be obtained by other methods. And in the cases that are listed here, it's actually obtained by human, but by an agent interacting with the environment and learning from a numerical reward that was coded, not from human instruction. More recent work, like reinforcement learning from human feedback, moves into the space of getting some input from humans. I wanted to show you two of my favorite recent successes of reinforcement learning. One of it is work published in Nature in 2020, where reinforcement learning is used to learn how to control these loon balloons that are flying around in the stratosphere. And in this case, you want the balloon to sort of stay as close as possible to a particular geographic area. But what you can do is to sort of move it up and down, and then the balloon has to sort of catch appropriate wind currents in the higher atmosphere in order to be able to stabilize itself and to stay close to this goal position. The other picture here is taken from a paper from colleagues at DeepMind in 2022, where reinforcement learning is used to stabilize plasma in a fusion reactor and to sort of create particular configurations of this plasma. So in both of these cases, what we have is very complex control tasks where actually we don't really know how to solve the problem, especially in the case of plasma. You know, if we knew how to solve these types of problems well, we would actually solve the problem of clean energy and perhaps be able to mitigate the effects of climate change that we have now in the world. So this is a very important real problem, and reinforcement learning can help us to start getting a handle on it. I also wanted to show you another example of a reinforcement learning problem that I've been working on recently with colleagues at McGill and at Mila, which is the problem of molecule search. So imagine that you want to design, let's say, a medication for a particular disease. We might imagine this process as a sequential decision-making process where you start with an empty molecule and then you add building blocks to this. And as you're adding building blocks, at some point you might decide that you are done and you can evaluate how good this molecule is, for example, by estimating a docking score with a particular chemical target or with the docking with a particular target protein. And you know, if we like this molecule, then we can keep it, and eventually we might collect a set of these candidates and send them to a lab for actual testing, more thorough chemical testing for other properties as well. So you can think of this process as a reinforcement learning process in which the state is the current molecule that we have. The space of actions are these building blocks that we can add or remove if we want to also consider removal. And the reward is only received at the end. In fact, the reward may be very delayed if we really want to have ground truth reward that comes from a lab. And so we have this problem of trying to figure out how to navigate this space, which is extremely large, and how to do the credit assignment effectively from these trajectories. So there are some key features of reinforcement learning. We have this trial and error search where the learner is not told what actions to take, but has to sort of figure this out by itself. Oftentimes, this relies on simulations. we may have a stochastic environment. So for example, if you're playing a game, you're playing against different opponents. They have different strategies. So there's some randomness in the trajectories. The reward may be delayed, and there may in fact be trade-offs. So for example, the learner in a game may need to sacrifice some short-term gains for the longer term. And finally, we have this feature of having to balance exploration of the environment, so trying many different actions in order to understand their effects, and exploitation, where a learner actually tries to take advantage of its current knowledge. Now, reinforcement learning has developed at the intersection of many different fields. On one hand, machine learning, optimal control, and operations research, which are more computational. On the other hand, a lot of work in animal learning theory, psychology and neuroscience, looking at classical conditioning, reward systems, and also in economics, work that looks at bounded rationality. And so there's a lot of different areas that have contributed ideas and methodologies to this field. And also reinforcement learning, it is used to model problems and solve problems in all of these fields as well. So we're going to talk a little bit about the computational framework now. We're going to imagine that we have an agent that's embedded in an environment. For simplicity, I'm going to assume that we have a clock and that every time step, the agent is going to perceive its environment. Based on this perception, is going to choose some action. That action is going to cause a numerical reward, which could be 0, could be positive or negative. And then the time ticks again. We're going to end up at time step t+1, and this process is going to repeat, possibly until the end of an episode. We're going to talk about this in a minute. And so the goal of this agent is going to be to find a way of choosing actions, which we're going to call a policy, that maximizes the long-term expected return. And just a little bit of notation, the agent's perception we're going to call a state. It's denoted here ST. The action is denoted AT. The reward here is R. So RT is the reward at time step t+1. And the interaction is going to go on these discrete time ticks. Now, I just want to contrast for a second supervised learning, which probably you are much more familiar with, versus reinforcement learning, just to give a sense of what are the differences and what are the extra challenges perhaps in reinforcement learning agents. So in supervised learning, you have an agent that takes an input, could be this perception that the agent has, and it produces an output. And the training information is a desired output. So in the case of, for example, teaching an agent how to play a game, what the agent outputs is an action, and what I might sort of feed in as the desired output is what the agent should have done in that situation, what would have been the correct or optimal action. And then if we can compute an error between the target output and the actual output and use this error to train this box here, which might be a neural net or some other function approximator. In reinforcement learning, we have the inputs, the outputs are actions, and the training information is just this evaluation of rewards or penalties. And our goal is basically to get as much total reward as possible in the long run over the agent's entire trajectory. And so the training information is much more loosely connected with what we are outputting from the agent. The agent outputs actions, but the training information is related to these rewards. And we're going to need to figure out what would be good error functions. And part of what I'm going to talk about is what kind of training information, what kind of error we feed to this agent. But once we have this training information, the process of training the agent is going to be exactly the same. We can have a deep net, we can use backpropagation, and any of the tricks that one normally uses to train deep networks. In some sense, think of this as just using a different appropriate error function for agents that interact with their environment. Now, what's the agent's learning task? The agent is going to execute actions in the environment. It's going to do this using a policy, which is denoted pi here. The policy, think of it as a mapping from states to actions, but we want to allow for stochastic policies in general. because the agent has to explore its environment, okay? And so in general, this policy is going to be a probability distribution over actions at time step t given the state at time step t. We can make this deterministic if we want. And of course, if we knew the correct deterministic policy, that would be the ideal. And we're going to strive to obtain that. And even though what we want is a policy, we don't really have examples usually of the form state and action pair. That is a setup called behavior cloning or imitation learning. If we have that, in general, in reinforcement learning, we have trajectories of the form state, action, reward, next state, and so on. And so a lot of the methods that we talk about specify how we should change this policy as a function of the rewards received over time. And I'm going to discuss, hopefully I have time, 2 different classes of methods for doing this. Now, the agent's goal is to maximize the expected return. G here, GT, denotes the return from type step t or onward. And there's different ways of defining what return is, which are all sort of taking into account the future of the agent. One way to do it is just to look at the sum of the rewards received over time. We call this total reward. Okay, and this is very much appropriate when we have tasks that end. So episodic tasks where the interaction breaks down into, let's say, plays in a game or trips through a maze and so on. And so here we're just summing up the rewards obtained from time step t plus 1 until the end of the episode. And so one example is this little illustration called mountain car. It's a canonical control problem that has been used in reinforcement learning for a long time. It's a very simple benchmark. You have this car that you want to drive to the top of the hill, but it's not quite strong enough to just accelerate to the top of the hill. And instead it needs to build momentum by sort of swinging back and forth until it gets to the top. So now the question is, how do we formulate this as a reinforcement learning problem? In terms of the perception, we can think of the perception as the position and the velocity of the car. We can think of the actions as accelerating forward and backward. And in terms of the reward, one way to set this up is to say we are trying to minimize the time to goal. And so we're just going to penalize the agent that's controlling the car with a -1 for every time step where it's not yet at the top of the hill. And whenever we get to the top of the hill, then these penalties stop and the episode terminates. And so this is an example of an episodic task using total return. Now, in some cases, we want to think about a continuing interaction where we don't have natural episodes, or maybe we don't know how long these episodes ought to be. And in this case, we still want to have returns, and we want to make sure that these returns are finite, right? Because otherwise it's going to be very hard to work with them. And so in order to do this, we can use discounting. Okay, so a discounted return takes the rewards, but rewards that are received farther into the future are considered less important. They're delayed, right? And so therefore, intuitively, they might be more uncertain and we want to count less on them. And in order to implement this mathematically, we may use a discount rate gamma. And you imagine here perhaps that gamma is the probability of the agent continuing its trajectory at every time step. And with 1 minus gamma, the agent might stop and receive rewards of 0 thereafter. And so gamma between 0 and 1 is the discount rate. And the closer this is to 1, the more far-sighted the agent is, the more it cares about the longer term. And so this is something that we pick very often as a designer of the system, although there's been interesting research work trying to adapt gamma or maybe trying to do a curriculum where you start with a short-sighted agent that cares about immediate rewards and then it becomes more interested in the longer term. And so here's another example of a task just to give a flavor for what these discounted returns are like. This is a task called pole balancing. So here you have a little cart that's on a track you have a pole that's on top of this this cart, and what the goal is to keep the pole as close to the vertical and not let it fall beyond a certain critical angle. And we also want to make sure that the cart doesn't hit the end of the track. And you can think of this now as an episodic task where we might reward the agent +1 for every step before the pole actually falls. And so in this case, it would be a total return, a total reward criterion. But we can also think of this as a continuing task with discounting. And so in this case, the reward is -1 when the pole falls over. And we can use discounting that's less than 1. And so this would mean that the return of the agent is minus gamma to the power k, where k is the number of time steps that the agent goes through before it fails. And one thing that I want to point out is that both of these formulations are valid. And in fact, in both cases, the return is maximized when the agent avoids this failure mode for as long as possible. And so we can have different ways of formulating a problem, of defining a reward function that all correspond to the same kind of optimal behavior, but some of them might make it easier or harder for the agent to learn. And so, for example, in this case, if we have a very sparse reward that's mostly 0, except when the agent fails, it might actually take the agent quite a long time in order to figure out what to do, because there isn't enough information in its trajectories to kind of signal what are better actions or worse actions. And so there's also a very interesting literature on reward shaping. So how do we define reward functions, not just so that we can obtain a good policy by optimizing the corresponding returns, but also so that we can do so quickly with less data if possible. Now, we're going to talk about value functions, which are used as a helper to sort of guide to the agent. And we can have state values or action values, and we can evaluate fixed policies. This is a case called prediction. It's just easier to think about and easier to handle mathematically. Or we can try to find the optimal policy. And so in this case, we have these quantities V star and Q star, which are called the optimal value functions. And we might try to estimate them and use them to guide a policy. So these functions that are in this table here are expected values. They're mathematical ideals. But in general, the agent is going to maintain some estimates of these, denoted here, VT and QT with capital letters. And you can think of these as random quantities that are based on the agent's trajectories. And so what's a value function? It's the expected value of the return, okay? Because the return is the quantity that we are interested in optimizing. And when we have a fixed policy, we can take this expectation under this policy, as well as obviously under the stochasticity in the agent's environment. And the difference between the value of a state and the value of an action is what we condition this expectation on. So V pi, which is the state value function, conditions the expectation of the reward on the agent state, whereas Q pi, the action value function, conditions it on the state as well as the action. And so the way that we think about Q pi is that the agent at the very beginning of its trajectory is allowed to do something different from policy pi, is allowed to try an alternative action, denoted little a here in the bottom equation. And then afterwards, it's continuing according to its current policy. So Q is an interesting quantity because it allows the agent to think about deviations from its current policy and to do some exploration to figure out other actions that might be better than its current policy. And so this is just a very quick example of what a value function might look like. This is a small navigation task where the agent can move up, down, left, and right. It's got some jumps also that it can make, and these jumps have particular rewards of +5 and +10 in these two cases. And we can imagine this agent acting uniformly randomly in this environment. And we can compute a state value function for this random policy, which is depicted in picture B here. And so one thing that I want to point out here is that this value function is telling us what are good states and bad states, right? So for example, state A is very good, has a high value, 8.8, because afterwards we can make a jump to state A prime that is very highly valued. Okay. At the same time, state A prime is not so highly valued, because from here, it's going to take a while for the agent to return to the states A and B and the other states in the top row, which are highly valued. Now, how do we estimate value functions? The simplest way to do it is what we call Monte Carlo. And so in this case, you might imagine an agent that is doing trajectories according to its current policy, observes the returns on these trajectories, and then uses these returns as targets in a regression problem. Okay, and so here, for example, we are at the state ST, which is represented by an empty circle. We have different choices of action. The black dots are choices of action. We make a choice that's consistent with our policy, for example, by drawing the action from the distribution conditioned on ST. And then the environment responds by giving us a next state, right? And so this next state is drawn from the distribution of the environment. And we then continue this process all the way until we reach a terminal state depicted in green here. We get this sort of red trajectory. There's a particular return obtained on this trajectory. And we can use this return as a regression target for state ST. And in this equation, we also have alpha here, which is a learning rate. It's the usual thing in learning, number between 0 and 1. And obviously, we can use second order methods and so on, other tricks that you'd normally use in order to move the estimate V towards this regression target G. Now, one thing that I want to point out is that even though this looks a lot like supervised learning, it's not quite supervised learning, because we have a whole trajectory and we're going to have a whole bunch of examples of states on this trajectory and their following returns. And so the data that we receive is correlated. There's correlation both in the inputs, because the states are the result of taking actions. Okay, there's also correlations in the output, because the return has a nested structure where the return at one time step is a reward plus the return at the next time step. We're going to talk more about this in a minute. And so these correlations actually make this problem interesting, even though it looks a lot like supervised learning. So this is an algorithm called Monte Carlo. We can obviously do it with function approximation. And the natural objective, if we're just trying to fit values of policies, is to minimize the squared value error between these estimates that we're getting and the sort of true targets. And here we're going to think of this squared value error as being weighted by the probability of being in different states under the current policy. So think maybe of this as the fraction of the time that the agent spends in a particular state. And this is just an example from the book of how to implement it. And we might actually practice a little bit later how to do that. Now, what do we do if state spaces are very big? We're going to use function approximation. And so just to give you a flavor, I'm going to show you a very simple example where a function approximator is just a discretization. This means we take the states and we put them in bins, and the states that end up in the same bin all have to have the same value. And we're going to look at a random walk problem where we have an agent that starts in the middle of a segment of states here and can jump randomly left and right until it hits the end. Okay, and at one end we have a +1, at the other end we have a -1, and we're just trying to estimate the expected value that the agent is going to get. And we're going to do this by, again, putting the states in bins where a group of adjacent states has to share a value. Okay, so Now the discretization allows us to have a finer or a coarser estimate of the value function. And if we use Monte Carlo to do this estimation, we have the true value function, which in this case is a 45-degree line. It's this red line here. And the estimate that we're getting is this blue staircase line that is approximating the red line, but can't do it perfectly because we've reduced the capacity of the approximator. And so we're going to have some systematic errors here that are due to the fact that we've aggregated states into bins. So I'm going to stop there just for a second and see if there are any questions.
Any questions from the room? Oh, okay. I have one.
If we teach a model to behave in some circumstances, for instance, in this case with balancing platform, can we start with, for instance, a simulation and then like fine-tune the model to for the real environment?
Yes, absolutely. Excuse me. This is called sim to real. It's actually a good strategy for robotics tasks where you might start with a simulator, but the simulator is not perfect. So you can get an initial policy for a real robot and then actually run it in the real environment, collect the data from the environment, and basically continue feeding it and continue training. And of course, there's a couple of things. So first of all, you sometimes still need to allow the agent to explore in the real environment, in the physical environment, in order to understand well the discrepancies. And secondarily, we may want to sort of emphasize more, perhaps, the data that's coming later on from the real environment. So we may consider how we weight the data coming from the two. But yeah, this is something that is quite useful.
Okay. Before going to the next question from the room, I wanted to add a question from Slido, just because it's very related. So the question basically is, how similar should be the simulation environment and the real one to train the agent? So very connected, but like, yeah, there's any sense of the similarity in sim to real?
Yeah, so there's, obviously the more connected, the better. There are ways of quantifying, for example, if we train something in simulation and then we deploy it in a real environment, how much penalty do we incur? And so there are distance metrics that can be used to tell us how different the two environments are, and we can bound the difference in value function for the same policy, depending on these distances. Empirically, oftentimes people use things like KL divergence in these types of results, but we can also use things like bisimulation metrics, for example, which are perhaps a little bit stronger in terms of bounding these differences. The problem with the theoretical results in this area is that we often actually don't know how different the real environment and the simulation are. And so we may, we have theoretical results that impose these bounds, but we may not know for sure how much worse, for example, a policy might be in the real environment than it is in the simulation.
Hello, my question is if there is some difference if you train for regret or reward.
In terms of theoretical results, yes. So let me say a little bit. So regret is a quantity that compares the agent's returns to an upper bound. And this upper bound is oftentimes the optimal value. We will define that in a minute. And so regret minimization basically says, how can I reduce the difference between how much returns I'm getting now with my current policy and the best that I could possibly do. And this is very useful, for example, for proving sample complexity bounds. And I recommend talking to Michal about that, in fact. But oftentimes when we are in practice, we don't have the reference point, right? So the algorithms themselves optimize return. And, there's equivalences, right? So if I have an optimal policy, the optimal policy obviously is going to have no regret. But very often, the flavor of result that we want to obtain is talking about the training process itself and minimizing regret during the training process. This means how fast can we approach the optimal reference point.
Cool. Another question from Slido. Can DeepRL work with a variable number of actions?
Yes, and so one way to think about it is we're going to feed the action description as an input to a neural network. Let me see, I have a picture of a neural net here that takes in actions somewhere here. So one way to do DeepRL with action value functions is to take as input both the state and the action. And if the action has some description, then we can have however many actions, it doesn't really matter. We represent them all through their embedding. And so the number can be variable. And essentially, we're going to have a loop where we might evaluate a bunch of these actions.
Awesome. Another question from Slido. For development of control algorithms for critical and capital-intensive assets, can DRL be implemented? What are some examples of this in practice? And finally, what can we do to ensure that the agent doesn't take drastic actions that could damage the environment?
Okay, so the first thing about the capital, so in principle, this can be formulated as an RL problem. Has this been done in practice? I don't know. And, while there has been quite a bit of work implementing RL in financial problems, how that's done is not very much in the open knowledge, right? Because typically, if something works, you will not find out about it in that kind of implementation. So financial institutions tend to keep these as trade secrets. But in principle, one can think of, what's the state space? How do we, what information do we want this agent to look at? Maybe it is, for example, a history of investments. Maybe it is even these days text, right, about the context of the market and so on. Actions, what do we want the agent to be able to do? And then maybe returns in the case of capital markets might be an interesting reward. The main tricky thing in this kind of application, of course, is having the ability to train either from existing batch data or from a simulation where we have the ability to generate enough believable data. In terms of how to generate actions that don't damage the environment, there's one way to think about this is we can restrict the policy of the agent, the exploration policy of the agent, so that we outlaw actions that we know would be damaging. And this has to be done when, for example, the agent is interacting with a physical environment, like in the case of real robotics. If we're working in simulation, we can allow the agent to try out wilder actions and simply observe the results. And if the agent is optimizing its returns well, it will learn not to do those actions. And so both of these strategies are possible.
Okay, so we know that a lot of the theoretical results from the literature somehow are based on the fact that the state representation is Markovian. How do we make sure that this still holds when we use state aggregation? Don't we somewhere lose this property?
Absolutely. So state aggregation and all of the other function approximation, neural nets, etc., all lose the Markovian property. And so the results, the theoretical results with function approximation are simply a little bit weaker than the results with tabular representations. The algorithms still work quite well in practical applications. So all the examples that I've talked about before actually use function approximation. And in some cases, for example, linear function approximation, we can relate the performance of the agents with the quality of the function approximator, the resolution of the function approximator, and so on. But there's still a big gap between what we know from empirical results and the kinds of theoretical results that people have been able to establish. Now, actually, for my own research, one of the things that I'm really interested in is what happens when we don't have the Markovian property. What can we say about RL agents? And we're trying to make progress actually on the theoretical results in that case as well.
Okay, thank you. I'll just do one more question, and then maybe we can go back to slides so we have time. So it's more of a philosophical question. So the question is, among learning types, which learning do you think approaches most the human learning? Is it RL just because it has sort of this trial and error flavor, or do you think that's not the case?
So that is a very philosophical question. Obviously, I work in RL because I find it the most believable from a sort of biological compatibility point of view. Because you have the situation where the agent is embedded in an environment and can learn by trial and error and has a sort of looser reward signal. But, I think there's very likely a mixture of unsupervised, supervised, and reinforcement learning that goes on in biological systems. Certainly, if we think about us, right, there's some amount of, just unsupervised learning. There's rewards, right? And then there's also instruction and, imitation. And so probably there's a mixture of all these things.
Cool. Thank you. Let's go back to the slides, and there are going to be more questions at the end.
Yeah. So we've talked about, somebody mentioned in the questions, the Markovian assumption. The Markovian assumption is a simplifying assumption about the environment that allows us to build algorithms that are more precise in certain situations and also more efficient. And the assumption here is that the reward that the agent gets and the next state are drawn from a distribution that's only conditioned on the current state and the action. Now, one way to think about it is if you have some information that's relevant for the agent's transition on the next time step, that should be summarized in the agent state. And so you can think of this as an assumption on the environment, but you can also think of this as something that's basically on the agent to do. Like the agent could take its history and summarize it into a set of features that are sufficient to make this prediction of the very next time step. And in this case, when we have the Markovian assumption being satisfied, we actually have interesting optimality results dating back to the days of Bellman in the 50s. Basically say that in a Markovian decision process, we have a unique optimal state value function and corresponding optimal policies. And these are policies that are better than or equal to any other policies in terms of expected return. And these policies share the optimal action value function. And so that's actually quite an interesting result because it basically says, if we got a hold of an optimal state value function or action value function, we could then derive an optimal policy out of it. And so basically we can, if we had an optimal value function like the one that's depicted here for our environment before, we can read out of it an optimal policy by considering at every state what are the actions that have the highest expected value. And if we have actions that are tied, we can make an arbitrary decision between them. For example, we can choose randomly between them. And so optimal value functions are very powerful objects. And if we had an action, optimal action value function like Q star here, we basically can read off the optimal policy out of it by always taking the action that has the optimal value. Now, in the Markovian case, we can use Bellman equations in order to do these computations efficiently. And the Bellman equation is based on the idea that we can take a return and decompose it into an immediate reward plus the return from the next time step onward discounted. Okay, so the reward, the return GT is the immediate reward RT plus 1 plus gamma GT plus 1. And so the value function which is an expectation, can then be decomposed using linearity of expectations, and we get systems of equations where the value of a state is expressed in terms of the values of the next states. Okay, and so at the bottom of the slide, you have as example the Bellman equation for a fixed policy pi and for its corresponding value function. And then we can solve these systems of equations iteratively, right? For example, by starting with a particular guess, like the value is 0 at all states, and then taking a model of the environment, if we have one, P and R, and just applying this as an update, okay? And so that's what we call dynamic programming. And the way that we think about it is if you imagine the agent being at state ST, it considers all the possible next actions that it could do, considers all of the transitions to next states that might happen, and is going to estimate the value of ST by doing here a one-step look ahead, okay? And this look ahead actually requires us to know the model of the environment, rewards and transitions. And so I just want to contrast this with Monte Carlo, which is sort of a depth first look ahead, okay? And one way to think about a lot of RL methods is that they do something in between, okay? So instead of doing a depth first look ahead all the way until the end of the trajectory, they might do a look ahead just over the next time step, okay? And then use the dynamic programming idea to say from the next time step onward, the value would be whatever I'm currently guessing, okay, for this next state, ST plus 1. So rather than taking the returns all the way until the end of the trajectory, we'll look at the first reward and then the value of the next state V of ST plus 1. And we will use this to approximate what would be a full return. So this is truncated, and it's using bootstrapping. It's using our current guess for the value V in order to make a target. And this target can be used exactly on the next time step. And so compared to dynamic programming, one way to think about this type of algorithm is that we are, instead of doing a full expectation here at state ST, we're sampling from that expectation. We're using the one time step sample. And if we did this over and over again, of course, on average, we would actually obtain the expectation. So this is what we call temporal difference learning, or TD. Temporal difference learning because our learning signal here is the difference between our current estimate of the return via ST and the estimate that we would obtain on the next time step after we've carried out one more action. And we still have a learning rate just like the usual. So this TD prediction is just the estimate of the return at the time step t plus 1. And compared to Monte Carlo, of course, this is going to be more imperfect because it now relies on the agent's guess, okay? So unlike Monte Carlo, which uses truth, right, returns that are obtained from the environment, here we're relying on the agent's guess. And in terms of the implementation of this with value function approximation, this algorithm is going to not quite be gradient descent. Okay, so in gradient descent, you have an error function and you take its derivative and use chain rule, okay? And if we did this in our case, we would have our target here, and our target would contain the agent's current estimate V hat, which is parameterized by theta. But actually, when we do temporal difference learning, we kind of pretend that the target is constant, doesn't depend on theta, okay? It's independent of theta. And so we're going to take our gradient only with respect to V hat, okay? Pretend that only at the current state we're actually parameterized. And we can do this with value functions or with action value functions. And also, I just want to emphasize that the target depends on the agent's behavior. In temporal difference learning, also depends on its current estimate, okay? And so what we're doing here is really not a gradient based algorithm, yet we can show convergence properties for it as well. Now, what does this algorithm do? I just want to give you a little example just to illustrate the difference. So imagine that you saw this data where you have a bunch of trajectories First one, you have the agent is in state A, gets a 0, state B gets another 0. Then we have a bunch of trajectories, 6 of them here, where the agent is in state B and receives a 1, and then one more trajectory where the agent is in state B and receives a 0. And let's assume that we have a Markovian property and there's no discounting, and I'm asking you what's the value of state B and what's the value of state A. Okay. Well, the value of state B maybe is pretty easy because we have here 6 ones, right? So the estimate should be 6 on 8 since we've observed 8 transitions. Okay. But what's the value of state A? Well, in Monte Carlo, what we would do is we would say we have one trajectory where state A appeared, it had a return of 0. And so the value of state A, we're going to guess it to be 0. Okay. In temporal difference learning, however, the way we think about it is we've observed this trajectory, and our belief about this trajectory is that we have state A, which transitions to state B, okay? Because that's what we observed on this trajectory. And then state B might get a reward of 1 or 0, but the value of A is going to be based on the value of B. And so we would guess that the value of state A is actually 0 plus the value of B, which is 6 on 8. Okay. And so one way to interpret theoretically what temporal difference learning does is that it sort of implicitly fits a model of the environment, a Markovian model of the environment, and then the value that we're going to move towards is the dynamic programming solution to that model. Okay. So while Monte Carlo methods are gradient-based and they converge to a locally optimal of the mean squared error weighted by the state visitation, temporal difference learning methods conceptually fit a Markovian model of the environment and then approximate the solution to that model. And so one way to sort of conceptualize what's happening here is that we have a bias variance trade-off between these kinds of methods, where temporal difference learning introduces some bias in the estimates. The bias is coming from this Markovian assumption, and that's going to help us to reduce the variance. Okay, and so this is illustrated in this picture here, where we're looking at the same random walk as before. The blue line here is the approximate TD value. You can see that compared to Monte Carlo, we have some extra errors, especially at the ends here. Okay, where the line is sort of askew from the true value. But the ordering of states is the same, okay? And actually, we can obtain these estimates faster, typically, than when using Monte Carlo. Now, whenever you have bias and variance trade-off, you usually have some knob that you can use to go between them. And so in temporal difference-like methods, this knob is how far ahead do we look? So if we have these trajectories where you have state action next state, and we're making truncated estimates of the return on these trajectories, we could choose to use Monte Carlo, which is going all the way until the end. We could choose to use one-step TD, which is what I showed you before, but we can also use n-step TD, which means we take n rewards, and then we use the value of the state that we arrive at. And this value, in the case of discounting, would be multiplied by a gamma to the power n. And so obviously we rely less on this value. So as we go from temporal difference learning to Monte Carlo, we reduce bias and potentially increase variance in these algorithms. And it's very easy to write down what these algorithms are. It's still truncated returns. The two-step, for example, is written here, has the RT plus 1 plus gamma RT plus 2 plus gamma squared times the value estimate of the state at time step ST plus 2. And the effect of using this kind of n parameter is that we can get better with a fixed amount of data. So here we're looking at the average root mean squared error in a random walk example like the one that we've seen before. Over the first 10 episodes of the agent's experience, we're doing just policy evaluation. And so Monte Carlo are curves that are in the top left quadrant here. They actually have very high error. TD, usual one-step TD is the red line, okay? And it also has some error. It's a little bit better. And the lines in between with n equal 4 and n equal 8, for example, are much better. And they're much better for a larger the range of the learning step size alpha, okay? And so what we're buying basically with these sort of temporal difference type methods is essentially a little bit faster learning by controlling the bias variance trade-off. And we can do various ways of aggregating over the space of n. So if you don't want to choose a particular number of time steps, you can use lambda returns or sort of weighted returns in order to combine all of them. And there's a very elegant mechanism for implementing this. So just to sort of paint a sort of a unified picture, if we're doing this kind of sequential decision-making process, we have a bunch of methods that we could use. Exhaustive search is not really interesting or feasible, but we can always use Monte Carlo. We don't have any assumptions for using Monte Carlo. If we have a Markovian assumption, we could do dynamic programming or temporal difference learning. And the width of the backup, how many actions we're considering and how many sort of possible transitions to the next state controls the space between these two methods. And then we can also go between temporal difference learning and Monte Carlo by thinking of the height or the depth of the backup. Now, if we want to do optimal equations, we can, instead of thinking of doing an expectation of our actions, we can maximize over actions, right? So always consider the best possible action. We obtain also Bellman equations, which are now nonlinear systems of Bellman equations, but they can also be solved approximately by iterative methods. This is sort of the relevant backup diagram where the transition out of a state, instead of having a stochastic policy choice here, we always pick the action that currently looks best. Okay, so we do a max. And we can do this with action value estimates as well. The iterative algorithm that we can obtain here is, again, starting with some guess for our value function and then just iterating the Bellman equation until we obtain convergence. So this is just an intuitive picture of what happens. Imagine that you have a navigation task and you have a goal state here that's marked by the black dot. One way to think about what value iteration does is that it propagates this value from the goal state that has the reward through the environment, right? So we can do this to the states that immediately precede the goal state in one iteration. Then the states that are two time steps away from the goal state will get some value in the following iteration and so on. And so you can see that this process is going to work, but it will take some time, especially if the reward is sparse. That means there's only a few states that have rewards in the environment. And so there's quite a bit of work in trying to make this process faster, more efficient, and so on. And it all relies on function approximation, right? So if states look similar in terms of their features, we're going to want them to sort of share estimates of the value and also perhaps share a policy. And so in the case of value of function approximation for control, we're going to think very often of using an estimate of the action value function Q hat. Inputs will be a description of the state and a description of the action. We're going to parameterize this, right? So maybe this is something like a deep neural net. And we're going to have a target for the update. And so this target can be many different things. We can use Monte Carlo-like targets, dynamic programming-like targets, or TD-like targets. Now, the main important thing is that now, if we're looking for an optimal policy, we also want to try different actions. And so in the case of Monte Carlo, for example, if we have a fixed policy pi, we might need to actually explore at the beginning and so allow the agent to take different actions at state S than what pi would recommend. Okay, and then we're going to use this data to estimate the value function and then improve the policy. On policy methods, always try to improve the policy that is currently being followed by the agent. They learn about the policy that's currently being executed. Oftentimes we're going to assume that this policy is randomized in order to give us a chance to try out all the actions. And the easiest way to do this is to use epsilon soft randomization, where we have a high probability of taking the best action or the greedy action, and otherwise we have a non-zero probability to take any other action. So if we have a finite number of actions at a state S, denoted here as A of S, we have an epsilon probability spread uniformly around all of these. And so as time goes by, since we're using the value function and the value function is becoming more accurate, our policy is going to move more towards a greedy policy. And so an approach like this is going to converge to the best epsilon soft policy. So the best policy that takes every action with at least epsilon probability. And you can think of this epsilon as a parameter or hyperparameter that controls the randomness in the agent. And there's lots of different ways to look at the effect of this epsilon. This is just some very simple toy examples. The main thing that I want to point out here is that if you don't do any exploration, so you use epsilon equal to 0, you're always greedy, you converge to a suboptimal solution because you may never try actions that are actually really good. And otherwise, the amount of exploration that the agent does basically controls the speed of learning. And there's a very rich literature that I'm not going to have any time to talk about on how to choose actions, but I suggest that you ask Michal about it since he's done a lot of work in that area. In terms of semi-gradient control, we can, again, write out various targets, right? Monte Carlo just uses the return. We can have on-policy control using SARSA, right? So SARSA basically says we use the reward plus the action value of the next action that the agent has actually taken. And that's the target that we're going to use in an update. We can also do an expectation over the next action. That's called expected SARSA. Or we can just do dynamic programming if we actually know a model of the environment. So at the states that the agent arrives at, it can do a backup using dynamic programming. All of these have different trade-offs in terms of how easy it is to implement them, how much knowledge we might need. Very often, we're going to use things like SARSA or expected SARSA just because those algorithms have good empirical properties. We can also use the n-step idea that I mentioned before and combine it here, and we get similar effects to the ones that we observed before, where intermediate values of n here are actually better in terms of providing a good bias variance trade-off. And then finally, there's Q-learning. So Q-learning is a very popular algorithm where what we do is we make a target based on the reward plus the value of the best action that the agent could possibly take at the current state, okay? And so this is based on value iteration for action values, which is the top equation here. Q-learning is going to use a sampled target using the reward plus the optimal action value at the next step. Now, what I want to remark is that this is an off-policy learning algorithm, which means that no matter what the agent is doing, it's always imagining that at the next state, it's going to do the best possible thing. And so that's very powerful because it allows the agent to decouple how it's choosing actions from these kinds of targets. And in the tabular case, we can show that this algorithm converges even if the behavior policy is randomized. The theoretical properties with functional approximation are pretty bad. We have examples, for example, where this algorithm diverges, but the empirical results are really strong, and they rely on some tricks in order to stabilize the learning. So I'll show you this now. Okay, and this is based on the original work on DQ networks that was used to train agents that play Atari games. Okay. And so in this case, we have an agent that's using Q-learning. So it's using this kind of target of reward plus gamma times max value of our actions at the next state. It's using the semi-gradient idea. So we pretend that this next state value is fixed. Okay, and we apply the gradient based on the parameters W only at the current state and action pair. And now the question is, how do we actually make this as supervised as possible in order to make sure that we have convergence? And so the first trick is to make the information that the agents receive more state-like, right? So more Markovian. In order to do this, we consider a history. So not just the immediate image that the agent has observed, but in this case, a stack of 4 previous frames. And this allows the agent, for example, to detect things like motion, right? Objects that are moving, how fast they're moving. And we have, in this particular case, because we're dealing with stacks of images, a bunch of convolutional layers, and then a fully connected output layer. And here we have a fixed size action space because this is sort of joystick controls. And so there's 18 possible actions. And so that's the size of the output layer. And so this is just another picture just to show different kinds of games that we can learn how to play. Now, in this particular case, each agent learns to play a specific game, okay? And one of the things that would still be really nice to have is a single agent that learns to play all of the games in one brain. That's a lot harder to do. So here we're just assuming we have one agent that plays Space Invaders, another one that might play Breakout, and so on. What else can we do in order to stabilize the learning? Well, one thing that we might want is to make this problem as supervised as possible. In order to do this, we may want to fix the way that the target is computed. And so this was the idea of target networks, to have two copies of a neural net, one which is training and one which is providing the targets. This one that's providing the target gets updated every so often, but in between these updates, it's fixed and it uses an older version of the parameters. And so the process is stabilizing, if you will, the output. The other thing that we may want is to decouple the training experiences from each other. So to have some independence in the inputs. And that's the idea of using replay buffers or experience replay, which was pioneered by Long Jilin actually in the 90s. And the idea here is to take tuples of experience, state, action, reward, next state, and then shuffle them, randomize their order, and do updates based on these. So in both of these ideas are trying to move the updates of Q-learning to look more like updates of a supervised learning algorithm, which sort of gives you more stability and a bit faster learning. Now, there's many other improvements that have been done later to DQN. One of the things that I want to mention is prioritized experience replay, where in the replay buffer, we are actually not going to sample all transitions uniformly, but we prioritize them in some way. One idea is to prioritize transitions where the estimated error is high, because intuitively this actually helps the agent to learn faster. And so the red and blue line in these pictures here are the ones that use prioritization. And you can see that the agent does indeed progress faster in these cases. Now, we can also add all of these improvements on top of each other, and we get this rainbow line here, this work by Matteo Hessel and colleagues. And so there's lots of ways basically to get these agents not only to be superhuman, but to learn how to do that quite quickly. So here the y-axis is the median human normalized score, and 200% means we're quite a bit better than people. So I'm going to pause there for a sec and see if there are any quick questions of sort of Q-learning, value-based methods, and so on. And then I'll talk a little bit about policy gradient methods.
Okay. Any questions from the room? There are a few questions on Slido, so maybe we can start with that. So the first question is, we know there has been cases of human bias creeping into supervised learning. What are some of the ways human biases can creep into the RL agent? And
yeah, so the most obvious one is if the reward function is coming from people, for example, people interacting with an agent, then obviously there is some bias that comes in, from whomever is interacting with the agent. Another way to have bias is by the action choices. So how do we define the action space? How do we define the agent's perception? And how do we limit the choices of actions that the agent is allowed to take? And then finally, we can, for example, use some existing data in order to pre-train an initial policy for an agent. And if that data is biased in some way, we have the same type of bias that we would have in supervised learning.
Thank you. I wanted to ask, so I see many of the tricks in deep Q learning
seem to come from like empirical investigations, like for example, having the target network, some sort of smoothing, some actor-critic thing. So I wanted to ask, is there any theoretical investigations that prove that they actually work better?
In some cases, yes. So, for example, one of the things that is not on this picture but is mentioned here is distributional losses. Distributional reinforcement learning, instead of using the Bellman equations that I showed you before, is using distributions over value functions. And there we can sort of show lots of things. And there's a nice textbook by Mark Belmar and Will Dabney and Mark Rowland that's just come out that describes all of that. There's a rich theory surrounding that. So there's a mix, again, in terms of better exploration methods also, there's actually quite a bit of work that's shown, at least theoretically, that some exploration methods can lead to faster learning. So there's really a mix. Some of these improvements come from empirical observations and some of them come from theory.
Hello. My question about if there are some patterns in usual intermediate goals. So in deep learning, I saw the approximation of the state space more often. But my question is if one could approximate the intermediate goals or the value function structure as well.
So, I mean, we always have approximations to the value because basically the value function is a function approximator. We can feed an input. That input can be any state and we can get a guess of what the return would be from that state. We've likely never seen that state before. We can also break up the problem in various ways. So for example, in the navigation task that I've shown you, if we have very sparse rewards, instead of using that reward function, we might put intermediate goals within the environment and then have the agent sort of go through a curriculum where it learns how to achieve those goals and then uses that policy that it's learned in order to help itself for the future. And there's been quite a bit of work in terms of figuring out how to decide what might be good goals for the agent to pursue, how to make a curriculum and so on. There's actually quite a bit of literature on intrinsic motivation, for example, and on curriculum learning for agents that helps with setting these goals. I'm not sure if that's exactly answering your question.
Okay. For the next question, we're going to go to Slido. So the question is it always straightforward to design the reward function? What are the solutions used in cases where designing the reward function is challenging?
It's not always straightforward now because we might have trade-offs, right? So there might be multiple criteria that we are trying to optimize for. There are broad classes of methods when we don't know exactly how to design the reward function. One is various forms of constrained reinforcement learning, for example, constrained MDPs, or multi-criteria reinforcement learning, where we might have in mind some most important criterion and then have some secondary things that we would like to improve as well. So, for example, in a control task, we might want the agent to do their control very precisely, and we might want to minimize energy while doing so. And so we might have one reward function, let's say, maintain the pole vertical, and then we might impose a constraint that says, and also don't torque too much, right? Or don't put in actions that would consume a lot of energy. And now we have a constraint optimization problem that we have to solve. And we can solve these in various ways. I'm going to show you one example of that in a little bit. Another way to do it is to sort of have people provide feedback, right? So the way that reinforcement learning, for example, has been used most recently in chatbots is that we have a person interacting with an agent. The person is shown two different trajectories, and the person says, oh, I prefer this conversation to that conversation, right? So there's now preference data on trajectories, and we can try and extract a reward function out of that. That leads to a very iterative process where the reward function has to be refined, and then the policy gets refined, these trajectories get better over time, and we sort of improve in that way. And so this is a case where we're trying to learn what the right reward function is from this sort of preference signal, if you will.
Thank you. Let's do 2 more questions, and then, or maybe just 1 question, so that we have some time for the policy methods. So the next question is, RL is well known for being sample inefficient. Is there any reliable way to solve this problem?
So I think this is a myth, okay? But it's a myth that's really taken root. I mean, you know, deep learning is also sample inefficient. There's lots of things that are sample inefficient. There's been tons of work in reinforcement learning in terms of improving sample efficiency. It comes in different flavors. One flavor is just to do better exploration, which means we're trying fewer sort of meaningless actions. And again, there's like, you know, thousands of papers probably on this topic. And there are quite good, efficient ways of doing exploration, for example, by using optimism in the face of uncertainty, or by using Bayesian ideas. There's also a lot of work in terms of improving the credit assignment, right? So instead of, when we have sparse rewards, for example, instead of propagating values slowly back, to kind of propagate them more effectively over state space. And for example, hindsight experience replay is a really interesting line of work that I quite like, that kind of does prioritize replay buffers, but in a way that really improves the credit propagation. And so there's quite a bit of work on that.
Thank you, Dana. Yeah, since we only have 15 minutes and a bit, let's jump to policy methods, and maybe we'll sneak some more questions at the end.
Sounds good. Yeah, so we've talked about action value methods that learn the value of each action, and usually will strive to pick the max. What I want to tell you about now is policy gradient, where we're trying to learn directly the parameters of a stochastic policy. And we're going to make updates to this policy by doing gradient descent on our performance metric, which is the expected return. And so some methods focus on the policy only. Other methods still leverage the value function. Actor critic type methods, for example, leverage the value function, but still learn explicitly a separate policy rather than relying only on a value function. Now, why do we approximate policies rather than values? In some cases, the policy is just simpler. So one example I want to give you is we did some work at some point with Hydro-Quebec, which is a big energy company here in Canada. And they wanted to optimize the way that they control a power plant by opening and closing where they turbine the water. And there, the policies are actually simple because, you can have the opening, completely open. You can sort of torque it down. And so the policy has a threshold, is a linear part, and then another threshold, okay? Now, what you want to optimize is something like revenue, okay? And that is very complicated because there's many factors, right? There's market forces, etc. So the value function is very complicated, but the space of policies is very simple. And so thinking of the policy as an object in itself can be much easier than thinking of approximating a full value function. Also, in some problems, we want an optimal policy that is stochastic. We want that probability distribution approximating directly. For example, if we have partially observable Markov decision processes, or POMDPs, that may be the case. We might want to enable smooth changes between policies, or have biologically relevant policies, like, for example, when we model spiking neurons. And so in all these cases, we might want pi itself to be parameterized. Okay, so the basic idea here is we're going to have a set of parameters theta that parameterizes the policy, the way of taking actions. And we're going to use an objective that depends on this data. This objective is still the value function or maybe the average reward in some cases that the agent receives. And we're going to approximate stochastic gradient descent. And so we're going to move the parameters of the policy from the current value theta t to a value theta t plus 1 by doing ascent on an approximation of this objective, okay? And alpha here is, again, a learning rate. And there's actually sort of a trick, okay, which is the sort of grad log pi trick, right? Basically, the gradient of the policy divided by the policy itself is the gradient of the log of the policy. And we can sort of use this in order to prove this sort of fundamental result called the policy gradient theorem. The policy gradient theorem basically says we can write out a gradient of our objective, if the objective is something like value, in terms of the gradient of the policy. Okay, and so we can use this in order to now make algorithms that move the parameters of the policy directly. Okay, now one of these algorithms is called reinforce. In the case of reinforce, what we do is we use the policy gradient theorem. Policy gradient theorem has an expectation over trajectories of the current policy. So we're going to usually use sampling, right? Just run the policy through in order to sample from this distribution. And then we need to have some estimate of Q pi. And an estimate of Q pi here could be just the returns, Monte Carlo. And so reinforce moves the policy parameters based on returns that we are actually getting. Okay, and so the algorithm is the last line here. Top just shows you the derivation of how we obtain this. And this last line relies on the returns and modifies the parameters of the policy in a gradient fashion. Now, in contrast with, let's say, doing TD, which is not a gradient-based algorithm, this really is a gradient-based algorithm, right? And so it has all the properties that you would expect, including converges to locally optimal solutions if the step sizes are chosen appropriately. Now, another thing that we can do here is to use a baseline. Okay, so baseline is any function that's a function of the state but not of the policy. And we can use it to essentially, again, control bias variance by shifting values. Okay, and so, for example, we might have a baseline that is the current value function that's estimated as an average, for example, of the rewards obtained over the agent's lifetime. Okay. And that can help out as well. One thing that I want to point out is that there's different versions of these algorithms. Some of them, even though they are very much correct, they're actually pretty sample inefficient. So you see here an inserted gamma to the t in the very last equation. Normally, we should have that. There's been interesting work by Phil Thomas showing this, that's sort of the true gradient algorithm. But if we introduce that, we might have very inefficient updates because here gamma to the t decreases very quickly over time, right? So there are versions of these algorithms that are biased gradient updates, but that allow us to do things with a little bit more data efficiency. Now, if we want to take full advantage of the data, maybe we want not just to parameterize a policy, but also to parameterize a value function and use this value function in order to provide a signal to the policy. And so this is what we call an actor-critic architecture. Think here of the value function and the policy as both being function approximators, where the policy is using a temporal difference error in order to get updated. It produces actions, and then we observe state action rewards next state, and we update the value function by whatever means that we've discussed already, including, for example, temporal difference learning. And so we can do an actor-critic method, similar way as reinforce, but where we're using current estimates of a value function, parameterized estimates, in order to update the policy. And so the easiest way to think about this is that we're going to have two separate function approximators, one for pi, with theta as the parameters, the other one for v with w as the parameters. And we can, this is the basis for algorithms like A2C and A3C. The idea in, so this is called advantage actor critic. Advantage actor critic basically means we're going to use a return and then compare it to the current value function. And we're going to use this discrepancy, which is called the advantage, okay, in order to drive the learning. We're also going to use the tricks from supervised learning, for example, mini batches, perhaps using Adam in order to set up the learning rate and so on. The difference between A2C and A3C is that in A3C, we actually can use multiple copies of the policy in order to act in the environment. And so we can have multiple actors that are all sort of pooling their data and then feeding it to one critic. And then this critic is updating the policy, and the policy gets copied back to all of the actors. So this is very advantageous if, for example, we're doing learning and simulation, and we have many processors, and we can run parallel trajectories on all these processors. So if we have games, this is obviously the case. And it allows us to gather data quickly and also to mitigate a little bit the exploration problem, because now we can, for example, start the different simulations in different states, right? And we're going to get some randomization just by virtue of having these multiple trajectories together. And these are some results. Again, in some of the Atari games, we can get these this A3C approach to work better than DQN, right? You've seen before results in which DQN was working better, or variants of DQN working better. And so, which one works better? That really depends on the domain, and it also depends perhaps on how how good we are with all these tricks for implementation. Now, sometimes we also want to make sure that when we're doing policy improvement steps, we have enough support, right? So if I had an old policy that gathered the data, and we know I want to change this policy, I want to make sure that this change is real, right? It's not just something that, where it's wishful thinking because I didn't have enough data to estimate things correctly. And so the idea here is that we're going to collect data with some policy pi old, and then we want to sort of move this to a new policy pi. And so we want to make sure that when we're using our data, we are imagining the values correctly, right? So in order to do this, we have an important sampling correction here that takes the advantage as estimated by our current data and important samples it by, multiplies it by the ratio of the new policy and the old policy, okay? And so we're going to mainly rely on the data that is like the new policy in order to make our estimates, okay? That's great. The other thing that we might want to do is to sort of slow down the learning so that our data distribution doesn't change too quickly. So that's the fundamental idea of trust region policy optimization, or TRPO, where we have a policy that we're trying to optimize, but we're going to sort of take into account how the data was gathered, and we're going to require that the new policy pi is not too far from the old policy. And here we have a tail penalty in order to sort of put that in. And the loss itself is going to be this important sampled advantage function, and we can construct it from data, okay? And there is a different version of this approach called PPO, proximal policy gradient, where instead of using a constraint, we now do a Lagrange-based method. And the other innovation here is that we have this sort of Lagrange penalty factor beta that we can twiddle with, right? We can make it higher or lower. Okay, so for example, if the policy is too close to the old one, we're moving very slowly, we might decrease the beta, so we allow the policy to move more freely, and vice versa. Okay, and so this has been used in all kinds of sort of gym control tasks, as well as Atari games with pixel input, and we can sort of also use this in order to construct deterministic policies, not just stochastic policies. The idea here is called deep deterministic policy gradient, and it relies on replay buffers and target networks, and also a averaged version of Q. I really don't have the time to get into the details here, but it's an algorithm that's quite reliable and state-of-the-art in many of these control tasks. So policy gradient is a very general approach. You can apply it whenever you can compute the effect of parameter changes on the action's probabilities. There's a lot of different shapes of policies that have been used. And whether we do value-based or policy-based really is an application-dependent choice. And in some sense, it depends on how simple the policy space is to parameterize and to search through. But value functions can also just reduce variance, even if we're focusing on policies. So just to wrap up, I just wanted to mention a few open questions. There's actually been quite a bit of work, both in theory of reinforcement learning and in practice, but there's a huge gap between where the theoretical results are and where the practice is. Practice is all deep nets. Theoretically, we know very little of these algorithms. There's a lot of ongoing work on improving the stability and data efficiency of DeepRL further. One approach that I haven't gotten a chance to talk about is model-based reinforcement learning, where we fit a model of the environment and then we use it in approximate dynamic programming and other kinds of methods. And then, of course, exploration is still very much a problem, that where people are still working on improving both the theory as well as the practice. So I'll stop there. Thank you for your attention, and happy to take a few more questions if we have time as well.
Let's start with a question from Slido. So the RL field suffers from reproducibility issues. Have you seen any real efforts from the community to solve this?
I'm sorry, I can't hear you very well.
Sorry, my mic was off, sorry. Let's thank the speaker again because Aina did not hear us. Thank you. Sorry for the mic. So I said let's start with a question from Slido. So the first question is, the RL field suffers from reproducibility issues. Have you seen any real effort to tackle these problems?
There's a lot of effort on this. Of course, there's simulators that are publicly available. A lot of people have started putting code out, right? We had a paper with my colleague Joel Pinot and a couple of our graduate students looking at reproducibility issues, and that led to a whole push in the community to have open source code put together with the papers as well as these reproducibility checklists. It's always difficult. It's especially difficult when we're using not the simulators, but data, and the data is somehow not public, which, also is sort of the reality in some applications that depend on customers or real people, for example. There's, privacy issues there. I think it's something that we have to sort of goes hand in hand with this issue of improving stability. So if the algorithms were more stable, results were more reproducible. And so in my view, sort of anything that improves the stability of RL is really also a step towards improving the reproducibility. And I think we've made progress in the last few years, but it's a big field. And so it's unwieldy as a result as well.
Any questions from the room? Okay. Okay. Then I'll jump to a question from Slido. Can the human be included in the training loop in some other way than as a reward dispenser?
Yes. So, for example, in robotics, sometimes the RL starts with some behavior cloning that's obtained from, let's say, a person driving the robot around, right? Or, some other fixed policy. So we can assume that there is some data that's generated, right? Or maybe we're observing a human doing a task. We want to copy that in order to obtain an initial good policy. So in that case, the way that we incorporate the human is by looking at trajectories that they perform and then trying to imitate those trajectories, as well as then doing some reinforcement learning together with that data or on top of that. And of course, there's the whole process of designing features for states and for actions, where sometimes, so for example, if you're working with a company, you're trying to apply reinforcement learning in their context. The knowledge of the person comes in indirectly, right? By talking to them and trying to understand, what kinds of things are allowed, right, within their policies, what kinds of, how do they describe the state of their system, and so
Thank you. Let's do one last question from Slido because timing is running out. So do we keep every experience in the replay buffer, or are there experiences that are better to remove?
So in general, my own attitude is you keep all the data that you have. But sometimes, in practical applications, again, you might have situations where either you have an overwhelming amount of one kind of data, right? So, there's some normal way of operating that's like 99% of everything. And you also want to focus on the exceptions. And so either you can rebalance things, just like you do in supervised learning, for example, when you have class imbalances, or you might do important sampling, right? So if you have some trajectories that are really more like the policy that you want to see, you might emphasize them by important sampling corrections. And then, of course, sometimes, like if you believe that some data is bad, you might filter it out of the replay buffer, right? So for example, if you think that some actions should never be taken, somehow they ended up in the replay buffer, and you're seeing that you can't, that they maybe dominate the value function or something, you might replace them. But, my attitude is that the learning algorithm should be good enough to get rid of this information without an extra filter.
Thank you so much, Dana. Let's thank the speaker again.
Thank you very much. And I hope you'll enjoy the rest of the school.
Okay. Now, can I have the other organizers maybe on stage just before?
Yes.
Yeah, so basically because all organizers are present, we wanted to make a statement about the continuing Russian war of aggression against Ukraine. So we just wanted to say that on a personal level, but also as organizers of EML, we are against the war, and we want to express our solidarity with the Ukrainian people going through these horrific times. Many Russian citizens do not agree with the war and have moved out of Russia as a result. So EML does not discriminate just based on citizenship in cases where the participants do not currently reside in Russia or are not affiliated with a Russian organization. To show our support further, we will continue to offer EML travel grants for Ukrainian students. We're also trying to do this to attend upcoming ML conferences. More details about this will be announced on our website, so look out for that. And please reach out to us if you'd like to be considered or to help us spread the word, if you have friends or colleagues that might be interested in these travel grants. We want EML to be a safe place, a safe and collaborative space where all attendees can feel comfortable, and therefore we would like to remind everyone about the code of conduct. Please be mindful when discussing such sensitive issues and show respect and solidarity. If you have any concerns, please reach out to us. Thank you. Yeah, now we go for lunch in the same place as yesterday. Hopefully there'll be volunteers to guide you if you get lost. Thank you.
Hej, raz, dva, jeden, dva. Hej, raz, dva.
eventually.
Okay. Oh, now it's working. Okay, everyone. We're going to start the afternoon session. So please take a seat. Okay. So it's my great pleasure to return the favor to Mikhail, to introduce him as he introduced me. So I know Mikhail for a while now, since he joined DeepMind. I still remember, I think the first time I met him was during graph neural networks meeting. And I think the kind of graph networks that Mikhail was doing was very different from what I understood by a graph neural network. So that was nice to see sort of the, yeah, how the same term can mean so many different things. So I guess everyone already knows Mikhail. He's an organizer of the school this year. He's from Košice, a colleague at DeepMind, and also part of INRIA. And he's going to continue the lectures on DeepRL. Thanks, Mikhail. Over to you.
Thank you, Razvan. Welcome, everybody. Welcome again to the RL Day, because today we'll be spending the day talking about reinforcement learning after the federated learning. So there was Dojna part that told you the concepts, value function, gradient bend methods, and so on. And now we will build on that to talk about different things about reinforcement learning. I'll try to make it included with other things that we talked today, like self-supervised learning, vision. And I try to make it a connection, because there are other things that we can do in reinforcement learning. One of the things is to learn the value. Can learn it's a world that will be able to answer what-if questions. So what happens if, in this case, I do this action? Well, this clicker falls. So I would like to know how to build such a world model, because this will equip our agents with some kind of map, and we can plan ahead. We can plan in our head what kind of things we have in our model. So also I'm very elated that, that after long preparations, I can welcome you to my city, and I'll tell you a little bit about it, maybe something that you didn't know. So this is the coat of arms. I believe 1,000 from 1396. And this is the first coat of arms ever given to a city. Because in the past, coat of arms given to like the royal families, but the emperor of the time said like the people in the city are so great that they deserve a coat of arms. This is how it evolved. And since then, every city started to have a coat of arms. So this is a part of the history that I'll tell you. Another part of history, it's more a familiar one. So in this Ala Maxima is my grandfather, did his studies, and actually half of my family. And actually, even in these rows, I was sitting as a little boy 30 years ago when we were doing the regional rounds for Mathematical Olympiad. So I'm very happy that now I'm here on the stage and telling you about reinforcement learning. All right, so let's start where we end up it, right? So in reinforcement learning, we try to build some kind of more general way of doing action, right? So while supervised learning is classifications and those things, reinforcement learning is taking action. And more generally, we often, when we really think big, we think about AGI, right? Like we would like to have an algorithm that will be general and will be able to answer any problem and do any task. But what do we need for AGI? Well, for AGI, if we want agent to generalize significantly beyond one specific task, we will need to train them with a lot of data. Well, we don't have a lot of data, right? It's the stuff that works on in machine learning or deep learning. It's a huge amount of data, huge ball. This is the recipe, right? But we have very limited supervision, and we know that we need those things. And so one way that we master those things, we'll try to build on something called self-supervised learning that we had from Jana before. But in context of reinforcement learning, you can call it unsupervised reinforcement learning. What to do, how we can take good actions when nobody tells us what to do. Nobody gives us a reward. Because you can imagine that
Well, if I wake up, get morning, get a coffee, get a lunch, decide to come here to election, I don't get the reward as every single step, right? In what DAY2 presented, well, the agent does an action and receive a reward for that action and updates the world model and updates the policy. Well, as we behave, nobody gives you action that you start to write the letter. We somehow manage to get by without that, right? So how we can somehow take inspiration of that and make it work also for AI systems, right? So we'll master as a self-supervised learning and try to use it for reinforcement learning to grow. So what will be agenda? We'll quickly recap in a few seconds the notions of RL, why we do it now. Then we'll make kind of I'll show you our paradigms, how we approach self-supervised learning here. And then we come back to RL, and we find the way how we can use self-supervised learning for reinforcement learning to create world models that will be used for exploration. So please interrupt me with any questions, shout, raise hands, put them on Slido. I don't need to take all of my slides. I have slides, but I'm not married to them. We can finish in a half of the time, and I'm rather happy if I answer a lot of questions. So please, even now, if there's any question, please stop me out. Yes, there's a question.
You told that we do not have a reward for every single action we do, like having coffee or breakfast, but in fact we have a reward, like our hormones.
Exactly. Yes, and so this will be an inspiration, right? We have a lot of rewards, hormones, curiosity, a lot of drives, psychological drives that somehow embedded in us, and this is exactly what we'll try to use to motivate, let's say, our AI system to take actions. Specifically, most of the time I'll focus on one of the drives that it has is curiosity. That's one of the drives. Any other questions?
Yeah. Any questions?
Yes,
there is a question on Slido.
Oh, really? Already?
And I'm not sure if you have an answer, but so Michal, what would be a realistic timeline to see the first true AGI?
I'm not allowed to answer such a question.
I assume.
At least without 3 beers, I will abstain. The question, more serious answer is that we don't know the good definition of AGI, right? Depending how we define it, we already have it or not. It's not a mathematical concept that you need to have such a capabilities to have AGI, right? Like in the past, we have this. We will have AGI if we pass the Turing test. Well, now we pass the Turing test, and we saw what kind of methods pass the Turing test. I said, well, this is not really AGI. This was some kind of illusion games. Tell me about your childhood, and people felt that there's AGI behind it, right? Sometimes we define the benchmark, then we will pass them and we look what is inside them and say, well, no, this is not AGI, and we improve it. So I will actually present results that relate to that. So in DeepMind, we have a team that every year comes up with new sets of environments, and when we pass it, we improve it, right? So we kind of like strategically get to the better and better and harder problems. But the answer where we'll have AGI, well, depends on what it is. And so it maybe it already happened and will happen in the future. All right, so what was reinforcement learning in the way that DAY2 presented? It's like learning by trial and error. That's something that we know. There is not a very difficult concept. It's coming from neuroscience, coming original from a Pavlov dogs. A lot of language that we use comes from neuroscience for this reason. And so that's why we have these notions, drive, curiosity that sounds not so mathematical because originally comes from then, from 50s and 60s. But it's learning to act. So we're learning actions in unknown. This environment could be stochastic and maybe maximizing some kind of reward signal, and most of the time you will not have it in this talk, right? So a good example, you want to learn how to drive a bike and you don't know the rules of physics. why it's not ready now, right? Because it's really difficult, you know. RL is almost encompasses all possible problems that we have, you know. It's, you know, supervised learning is just part of RL. Representation learning is part of RL, right? So we need to reason about time, long-term consequences of actions, predicting the future, how to gather experience, you know, dealing with uncertainty. You know, if I show my robot, look here, I don't even know what happens here, right? I influence my own actions. This is most of the difficult time. That's something that motivates and challenges me, this kind of close feedback groups that rather in other fields, you have those data sets and you can evaluate based on them. Here you choose your own data set. So if you tell robot turn this way, you don't even see what is there. You're creating your data. And you know, you can maybe forget that there you get better reward, right? So it's not independent. It depends on your actions, and there is some kind of feedback loop independence, and that's very interesting. And that's why it's hard. All right. In particular, in this talk, we'll focus mostly on long-term consequences of action, dealing with uncertainty, but there are many, many, many facets of RL, and they'll take some time maybe to resolve them all. Right? So why we're talking about RL now? You know, so you know, there have been recently, you know, let's say, you know, 6 years ago, some Doina mentioned it, advances in games of chess and shogi by kind of the safe play. There have been also a few years after we have been able to solve StarCraft, which also has a specific point that you don't see everything what is there. We're also more difficulty than chess and Go, right? You don't see all the board, you only see some fraction of board, so you actually have to reason about what is around that you don't see. You know, then there is, you know, with the self-play, and you know, there's more things to do when you have multiple actions, you have collusions, and so there have been recent advances of that. But in reinforcement learning, we actually don't care about solving this game, even though, like, you saw a lot of announcements, you know, my company is guilty of that, right? Like showing advanced in the RL is game. RL is not about games. The reason why we focus on the games, because it's easy to simulate, right? Like, you know, robots break, take a long time, but the games are easier to simulate. But what we would like to do in ideal situation, have one single algorithm to solve them all, but not just games, but also the, you know, difficult visual environments, difficult robotic things, and so on, right? You know, also RL, you know, like I think I didn't put a slide on that. In 2023, it's more about, you know, learning to, you know, fine-tune large language models, right? So the last step of the fine-tuning of large language models as a bar or ChatGPT is this reinforcement learning fine-tuning, where we can also influence some kind of behavior. So, for example, if we don't want our large language model to exhibit certain type of behavior, so for example, not giving medical advices, not being racist, you know, this is something that we can influence using reinforcement learning algorithms, right? So reinforcement learning is really in heart of what's going on right now. And you know, you know, fine-tuning large language model is how I spend most of my days, because that's really on point of the game. And so it's good to actually learn the concepts, and it's actually very timely time to learn about that, right? So let's review our concepts as Doina presented in the way that we use it. So it's a simple, very simple scenario that kind of models how the life works. We have the agent. That's what we're trying to learn. We're learning the agents. This is what RL is about, taking the action. So agent can take an action. In the environment, it can change the environment by taking the action. It influences the environment, and from that, gets observations and sometimes rewards, and sometimes not even observations, right? And so what we're trying to do, learn the agents so that decisions are good in terms of these rewards, right? From some kind of experience. So little more formally, you know, if we model this, we can sample action with some kind of distribution of the policy. So oftentimes, and almost always, in 2023, you know, policy is a network parameterized by parameters, given some kind of observation, because sometimes we don't know the full state. You know, for example, in the StarCraft, we only see what camera shows us. Based on that, we created action. We can sample the action. The sample is probability. You know, for example, in large language models, you know, we're sampling every time step a new token, a new word, based on the previous ones. So this is example of the action. Sample next part of the sentence in large language models. This is our action. here in language model is quite simple because action becomes our observation. This is a very simple environment. It's deterministic. And we're not changing it unless we're updating it. But then, you use this action environment, we get a reward that we can model to get a new, depending on the observation action and the next action. We can make it simpler, only depending on observation or on the action itself or on both. And then new observation comes from some kind of dynamics. Usually these dynamics are known. In large language model, these dynamics known. So we have some kind of probability that if we took the action in that kind of situation, what will be the new state of the action, right? And this is RL, and the only thing that becomes different in deep DRL that we use deep neural networks as policies, right? We can, and in this talk we also use them for creating the rewards. But in the beginning, you remember this DQN presentation part of DAY2, we used deep learning as policies. Well, so one good example, this is Eastern European summer school, so everybody knows Tetris. I will not even ask who does not know it. This is where we grew up on it, and so this is a very good example of reinforcement learning. The state is current on the board, and the orientation, and which block to add. Action, you can change the orientation or put it down. Reward is increment of the score, and transition is a new mode, and randomness of the new block, right? So this is super difficult action space because there's a lot of it, and this was one of the last thing that was solved without deep networks. So this was possible to solve, but it was around 2015 when we were able to have like a first decent reinforcement learning algorithm that played Tetris. And one of the difficulties, it's a large state space. So representing all possible states it became or was difficult, especially if we make the board large. And this is part of the things where deep networks and deep RL change the field, because somehow the main thing that deep learning addresses is this representation issue of the action space. All right, so let's talk about the rewards and answering those questions. So most of the rewards, if you look at the book, it's like somebody gives me a reward, and most common question in the modeling rewards in real life is like, where does the reward come from? Because where we take a coffee, you don't get the reward, but maybe you have some drives. So typically in the book, we consider this reward like string hard-coded, and that's why oftentimes we focus on games, because it's easy to define what is reward in chess. You won or you lost, it is easy to define what's the reward in Tetris, you're scoring crores. But when you try to create the reward for, well, I want to drive car really well, that's very hard to define what's the reward is. Well, you need to go between the cars, you should not bump to the other cars, not speed too much, not burn the brakes. There's a lot of things, and it's hard to define for a lot of things, and that's why there's other ways to do it. So that's why, what we focus now is this intrinsic reward. So nobody tells us what to reward, but as humans have it, all of these have their own research subfield of RL, how actually we can substantiate or replace this extrinsic reward with intrinsic reward. So one of the social, how much thing we can influence. Imitation, how we take an expert, I want to learn tennis, I hire Federer, I try to imitate him, you can have explanation of the thing, we can have language, desire to control, empowerment, how much, which action do we can that it influences environment the most, curiosity, most of the day we'll spend on curiosity, it's meta-learning, so, Razvan can tell you all about that, the learning progress, how much you improve, for example, on some expert trajectory or explanation. There's lots of it. The list is very long. It's kind of, it's also inhibits, parts of the intelligence. So now, I'll talk about the way how do we represent the deep RL, how do we represent the world in the RL, and especially for the work that we've done in our team when I joined in for the last 5 years. But if there's any question about these basics, now it's a good time. Yes.
So do you see actually emerging in some models these intrinsic goals? Like, for example, I'm not a professional chess player, but I know that some masters teach that what's the score of this and that chess play, and I mean, figure.
Yeah.
I imagine that if you run a very long training time with just winning or losing, then you somehow emergently see these kind of intermediate values or goals.
Yeah, so you know, it's a very good question, right? And so you know, the games like chess are very difficult. You know, actually, we like to play them because we are not good at them, right? That's why we have competitions of those games, because actually we're not as good as in reasoning as we think. You know, we cannot plan 40 steps ahead, and so there, you know, we kind of, over the history of chess, we kind of find some proxy rewards. Oh, this figure is this one, so if I take this figure, right? So we think that this is where we can imitate, we can simplify, right? Like Peter said at the beginning, you can simplify by the language, you can simplify something, right? But, you know, and then we try to imitate some kind of experts. This can work to some extent, but it does not necessarily need to be good. So this is kind of the story of AlphaGo, AlphaZero, Mu0, PO0, you know, and follow-ups, right? Like AlphaGo, we learn from these experts, try to imitate them, you know, and maybe try to improve it. In AlphaZero, you know, we start from a 0, and we said, well, the only thing we care is the final reward, no matter how you get them, and we just use the self-place. And then we discovered, then, you know, that we can do even better than humans, right? So using humans to, you know, to imitate them, you know, you actually kind of reach the limitation of humans. Sometimes you actually want to become better than humans, you know, and you know, as we call it, superhuman. So have a better performance as a human. You know, there's this DeepMind movie of Move 37, right? When the player made a move, and you know, like everybody said, well, it's such a stupid move. How could you do that? Nobody in the history would do such a move, because it was not considered as cool move according to all these principles. Right? And there is also recent paper how they discover new techniques in chess. So yes, you know, most of the times when you want to short, you know, fast, speed up learning, you know, it's good to do these things, and you can then see this in value when you encode them. But I guess the challenge of deep learning is just to encode as little as possible and make it learnable, usually end to end. So for example, a difficulty in AlphaFold, right? Like you want to encode that atoms are aligned in a certain structure, but you don't want to encode them too much, because then it's difficult to differentiate. So it's like striking the balance, how little you encode, so you can learn much more.
Hi, I have a question. You mentioned that in StarCraft here, you have partial observability of the environment, right? So how do you actually learn in this kind of environments?
So this is the purpose of my talk. So just wait 10 minutes and we'll get to that. And if I didn't answer the question, please ask me again.
Any other questions? Okay, just a comment. I disagree on the remark on the deep learning that's about, the deep learning is about encoding as little inductive bias as possible. I don't think that's what we're doing, but it's a different discussion. Go on.
All right, so let's get into it. You know, how we can represent deep learning in the world, and I'll now present you to our approach to self-supervised learning. So like building on what Diana said yesterday, you know, and this work is covered by many colleagues that I will mention later. Maybe you heard about BYL and the follow-ups of that. Jana presented some of them. But first of all, why we actually need this self-supervised learning, right? So in computer vision, the goal is to process an image to solve a downstream task, such as classification, segmentation, or object detection, right? And in this deep learning framework, we first process image with neural network, you know, to extract some visual representation. So we learn this kind of encoder network. And this representation is then fed to different downstream tasks to solve the task at hand, you know, usually with a specific, you know, human-labeled things. But how do we train this neural network? How do we train this encoder, and how do we train this downstream network? What kind of data do we use for this? All right, so in practice, there exists two kinds of data. On one side, we have a label data, such as images comes with the ground truth information, labels, bounding boxes, Jana talked a lot about that, but this data is very expensive, task-specific, and it's a limited number, right? So you not always possible to train entire network pipeline is full capacity. So on the other side, we have a lot of unlabeled data in the wild, and the goal of self-supervised learning is thus the leverage to abandon labeled data to pre-train neural networks. And in reinforcement learning, we'll also show how actually, what is this unlabeled data in the context of reinforcement learning. In case of, this will be more of a past and a future within a trajectory, to spoil a little bit. So in our approach, we first train the generic encoder in the computer vision, by using this unlabeled data, so no labeled necessary, so only intelligence will come to some kind of this augmentation. And then we train downstream network with labeled data in a supervised fashion. Well, in this presentation, I'll spend next 5 minutes just to discuss BYOL. So this is our contribution, which is a self-supervised method for pre-training image representation. And this was now already 3 years ago, it caused a revolution in the field, how we do things. All right. So how does the BYOL work? And this was a work with lots of collaborators, lots of helpers in DeepMind, lots of engineers, and a lot of compute as well. So how does it work? So one main ingredient of most self-supervising methods is to take advantage of this image transformation. So when I say it's self-supervised, and doesn't mean there is no human intelligence coming to it. Human intelligence comes in selecting these augmentations. So one step closer to AGI will be, just to not be needing to solve them. But, for now, this is what we need. So for instance, we take image of the dog and we transform it with the random crops or color distortion or core information such as breed shape will be preserved. So more generally, we expect the high-level semantic information to be preserved with these simple transformations. So BYOL and many, many other self-supervised methods build on this idea. So we're given a transformer view, we look directly to predict the other transformation without additional information. Rather, image of the dog is still a dog. So as both views contains the same semantic information, we should be able to predict their representation independently of transformation. So how do we do it? So we first process, we'll take the image from the data set, we process with the view, we pass it through an encoder, we go it through a predictor, to output a prediction. However, remember, there's no labels. What do we predict? We're unlabeled data, so we need to generate our own targets. So therefore, we introduce a second network, which will be the same architecture. Here you can think of ResNet that Rasmus presented. And before I continue, I need to point two things, right? So first, we only train network making the predictions, but we do not propagate this prediction through the target. This is super important because we don't know to encourage this view to be easily predictable because then some bad things could happen. Rather, we want to force the view to be predictive of each other. The second thing in BYOL, both of the prediction and target networks are continuous vectors, right? So we don't have some kind of labels. There are methods where there's kind of pseudo labels, pseudo targets, and so on. It's all vectors of numbers. So we target numbers are continuous vectors. So we're working on embedded level. And so this enables us to lose a simple L2 loss. So at the beginning of the training, we randomly initialize the network, right? So the weights are random. Doesn't mean the predictions are random, because we still, as Randall said, there's some inductive biases. So it's different between the random labels and the network coming and the prediction of the random networks. So we then start regressing the prediction from one towards the other, towards this fixed target representation of the view. It will be not very good, right, because we predict labels from the random initialization. But if we do it some evaluation that I'll talk about it later, it will get, let's say, 1.7% very bad score, but it will be better than 0. So we then try to regress it, and we'll build the better predictor, right? So very interesting phenomenon is going to happen. So if we keep the target network fixed, so this is fixed, and we try to backpropagate these targets to update the weights of this part of the network, this process already allows Encode to learn better visual representation than its random initialization, right? So it gets slightly stronger. Then the natural idea, which is coming from reinforcement learning, is if you paid attention to the DOINAS talk, in a particular DQN part, you can see a lot of connection and inspiration for this work from reinforcement learning, from resources to be finally used for reinforcement learning. So that's all over. So we replace this random RAN network, generating the targets by the new encoder, right? So now, it's not good, but it's better than nothing, but we can predict better targets. Then we can repeat the regression training procedure by predicting these new targets. And if we keep bootstrapping the encoder representation into the target, we can improving encoder representation. Well, and so on, and so on, and so forth, until the conversion and until we cannot improve anymore. Well, then at the end, what we outputting is just encoder, because that's what we wanted at the beginning. And this is the output, right? Now we will have some network that at the end taken any image of a dog, and predict some kind of representation of it, some numbers. So now that we have intuition, let's have a little bit of detail how it works in architecture. So first, we generate two views of the same image. This is super important. Like most of the work is done there. Most of the work was done with a whole of vision communities. Here, particularly, we were 12 different possible augmentation. Each of them we sample with some probability. So we sample one augmentation with some probability, with crop with 70%, and I think with 35%. We hyper-optimize these numbers, and we have a different probability for this one and different probabilities for this one. A lot of work went down that. So I need to stress that this is, there is a heavy machinery going on, and this is the most of the time that we also have the selection, and that's the human comes from. So then generate these two views of the same image. So one from the online and one from this target network. Then each view is processed by the ResNet. So like you get the output of 2048 numbers to get the image representation. Then we project each image with a multi-layer perceptron, similar to what's done in contrastive learning, to project it to a smaller space, because it's easier to, for example, let's say we project it to 256 numbers, because then it's easier to the prediction, but we don't output the final thing as output, because 256 numbers is not enough to represent the image. It's not expressive enough. For a lot of downstream tasks, we need these, let's say, 4,096 numbers or 2,048 numbers. So we project it because then it's easier to predict later. And then on the online range, we also apply a second NLP to extract the prediction, and then we try to predict it. Right, so here we just construct these targets, and what we do, this is a cosine similarity or normalized L2 distance, and then we just do gradient descent. So that's also it is. So another thing that I want to mention, so instead of copying the network, we do something typical as is done in like reinforcement learning, like exponential moving average. So we always take instead of replacing them and keeping the network as it is, we take current weights. We take the current weights, we multiply it by some small number, and then we add this thing, right? So we keep kind of moving average of the path. This is for efficiency reason, because ideally we would like to keep all the networks and do the average of the labels. This comes from some game theoretical implementation, but keeping all the networks in the stack is very, very costly. So this is kind of simple trick, Instead of averaging the labels, we averaging the weights. It's not exactly that, but it works. And instead of updating the network from some paths, we do this exponential moving average. All right, to summarize what we did, because we want to move to reinforcement learning part, BIOL is composed of three core ingredients. Image transformation first, target networks, and third, a predictor. And we see later that it's crucial for this work. So interestingly, it's super simple procedure. It doesn't require any specific trick to work. And in pros of the contrastive methods that were highlights of the field until 2020, such as SimClear or other CPC methods, they don't require negative example to stabilize your training. And a cost of pseudo labels, of clustering works at the level of L2 networks. There's a question.
There is a question on Slido.
Yeah.
So the question is, how do we know that we can no longer improve the self-supervised learning process? So how do you measure
So we usually do something very simple. We have a fixed training alpha, but we can measure it because we can also evaluate. We have an evaluator that every certain number of epochs, we look at some kind of accuracy on some downstream tasks, and we see if that's not improving. But practically, we know that after some point, there is no point of training.
So hi, so in which situations we should use these self-supervised embeddings instead of just pre-trained convnets?
So this is the way how you pre-train convnets.
Okay. I meant like in transfer learning sense.
So if you were to transfer learning, so like if you're this, so the thing is like what is being transferred, like if the project is like for a label transfer, right, then you can just take the pre-trained network and train it on the new change labels. If the whole distribution data transfer, you can also keep that and keep training the network. But all the problems that comes with with the transfer and learning and catastrophic forgetting and catastrophic unlearning, that Razvan is expert on, it happens also here. It's still a ResNet. And what here we're not really focused on, improving the architecture. We improve the way of training, right? So like people took it and, tried to improve the architecture, right? Like the follow-up work as Barlow twins and a transformer comes with that. And so there are a lot of people that improve the architecture and get better results. But here it's kind of a paradigm how to actually train this in a way that you don't need negative examples. And that's why it's, that was this main relation of the field, that you didn't have to have negative example that I'll mention in the next slide.
Thank you for your nice talk. My question is also related. So how does it differ from the hide-and-seek data augmentation technique to pre-train CNNs? They also use it to hide the relevant features and then make the network to learn from other.
So like we did not do any work on augmentation, right? So if you do better augmentations, this is orthogonal improvement. If you do better augmentation, you get better, better improvement. Since 2020, there's lots of work on augmentations. The augmentation improved. Jana mentioned some of them. There are augmentations of this year. There's a multi-crop. There's hide-and-seek augmentation. We have a paper in 2 weeks on the augmentation for graphs. Augmentation is a big thing, yes. So you can use it together with other kinds of augmentations.
Hi, first, pretty technical question, but if you copy encoder, do you is it only backbone or backbone and reprojection head?
You only compute, you compute both of them.
Both of them, okay.
Both of them, yeah.
And in terms of comparison to SimSam, that also does not require negative samples. How would you compare in terms of the?
I think I have a slide,
okay.
yes, on that. Yeah, I think so. Yeah.
Okay. One last
so
question.
SimSam doesn't. So SimSam is a follow-up of the work. Actually, SimSam is a reproduction of one of the appendixes in our work. We already SimSam was done following our work to actually figure out which of the things are necessary. So we already actually did SimSam as a part of the bio work as one of our ablations before.
If understood correctly, the complexity of the predictor induces different transformation classes that relates the two embeddings.
Yeah.
For example, if the predictor is the identity, we are forcing the encoder to be invariant to transformation of the images.
Yeah.
Did you experiment with different kinds of, for example, what if the predictor can only learn an orthogonal transformation? Is it better?
I mean, yes, we experimented. There's a follow-up on those things that are very important. So what is nice about bio compared to contrast emitter is less sensitive to this augmentation. I have also a slide on that.
Okay, thank you.
Maybe, yeah, okay. Yeah.
Can I get one more question? So what's the target here?
So the target is just a vector of 256 numbers that you try to predict. It's not the label, it's just output of the target network, whatever it outputs. It doesn't have, it doesn't have meaning in the way that, it means a dog. Because and this is actually a beauty of it, right? Because on this picture, it's not just on a dog, there's also grass, right? You would like your target output represent everything of image. That there is a dog, there is a graph, that dog is turning left. You would like to have encode all of that, right? If other methods that focus on okay, let's try to somehow create that this is a dog. Well, this is kind of disadvantage of our methods. But it's just a vector that tries to make such representation that the close images will have a close representation, whatever that is. maybe let's finish
Let's,
this
yeah,
dial
yeah,
part. And I want to get back to oral part because most of the question I'm answering in the next 5 slides that I'm getting. All right, so let's just show the performance of the BBIL and how did we train it. So since there's unlabeled data, it's hard to evaluate how it does, right? Because you just output some numbers. So the way, there's several ways of evaluation in the field. One particular way is that you train the representation, so you output this encoder. So basic benchmark model is that, you take this linear evaluation of ImageNet, like the first encoder, typical ResNet, is trained with self-supervised methods. Then the second encoder, in the second step, we freeze the weights, and we train the linear layer on top of that. And if you can manage to train better linear layer, you will say that encoder is better. That's one of the way of elimination, right? So we take the thing, we freeze the weights, and we only train a linear classifier, and we decide, how good it is. And so, in 2020, that was like the best performing method. So every reference point, we here show the accuracy of supervised learning baseline. This doesn't actually mean that you cannot get better than a supervised learning. So this goes back to the question that your colleague asked, right? Like maybe, supervised was the upper bound. And no, because actually the human labels can encode biases, can be wrong, for example. Sometimes labels are wrong. And so self-supervised learning can actually, improve the performance because we don't learn on the human mistake. So it's not completely upper bound, but it's a good, close to performance where we can get. And now there are methods that attain it, right? So here, the higher the better, and the X factor indicate the multiplicative factors in the channel dimension. That's not very important. And in submission time, this was the state of the art before right? The SimClear, the contrasting method that were leading the curve were doing that. And BIO successfully managed to lower the gap between the supervised learning baseline. This is for ResNet, this is for the multiplicative of the channel dimension 2 and 4, between the supervised learning baseline and self-supervised learning method, right? So it also outperformed SimClear, which was the state of the art at the submission time. All right, so to answer some of the questions, so wide variety image augmentation helps standard contrasting method retain diverse features. So it's good to look at the, how actually it performs if you remove some augmentation. Now responding to your question, right? So if you remove augmentations, the performance gets worse. But it's interesting to see with BIL gets worse much gracefully, right? So of course it is well known that contrasting method will suffer from diversity of information, but when the variety decreases, the simple increased performance suffers, but the BIOL is much more robust. Another thing that was also very important, we don't use negative examples, so it's less sensitive to the batch size as a contrastive approaches, because where do you get these negative examples in the training? From the batch size. If you want to represent what is not something, you need a larger batch size. And so since we don't need negative examples, like a SimClear, we can even work with the smaller batch sizes and still do reasonable performance. And this is expected because contrastive methods really, really rely on the large batch sizes. Before I'll mention, I think I'll skip those slides. Actually, next, I want to mention the reason why this caused some revolution, because most of the methods needed to use negative examples. And why these negative examples are bad? Because when you had to create, you put the image of the dog close to each other and the image of something which is not a dog far from each other. But what is not a dog? There's so many ways how you cannot be the dog, right? It's hard to decide. You have only small batch size. And also, so what people do, you take a random other example. But what if there is a dog? So actually, you can actually do something wrong because you don't know what's the other image. So it's kind of a conceptual problem, defining what is not a dog, possibility of the mistake, difficulty of creating, and there was a whole industry, there was a whole science of how to create called negative data sampling. And so with BBIL, you actually remove that. An important thing that I only mentioned one of the things, when we start up on this journey of BBIL, we use it for graphs. We won a challenge of the large embedding, the challenges Stephanie mentioned. We use the protein-protein interaction in neuroscience, in videos, and we apply these methods in many, many areas. And in the last half an hour, I'll talk to how we improve it, how we apply it to RL. But for example, one of the reasons why this was important was for graphs, Because there you try, as Stephanie said, embed every single node. Well, how do you do negative examples, in the other, what was called contrasting method? Well, you will say, what is the other node? How many potentially other nodes there are? How many potential pairs of the nodes? It's quadratic in the size. So because of that, graph embedding methods did not scale because they were quadratic in the size for needing to perform well. I think I even have a graph on that in this. So you actually had to, oops, oh no. You had to make the methods working well, right? You had to use all the data, and if you, for example, subsample, the method perform well. So you need to have all the samplings to have a method have a reasonable performance. But our method had no contrastive samples, and so it uses much less memory. So it was, from quadratic memory to, let's say, linear memory for that. So I will focus in the remaining time on reinforcement learning, but I think it's now is good to take another questions if they are respect to the representation learning of B-Bio.
There are a few questions on Slido, but okay, let's try to go a bit through them. So the first question, isn't it possible for the two networks to learn to always output the same trivial solution? So basically learning to collapse in Bio?
Yeah, and so this is still an open question. We verge on some kind of theory investigation. We have two papers, and I maybe mention one of them, two papers presented in a conference in 3 weeks in ICML that tries to answer some question. The answer is not fully satisfying. Obviously, 0 or any constant is a minimum, but it's probably not a stable minimum. So I skip those slides and I can go over it over the break, why this is happening. But the kind of intuition is that somehow if you initialize with 0, it stays 0. But somehow, this is not a stable minimum. So like when the training happens, it's most likely that it finds stable minimum where this doesn't happen. So there are many minima, which is also called in this field neural collapse because you're predicting the same thing. But it's one of the intuition is that here in BIL we're not really doing gradient descent as in reinforcement learning. So there is a loss. We're trying to do the step within this loss, which you call bio loss. It's an L2 loss. But once we do the step in the loss, we change the target. And then we do empirical moving average, which is not a learning, it's not the gradient step. So it's not a single loss that we optimize. We don't try to get to the minimal loss. We take a gradient step with this loss, we change the target, and then we do gradient step with another loss. So it's not, we cannot apply the simple reasoning that, okay, this is gradient descent, 0 is a minimum, so you find this minimum. It's a more complex dynamical system that we still not fully understand. There are tens of papers that try to figure it out. Some people, Jan Lekan calls it magic. It's still not fully understood. We have partial understanding. We have few theoretical papers that I'll share with you. But this is kind of the first intuition. We're not doing gradient the stable loss, and which means 0.
Maybe a quick question to answer. Are you enforcing some kind of Gaussian distribution on the embedding? So do you have like a prior that when you do bio?
No. I mean, so like the only thing that it's a kind of inductive bias of ResNet. We're not enforcing any other things. So. But of course, there's a lot of tricks that are used, and they're described in a paper. Cosine learning rate, the normalizations. A lot of things are there. But no, we're not enforcing explicitly any. Absolutely. And this is why it is self-supervised learning, but it's not completely self-supervised learning in actually, so in images, we're lucky that there is all these decades of people, like Jana and others that created amazing augmentation because they understood what is important for vision, right? In a lot of other fields, I skipped those slides, in terms of time, we don't have. In neuroscience, there is no augmentations. In graphs, the only augmentation we come up with is just randomly, delete some of the edge. So it's actually simpler because we don't need to think hard, but it's also difficult. And in reinforcement learning, I'll show you next time what we came up with, because there's also what is the augmentation in reinforcement learning. So I'll talk to it in a few minutes.
Okay, maybe the last question. I think you kind of answered, but just to re-say the answer. So can we compare BIOL to some teacher-student architecture where you would apply knowledge distillation from?
Yeah, of course. There is a teacher-student architecture. Like BIOL is the I didn't put these slides, but BIOL is composed of these three main things: the target networks, the stop gradient, the learning stuff. If you remove any of them, everything collapses. And so a lot of the previous method didn't have some of them, they had to have specific labels, some had a pseudo labels, some didn't get any steps. And we also compared the ablation and in the paper, or like I'll talk to you on the coffee break after that. These are all important. And you can also combine it with negative examples. It improves slightly bit, but it's not significant. But yes, there is obviously student-teacher architectures, Siamese network kind of style, by Raya and Ian Lee come from 15 years ago. There's a lot of things happening. So our contribution is this kind of bootstrapping way of things, and these three ingredients, and in the way how we combine them together.
Let's jump to the world models.
All right, let's jump into the world models in the last 22 minutes. All right, so we come back to the slide of reinforcement learning. What we're trying to do, create the agent that takes an action, right? That's what we want to do. But it's very difficult to do it in a very visually complex environment, right? Like we don't see, you ask this question, what to do if we don't see? If we have something like that and we will need to learn a world model. Right, so here we are learning the world model. We're not learning the policy, but actually we're learning, two at the same time. But what we're trying to address is like, okay, how to do reinforcement learning in this thing? Very visually complex, don't see everything. What to do? That's our goal. So the aim of this research is to develop a universal exploration algorithm for RL agents. Right, and so like I present the paper that we presented the last NRIPS, and we have follow-up in ICML with two other papers within this vein of research. So exploration is an important part of our expositional learning, right? Like Doina mentioned that, and especially important when you have sparse environments, right? So one of these difficult DMA environments, there's a golden apple behind the fence, and you barely see it only if you really look at it. So if you scale up to larger and more complex environments, it becomes completely infeasible to try to explore everything in those environments. So it becomes crucial what to pick and which parts of the environment just you never see, because you cannot see everything in these difficult environments. Well, you cannot go to every place. So we need to pick and choose where we do or where we decide we will never do it again or never do it at all. So one of the way, and this comes to the graph, is this curiosity-driven exploration. So BioExplore has few ingredients. One is we learn the world model, and then we try to reward the agents for fooling the model. So we try to learn a model, we try to use the model to ask question, what happen if it turns it right, good. If it's not, it's a mistake, and we use this mistake in error. I'll be very specific about that. Right, so but I'll give you an example. Let's say I'll ask you, what is behind this door? If I can answer, well, very good, my reward 0 because I answer well. If I say something random, something wrong, and it's not what it is, this error will become my reward, and so I'll be attracted to go where reward is. So we use this latent world model, so we'll not try to predict exactly what it is. We try to predict a representation of what it is. If you remember in BYL, we did not try to predict original pixels of the dog, we try to predict representations of the dog. So we never learn in a pixel space, and we predict and build in intrinsic word in appropriate latent space. And so we use this bootstrap feature learning that we build in BYOL. So in order to pick and choose what to explore, we take this curiosity-driven approach, right? So this is two steps. First, we learn the world model of the world, and then we use the mistakes of the world to explore, right? So again, we go to the places with the largest world model loss. So we try to learn a world model, there is a loss, and then we just go to the places with the largest loss. Very simple. So the world model is this object that completely determines what is interesting and what to ignore. All right, so in our work, we built in BYOL and this powerful self-supervised learning method and extending to RL. And then we use BIOS as a loss at interesting reward to drive this exploration, right? So the particle world model will be something built on BIOL. We have some latent state, try to predict latent observation. And then then we drive the exploration to the mistakes of the later stage. So this combination results in mistakes that are dynamics aware and structured because in the RD lighting space. Right? So if we compare it to the other side, slide before, I just have a max over world model. So here we try to learn a world model. So BYOL was kind of just this part. We try to make the best possible world model, and then we send our policy to the places when it makes the largest mistakes. Right? Yeah, question. So the world model is just a neural network where you say, in this state, if I do this action, what happens? Input is observation, latent observation of the state, action, and the output is what should be the next observation. Just let's say you can have a pixels, but then you convert pixels to something more latent because that works better. An action, an output is a latent representation of the future. That's it. It's very simple, and I'll show the network very specifically to show this. So this requires it's a single unifying objective that we use for representation learning, latent dynamics, and exploration. Right? So we want to have it all. All right. So now we go to the very, very, very high level, but to the point that we understand what is actually happening. So we start with a trajectory of experience, right? So beginning, we don't know nothing. We don't know anything. So we're trying to learn something using curiosity. What do you do if you don't do anything? Well, you do, let's say, random trajectories. As Donna said, right, the modern deep RL, collects trajectories. These are the actors. They collect the experiences, and then they store in the replay buffer. And so here, let's say, we randomly do the trajectories, and we happen, there was a key, and then we saw a chair, maybe irrelevant. There was an unlocked door, maybe important, and then we find Koffola, like in the bar yesterday, right? So this is a trajectory. We don't know what's good, what's bad. That's what it is. What we try to do, we start with this trajectory. On the learner side, we're seeing various observations along the way, and then we apply online encoder, so like BYOL, to construct some kind of latent representation of the past, of the trajectory, right? So we kind of try to embed not only just the current trajectory, but also some kind of sub-trajectory, because it want it to be dynamics aware. So these representations should be also encoding everything here. These representations should be encoding everything until here. And then we try to predict the latent future observation from the current history, right? So as you were asking, how do we get those augmentation? Well, it's unclear, but for us, the augmentation of the past is the future. So what we're trying to predict is trying to predict the future, and we somehow know it because while we don't know what's good, but we know the future, it was this lock. So if we can predict the latent future observation from the current history, we then can use this loss to train our predictor and online encoder, right? So, and then we use the same loss as an intrinsic reward for exploration, right? So here, I'm just showing you how we learn the world model. So, how we learn this network, try to predict the future or like the representation of the future. But then we said, okay, look, go to the places where the mistakes are high and try to maximize this. So this is kind of curiosity. Be curious, see when we are not good in predicting, and go there. Okay, so practically how this works on like specific settings. So let's play the Atari game, one difficult Atari game, Montezuma Challenge. There is a little screen of Atari. If you can zoom in, there is this. There is avatar that tries to jump the stairs. So these are the trajectories, are just like the screens on the Atari game, right? So this is one, and here the little guy jumped, so he's a little higher, right? So what we were doing, we're trying to encode this. So this will be some kind of a ResNet that we encoded. To this, we did this, latent representation. Since we want it to be dynamics aware, so now I take advantage of what Razvan talked about, recurrent neural networks. So we embed it in the recurrent RNN cell or LSTM cells to get belief. And so the next one, it will be kind of, belief of the past, goes on to what was current representation to the next belief, right? And this is on and on and on, right? So this is just a simple convolutional net to get the representation. This is what representation of state is. This is what we're trying to learn, this representation of state. And this is this belief. So this is also encoding all the past, right? So because the past goes into it. So we combine the past with current representation. So this is this closed loop. We're trying to predict, we still don't know how to learn it, but you can guess, because that's what we talked about in the first part, right? So what we're trying to do now, this is a closed loop, this is a part of the open loop. And why it's open loop? Because here we add actions, right? So now we're asking this question, what happened if I let clicker down? What happened if I go around the core? These are the if I do, this is the action. What happened if, I press up? Or what happened if I press left, right? This kind of action. In the past, actually, I know what happened, right? Because I recorded all these trajectories. So I know what happened, so I could use it. But so here, I'll ask the network, what do you think would happen if I press up? It doesn't know it because, this happened later. This will happen here. I know it because it's in recording my data set of the trajectories, but I ask the question, what happened if I press up? Well, I'll say, well, it produced this one. And then I try to predict this kind of target. From this belief, I think this would have happened, and I said, to qualify how good this belief is, I'll try to predict the latent observation of this. So try to predict what will be the next kind of screen or representation of the screen. And these are the targets, and what do we use, these are the predictions, and what do we use as the targets? Well, we know the targets, right? As we did in this biviral paradigm, and this was all intentions of our work, and this is why we were doing that. Well, this is the future. We take the target network, so we copy the torso, same way as we copied the torso in BYL. We pass it to the same predictors. We did this output, and so we know what actually is prediction, latent representation of the future. We know what happened if we press up, because we did press up and we have it in the trajectory. And so we try to, these are our targets, and we try to make this prediction as close as our target as possible, just using simple L2 loss, normalized loss, right? So this is BYOL for reinforcement learning, BYOL Explore, with this paradigm trying to predict latent futures. So this is future, this is latent future, and we try to just make this prediction as close as possible. And then the gradient descent, we go all the way and try to update all these networks, the closed loop network, the open loop network, and the predictions. Here, and what for here, we just take always the copy or empirical moving average of those networks. Any questions about that before I go on some experiments? Good. Let's see some results then. All right. So to test it, we test it on the typical sites for the what is done in RL. So also in 2D, Atari, fully deterministic, but also on 3D. So every year, DeepMind comes with this different difficult exploration method. In 2022, it was called DM Hard A. So these are the super difficult exploration methods that I will show it to you that were not able to show by any RL method, except if you use expert human demonstration and you do behavior cloning or inverse reinforcement learning. This is also more difficult because it's 3D, partially observable, stochastic, and multitask. So this is how it looks like. I think I will have I think here, maybe I can click on here. Maybe it works. No, all right. Well, maybe I will try to see if I have a better picture here. No. Oh yes, it does work. It just took a little time to load. I just need to find my mouse here. Good. Yes, All right, so this is example of one of these hard environments. So it's easiest to look, it's the same image, but from different angles. So I think the best what you can see is here. Like you try here and you try to move this apple from the left to the right side. So you're moving up, and you're moving to the right side. So this is a top-down view. This is easy to see. But what the agent sees is just this thing, right? So the only thing that you get to see is just, these random images, well, not really random, of the apple that you're trying to move along. And this is when we're following the agent. I don't know why this is different color. Oh, yes, okay, maybe that's a little better. All right, so the agent tries to come from here to here, and the only thing that it sees is kind of super visually complex environment. It doesn't know how to represent the world. It doesn't know there is a map. It just needs to create the world model. And we try to use BBIOL Explore for this task. Let's see, I think maybe I need to come down here. Good. Yes, all right. So these are the 8 tasks. We did not solve 8, but we're the first one that will manage to do it without any human demonstration, and we solve like 5.5 of the tasks with this method, right? So a lot of other methods that exist before, R&D, ICM, action prediction, random network distillation, and so on method, or just PRL, they don't do anything. Some of them, they don't even do any learning for some of the methods. And these are the best possible score, 100%, like human normalized scores. And we got to reach it within straw across, baseball, wall sensor, drawbridge, and here we got only method that did something, wall sensor stack we didn't find in whole, right? So these are previously you could not solve it without the demonstration, and here we did not use any human demonstration to solve it. So that was kind of spectacular here. So also, the traditional thing, what you want to do also, because this is a new DeepMind benchmark, you can say, okay, we created benchmarks such that we can beat it. That's also we also wanted to have it in more, more benchmark that fields uses. So we tried this BioExplorer in 10 hardest exploration Atari games, and we were able to achieve near superhuman performance. And on some of the games like Montezuma Revenge, we do indeed get this superhuman performance, right? So again, this is the mean normalized human score. Yes, oh yes, it works. And so the BioExplorer gets this. We also try to have it with bigger networks. We got even better, of course, bigger networks, better results. Other methods, do much less and don't reach the superhuman performance on this task. All right, so it's superhuman on 10 games and massively outperforms other exploration methods while keeping very simple, because all these other methods had to use some tricks, episodic memory, mixing between different methods, combination, short-term, long-term rewards. We didn't have to do anything. One thing, this is not solving this directly, is the difficulty of all curiosity-driven methods, right? So you're driven by curiosity, which means you're trying to predict the future, and if you cannot predict it, you go there. Well, now imagine like the typical problem that in the field we call TV noise. So if you have a noise on a TV, it's a random noise. You cannot predict what's in the next step because it's always random noise. The agent sees this, it cannot predict the next step, so it goes in front of the TV and looks at the noise. It's not very useful agent. But this is exactly what happens when we have this kind of curiosity-driven exploration. And our next work, I don't know if I have time to mention some of it in 4 minutes, is dealing with that. But already in BioExplorer is able to predict some kind of noise, because you can have noise dependent on the action. Let's say you switch channels, and on each channel have a different kind of noise. This is very, very intriguing. Agents love those things. switching the channels, so unpredictable, so a lot of reward, and my curiosity is being really fulfilled. Very bad for RL. So, and very bad for curiosity-driven methods. But at least the methods where we actually added the random pixels to the screen, right? So you have a Montezuma challenge, and then we added the random pixels. the method did not get much worse. So already without explicitly hoping, doing something against noise, encoders were able to ignore some level of noise. It was able to ignore the second part of it. And so, so this is the way how we actually solve this throw across. This is another task of this method. And was able to go around the room, Bio Explore method is trying to go around the room, cross this fence, and move, these two balls and get the golden apple this way. So this is how the final result looks like. So to summarize, the Bio Explore part is like a simple cursor-driven algorithm that simultaneously does representation learning, dynamics modeling, and exploration. So, of course, we have more details in the paper, or I'm here all week. Please talk to me. I have 2 minutes for either going to how we address the newest work being presented in 10 days in ICML, or I'll take the question. I'll let Razvan to decide.
Are there any questions from the room? Okay, let's see the
Let's
hit
see it.
site.
Yes, let's see it. Of course, it's not for in 2 minutes. It will take 15. It was a trick, but
It's
no. I'll just mention a few things.
I can't be the only one who.
No, why not? All right. So, stochastics is a problem. The TV noise is a serious problem. You can be dependent on many of things. You can have a noise that is. You add the noise to the Montezuma Revenge. That Bio Explored work really well. You add noise, it goes really bad. It doesn't move on. You add sticky action. Sticky action is a typical case how we test this method. So in Atari game, you try to press up and down, and you press up, and instead of, with some probability, you don't go up, you repeat the last action. It's called you remember, I don't remember, like in the old times, in 80s, when you stick, the key didn't go up. So, that's called sticky action. So this is a challenging thing, and so you can break the methods by using sticky action, while, it should not be that difficult. And so like the big of the things, when you apply our new method called Bio Hindsight, then you're able to deal with sticky action. This is a ping method that goes up, and we are able to ignore the noise. Same, we can ignore the noise in this high-level stochastic setting. We can do other kinds of noise, that we also make dependent on actions, maybe dependent on the state, depends on action and the state, and interval, right? So the way how we did it, we try to describe it in some kind of structured causal model, and specifically create these embeddings that are robust to those things, right? So we're not first one that noticed that curiosity-driven exploration have problems. There are all these papers that try to do. Some of them, they're robust to the sum of the noise. So there is a check mark where the method is robust to sum of the noise. There is no method until the one that we'll present in a couple of weeks that is robust to all of those noises, and it does for any representation. So we have a method that is stochastic, different stochastic types, different dynamic awares, and different scalability. Right, so let me just present this idea, and then I stop, right? So it's an intuition. Consider you betting on a coin toss. The coin is hidden from us, right? Like, I'll toss a coin, I tell it, and I take an action. You can bet on heads or bet on the tails, right? So let's say, bet on heads, and I tell you outcome. You lost the bet. So therefore, two facts are clear. A priori, you could not have predicted what happens. Well, it's random, no matter what. But a posteriori, when I tell you you lost the bet, well, the coin must have landed tails because you know how the game works, right? It's a super simple observation. So we use this operation to, fix the problem of stochastic environment, right? So if we know how this game works, then in the hindsight, that's why the method is called Bio Hindsight, the outcome is obvious. On the other hand, if we don't know how the game works, then we would not be able to infer this Z, the latent fact, nor we would know how to identify the outcome. So this suggests that we can measure this understanding, so before curiosity, we define understanding as ability to predict outcome a priori, right? Can we predict what happens in the future from our latent representation if we do this action a priori? And we use this to reconstruct the outcome a posteriori. So we will make this action, we'll look what happens, and we try to reconstruct the outcome. So this is the kind of intuition how we actually implement this method, and this will manage to happen in the work, right? So like there is a formalization of those things. We will not go into details because it will take at least 5-10 minutes, but we represent things as a causal model. We do some kind of reparametric lemma. We did some exogenous noise. We represent everything with a noise. We try to find a way how we represent the action, and we try to then, we kind of inject the noise, that what happens a posteriori. In a way, you can imagine that if I tell you what is the noise of the TV, like the next step, then it's easy to predict it, right? If I tell you next step is the noise, and I actually inject to the network, then it's easy to predict, and error is 0. But then I cannot do something so easy. I'm telling the noise because the network will just learn how to copy it, and there will be no reward, will always 0. So we need to inject the noise, or inject something that would represent the noise, but it doesn't represent anything else, anything informal steps. So we do kind of two stuff. We inject the noisy part, but we make it sure that it's independent of the actions. So on the very high level, this is how it works. I'm still here. Talk to me, and I can just tell you, it's this is BYOL. It's a simple modification that the two things that I just said, it's adding some kind of connections, not many extra weights to accomplish this goal, to accomplish this extra loss. And what we get at the end is something that is able to be independent to the no noise, random noise, Brown oscillation, random pixel noise, on-demand noise, so like clicking to the different channel, and is able to deal with all of that. So with that, there's also theory. I'll not go through the theory, but we have another paper in ICML in 2 weeks to show why it works and what kind of things this BioExplo will learn, some PCN or transition metrics. And so at the end, I'll leave you with the references of the all bioephemery and our work in last 4 years since I'm joined. I hope this encourage you to maybe use our paradigm and maybe work in reinforcement learning. And so I'm looking forward to have some kafla with you. Okay.
We're slightly out of time, but yeah, if there's like one question or two.
Thank you. So thank you for the talk. It was very interesting. Actually, I have a very general question about what you said in the beginning, about the fact that maybe you wanted to build world models that would work for different environments.
Yeah.
So I understand that in large language models, it works because the language shares the same structure. But what if environments do not share anything, like between chess and, I don't know, a robot? Would it capture anything interesting?
So, this is a very hard question. If you learn the world model, of course, on the DeepMind HardX environments, it will very likely not work at all and anything else similar, right? So this is very kind of like the continual learning. Like what you can do, you can try to, so I didn't talk to this is like multitask, what we try to do. We try to, for example, train on 2 of these tasks and predict on the 3rd one. So there is some kind of transfer within similar structure environment, but I highly doubt that you can take this environment and try to apply it, for example, on Atari. Like you usually need to, do it in a different kind of work, and oftentimes you take even the encoders that it knows work kind of on this spring. Like in this exploration part, I did not focus on how to actually have made of word, but of course, ideally, you would like to have something, like people do in transformers, everything is a patch, text is a patch, video is a patch, to somehow work. Like this is more of like the concept level, these things as envisioned were also applied for transformers. So I hope that encoder will be something that will be able to encode a lot of different environments. So the hope is that the encoder will be able to encode these biases, and this will be the way how you train this encoder to do these things.
I have a question regarding the world model. So I'm surprised that for you the world model is just a neural network that maps some kind of encoding of the images that the agent receives. But I mean, we could say that the world is actually 3D and it has a very concrete structure. So I was wondering if you could like create a 3D model from the images or something.
3D
like
model.
That. Yeah.
Like create the 3D model from the images?
Yeah, like the Atari game. I'm pretty certain. I don't know. It could.
Like take the 2D model of Atari game and create a 3D model of Atari game?
I mean, this agent is moving a 3D world.
Oh yeah. Well, so this is so there were 2D Atari games and the 3D models. Yes, as the two separate environments. We didn't try to create from 2D to 3D.
I mean, to me, it looked like the actual representation could be much more constrained than just some random network that just.
All right. Okay. Okay. So of course, this is exactly the question. Like you would like to, if you know what's in your environment and you want to, make it easier for network to learn, you can also encode those things, and the networks could be simpler, right? This was definitely not what we tried to do. I believe this would work. We would like to have something that's more generic, but yes, this is definitely, this is completely orthogonal to what we were doing, what we were kind of doing. We'll try to, let's say, existing network that worked for Atari games or for these 3D environments, replace this representation, how people working in those fields represent representation. We did not do any additional research there. We just used whatever works there. And he said, let's try to learn it without human demonstrations or without rewards, and try how we can do stuff without rewards. So that's what we're focused on. There's a lot of research that you can improve the capacity of network. Like we're mostly reinforcement learning researcher. If I have questions on deep learning, I go to Razwan. He tells me how to do stuff. I try it. This is how it works. This is true.
Thanks, Mikhail. Let's thank the speaker again. Yeah, he's going to be around the entire week, so yeah, bother him with questions. Thank you. I guess now we have break until.
Now we have break, and then we have a tutorial of Omar.
comes, we'll see how we figure it out. Like, go ask. Go, let's see.
Na, na, na.
Hi. One question. Do we have extra mic we could use? Yeah, I guess like just one, because there's not enough people for more.
That was Madonna. No, I do.
Okay. Thank you very much. I guess we'll figure it out. Because like yesterday we pretty much covered the room.
Is it on?
Now it's on.
Oh, okay.
Now it's on.
Yeah, I also have them on my phone.
Yeah, no, I went through them and solved them. I hope I still have my solution. Okay, that's also gonna be useful.
They're all like the same ones, but the solution is
Okay, so no, this is the guitar.
the previous one.
The previous one is here. Life saving. That's times one.
Teaching assistant here as well.
Yeah, I'm on all of the tutorials. I don't really background in reinforcement learning, but
Do you need to do something?
yeah, we'll pass over the mics, I think, and also will help with the error in code. If there is somebody there will be somebody that will have some problem with code and will require some assistance. We will be there to help. So that's our primary task here as a teaching assistant. We were also.
I thought you were like expert enough to like know everything.
Oh.
But then maybe.
Do you need help?
Yeah, like normally, at least at the beginning, so that we will be assisting only on some of the tutorials, on the areas that we are more like, we more know about.
You can take this one.
Yeah.
We have another one.
Okay. Just for introducing a key.
Yeah, it's okay. No problem. Yeah. It's okay. And I guess Matt's outside still.
Yeah, I saw him. He told that he was going to prepare somewhere for the tutorial, but I thought it would be here.
Ah.
And then I went here and he wasn't here. So
well.
it's very comes
Non-stationary environment. Yeah.
Currently CVI doesn't sound sexy.
Say kernel-based RL.
We can start. I don't know.
Anytime.
Are we late? Yeah.
Yeah, we are 4.
Okay, let's see if I can do it.
All right, let's get started. So the third installment of our reinforcement learning triplet or triptych will be an oral hands-on tutorial by Omar Darwish Dominguez. Originally from Brazil, he went to Campinas University in Brazil, and then he did School École Centrale in Paris, then did a PhD in INRIA, in sequential learning thing, where he did PhD on contribution in kernel reinforcement learning. So he's known for his algorithm of kernel UCBVI and Kearns, named after famous RL researcher Michael Kearns. He also taught in reinforcement learning in African Masters AIAMs. He taught RL in Polytechnique, in MVA, in École Centrale, so he has a lot of experience that he'll share with you. And now he's being a research scientist in Oaking solving cancer. So let's see what he has for us today.
Yeah, thank you very much for the introduction, Michal. So hi everyone, I'm Omar and I'm going to guide you through the reinforcement learning tutorial I prepared for you. So let's get to it. So as a quick recap, as you saw earlier today, in reinforcement learning, we are interested in learning policies that allow an agent to act optimally in an environment. So we have these two fundamental concepts in reinforcement learning, the one of policy and the one of value function. A policy is a function that's mapping every state to the action that the agent has to take or to a probability distribution over actions if the policy is stochastic, and the value function is measuring how much reward we can expect to gain by taking an action A starting from a state S. And in this tutorial, we're going to focus on methods to approximate the optimal Q function. And also, as you saw earlier today, if you have an optimal Q function Q star, you can obtain one optimal policy by taking the argmax over actions. So if in every state S, you know the value of taking an action, you can take an optimal policy by maximizing over action. So every time, every state, you take the action maximizing the value. So you can obtain a policy, an optimal policy from an optimal Q function. So we can focus on approximating the optimal Q function. Oh, so I split this tutorial in 3 parts today. So I know some of you have never seen RL before in your lives, whereas others have done research on it. Maybe some are doing their PhDs or have more experience. So I tried to adapt the tutorial to the wide range of experience we have here. So there are 3 parts. The first part, it starts with very simple environments with finite states and actions. And if you know the dynamics of the environment, so if you know the reward function and the transition probabilities exactly, you can run value iteration applying the Bellman operator to obtain the optimal policy, one optimal policy. And if you have an environment that you don't know, so you can only sample from it, only taking actions and observing outcomes, you can use Q-learning. So that's the first part. Finite spaces, finite actions, where everything is simple and easy. Then we're going to move to the part 2, where we can have possibly large or continuous state spaces. And there we need function approximation. So we can start from linear function approximation with handcrafted features. So we don't use handcrafted features today anymore, but it's useful to see some trade-offs, to see what happens when you have bad features, just to build some intuition on function approximation. Then the part 3 is about deep Q learning, so DQN, using deep Q networks, where you use a neural network to approximate the Q function. So the features are kind of learned implicitly by your network, trying to approximate the optimal Q function. So here are my suggestions. So if you are a beginner, so if you never coded anything in reinforcement learning before, there is an introduction notebook recapping everything, so not everything, the basics that you need for the tutorial. And then I recommend you following part 1, part 3, and if you have time, go to part 2. If you're intermediate, so if you have coded DQN before in your life, I suggest you start looking at part 2, but optionally, and then go implement DQN. And I also put a challenge in the 3rd notebook. So there you can explore more crazy things. So if you want to try the latest cool algorithms that Mihal just presented, you can go to notebook 3 and tackle the challenge. And if you're advanced, if you know DQN, just implement it quickly and go to the challenge to have some fun. And here's how it's going to happen, everything. So you can code freely and explore the notebooks as you want. And don't hesitate to collaborate with your colleagues around you, so it can be helpful. And you can ask us any questions anytime, so me or the TAs who are there. And every 25 minutes, I will solve one notebook with you and guide you towards the next. So right after these slides, I'm going to guide you for the first one. And another thing, if you have a question that is more general, more conceptual, please raise one hand so we can give you a mic and ask for everyone. If you have code problems and need help that's specific to your code, you can raise two hands and say, hey, help me, and we go there to help you. Okay, okay, so I'm going to get to it when we get to part 3 to give you some tips. So now let me show you. So now so I told you what to do if you're a beginner, intermediate, or advanced. I'm going to follow the path for the beginners because, yeah, that's our focus here. So in the introduction notebook, the first thing you have to check, so there is a Colab setup, installing the main libraries you're going to need. And an important part is here, so showing you how to interact with a reinforcement learning environment in Python. We are using the Gymnasium API for that. It's quite standard. So let me zoom a little bit. Sorry. So you can see better. Yeah. So here you have to, so you can check the Gymnasium website to explore some environments. So here I'm using the Lunar Lander environment. So environments, they are defined by a string ID. You can create them like this. And there are two important functions that you have. The reset function, that is putting your environment in an initial state and returning the initial state or observation. So states and observations in this tutorial, they are the same thing. And then, so you can reset the environment to put it in initial state. And when you want to take an action on the environment to observe the outcome, you call the step function. So you call environment.step for any action that you want to take. And when you take the action, you observe the next state, the reward, and a flag. So terminated or truncated, which I'm going to explain now. So for example, if your environment is Lunar Lander, so here we are trying to learn a policy to make our rocket land between the two flags here. A terminal state is reached when your episode is ended. So, for example, when your rocket lands, or if you're trying to balance some bar when the bar falls down, or when your robot reaches its goal, you're going to have a flag indicating that. So, true if the episode has ended. So you can use that. Okay, and then if you need, there are some, I try to summarize some main concepts here. And the algorithms that you have to implement. Now let's go to the, oh yeah, all the notebooks are here in the GitHub of the summer school. So I just show you the introduction notebook. And to open it, you can just click on the notebook and then open in Colab. Yeah, here. So for part 1, so yeah, I didn't say, but the tutorials, they can seem quite long, but in terms of coding, there are basically 10 lines in total that you have to code to make things work. So the difficult part is knowing exactly what you code. And for that, I put some hints. So here, for the first part, you're going to start with, oh yeah, the environment we're tackling. This first part is a very simple grid word. So here, as I said, we start simple. So the environment is this one, so it's a 2D world. And you have an agent with this magenta diamond shape trying to learn how to reach the green flag at the bottom right. And there is this wall here just to make things a little bit more interesting. So here I'm showing you a random policy. And then you have to implement 2 things in this tutorial. The first one is the Bellman operator. So as you saw in the lectures, to find the optimal Q function, it you can look for the fixed point of this Bellman operator. And for that, you can just iterate. So if you start from a 0 function, apply the Bellman operator very many times, it will converge to the optimal value function. And the challenge here is, of course, you need to compute this sum. When your state space gets larger or continuous, this becomes very complicated. But here's a simple case where you can do it. So you have to implement. So yeah, anytime you have to code something, you're going to find this big comment saying your implementation here. So I'm going to find it in the notebook. And all you have to do in this part is to write 1 or 2 lines computing the Bellman operator. I just showed you the solution. I hope you didn't get it. Yeah. I was coding myself. Yeah. So just to show you this. So when you get the solution, your agent will reach the green flag. And you're going to see the convergence. All right. And then I'm not going to show you the solution for Q-learning, but it's the same. You have the equation here and the line where you have to implement hiding the solution again. Oops. Just compute your delta. Oops, again. Yeah, basically it's going to work if you implement correctly, and you see that the convergence is quite long. That's it. So I'll come back in 20, 25 minutes to follow up on this and to guide you to the next notebook so you can start coding. And don't forget, 1 hand for general questions, 2 hands for code. Yeah, and just trying to give you some extra motivation, maybe not so motivating. But in the end, we're going to move towards more interesting environments. So for deep Q-learning, there is this pole balancing task. And you'll also be able to handle the lunar lander environment that I showed with DQN and this one. So if it's not clear for anyone how to interact with the reinforcement learning environments in Python, please raise your hand. Okay, so that we can advance slowly, I've been showing the solution for a few minutes. I don't know if you noticed, for the first part, for value iteration. So it's here. I'm gonna display it in another notebook so I can keep track of the solutions. So if it's not clear for you how this equation translates to this implementation, let me know. No? All right, so let's recap what's happening here in this first part, in the value iteration part. So as I said, the optimal Q function is the fixed point of the BEMA operator. In some cases, it's easy to compute this fixed point. And precisely here, it's easy because we have access to the reward function. So this operator relies on the reward function and the transition probabilities. And you see that in this function, we have access to both. So we have the P, we have R, reward function and transitions. So, and it's easy to compute this sum. So everything is discrete, so you can store rewards, transitions, and Q functions in NumPy arrays. So no memory issue, no computational issue, so it's easy. It converges quite fast. So if we look at the error, as we increase the number of iterations, it goes down very quickly because the environment is small, it's very easy. And by following the greedy policy with respect to the value function, and by greedy, I mean the one that's taking the action maximizing Q in every state, we get this policy. So the agent learns how to move to this green flag and avoiding the wall. But there are two important things here. So in reality, we don't know the reward function exactly. We don't know P. If you take an Atari game, you don't have a description, you don't have a table with the reward function. You don't have a table with the transition probabilities. We don't know this for the word. So if you're learning how to interact with the word, if you're learning how to recommend movies to someone on Netflix or songs on Spotify, you don't have access to these true transitions or these true rewards. So you cannot compute this operator exactly. Another case is even if you know the dynamics of environments. So if you're learning how to control a robot and you modeled the dynamics and the rewards very precisely with equations coming from physics, the state space can be very large, so it can be hard to compute exactly this Bellman operator. So that's when we start moving to reinforcement learning. So this is more dynamic programming, actually. So not really reinforcement learning, I'd say. Depends on your definition. But when we start moving towards reinforcement learning when we don't know these quantities. So we need sampling from the environment to estimate this Bellman operator, to estimate the optimal Q function, or to estimate directly the optimal policy. So that's a step that we are taking. In the next part, we are implementing Q-learning, so tabular Q-learning, and by tabular I mean that we can store everything in tables, in NumPy arrays. So here, we don't need to know the reward function exactly, we don't need to know the transitions. All we need is to be able to sample from the environment. So if you remember what I was saying about the Gymnasium API, all we need is some object on which we can call the step method and with an action and observe the next state and the reward. So that's when we move to Q-learning. So I'm going to implement this with you now so we can move towards more interesting parts since time is passing fast. So in Q-learning, so if you look at the code, it don't require any more R, the NumPy array with rewards, or P, the NumPy array with the transitions. We are only taking the environment as input and some parameters. So the discount factor that controls how we balance between short-term and long-term rewards. For example, so if gamma is very close to 1, we are interested in a very large time horizon for the rewards. If gamma is small.
Excuse me, could
Yes?
you please zoom in a little bit more?
Of course, thanks. Yeah, should be good. Okay, so as I was saying, here we don't need to know the rewards or the transitions exactly. All we need is this environment from which we can sample. So if you look, yeah, I'm using this because I'm lazy. I'm taking the number of states and actions, but I could also have taken, if following the API, I think observation space.n. So this would also work. So I could put action space here. So this would also work. So yeah, we still need some information about the domain. So what is our possible states or possible actions? But besides that, all we use from our environment is the reset function. So we need to, when we reach the end of an episode, the end of a trajectory, we need to be able to come back to an initial state. And we are also using the step function to sample from the environment. And once we sample from the environment, what we're doing here is we start from a Q function that is 0. Then we want to increment it towards the optimal Q function. So very similar to some sort of gradient descent. So if you look at this formula, we are trying some sort of stochastic approximation of the Bellman operator, right? So if you look here, when is your delta 0? So delta is a measure of error. So you can look at as the gradient or some step that you need to take in the direction of the optimal Q function. So if you look at when the delta is 0, is when Q, the Q function in your state and action, is equal to reward plus gamma and the maximum here. And if you look at the Bellman operator, you can see some similarity between these two things, right? So here, let me show you. So have the delta here. And if you look at the Bellman operator, it also has something involving reward plus gamma times some maximum, right? So instead of summing over all possible states, we are only using the sample next state. So instead of having this sum, we only have S prime equals to the next state that we sampled. So that's the intuition behind this Q-learning update. We are incrementing our Q function to trying to on average, reduce the difference between Q and the Bellman operator applied to Q. And there are other parameters there. There's the learning rate. So if I show you the update, so the update is very similar to gradient descent, as I was saying. So you have something that you want to improve, and you add some learning rate times delta. And delta, just as I described. And yeah, then you have the learning rate parameter to control. And another thing that is very important, so how are we going to interact with the environment, right? So, okay, yeah, we have this update rule, but how are we sampling actions to collect data? So as you notice, a fundamental difference between reinforcement learning and supervised learning, for example, is that, well, besides all the setup, is that in reinforcement learning, the agent needs to collect its own data to learn. So it's very important to define a strategy for collecting data. And here we are using an epsilon greedy strategy. So we can think of the extreme case where we are just sampling random actions. But if you look at our grid world here, to our environment, if you sample everything just randomly, it can take a long time. Sorry, I'm going to decrease the zoom a little bit just so we can see the environment. Yeah, so if you just take random actions, so if we start here on the bottom left, and you want to go to the bottom right, and you just take random actions, if the environment is very large, it can take a huge amount of time just to reach that flag by chance, right? So, and before you reach the flag, you have no reward, so you have no signal to learn from. So it's complicated. One thing that you can try to do is some epsilon greedy update, where with some certain probability epsilon, so you take a random action, and otherwise you try to follow the best action follow according to your current estimate of the Q function. So you try to mix random exploration with some greedy exploration. That's what it's called, why it's called epsilon greedy. Epsilon for random and greedy for greedy with respect to Q here. So yeah, when you implement it, so if you haven't had the time to finish it, you can start debugging with the easy environment. So it's just a smaller version of the grid world. You can set it to true. But basically, you're going to have some sort of convergence, like error like this. So in the beginning, you see that it's very flat. And this is because the exploration is random. So in the beginning, the agent starts here. So let me go to the beginning. Sorry, yeah. So the agent starts here, and it starts exploring randomly. And before the agent reaches for the first time the flag here, all the rewards were 0. And what happens when the rewards are 0? There's no update. So if you start with Q equals to 0, reward is 0, your delta is 0, so you have no signal to update from, right? So until you start getting some reward, you have no signal to update from. That's why we have this huge sort of plateau here in the beginning. So here the agent's randomly exploring until it by chance finds the reward. Then it starts doing some backward induction towards the first state. So here the information is being propagated from the reward signal to all the states. So the agent observes by chance a reward at the green flag, and it's propagating this information towards the first state. And why am I saying propagating the information? Is because we are only updating the Q function in the current state, right? So it has to reach the state of the reward. Then for the state before, it's going to update, and then keep going like this until all the states have been, the Q function for all the states has been updated. So you see that even in this very simple case, exploration is tricky, right? So you need to collect data to understand how the world works. And even if the environment is just a simple grid world like this, so what it is taking? It's taking like 1 million steps to start converging, basically, right? So it's very inefficient. There are much more efficient algorithms for this kind of problem. And as Michal was mentioning in the lecture before, there is this sort of intrinsic motivation things. So one thing that you can try to do is to add some sort of artificial reward, some intrinsic reward, not a reward coming only from the environment. So for example, you can try to encourage the agent to incrementally visit more and more states. So you can, for example, add to the rewards a term that says, that gives a reward to the agent if it reaches a new state every time. So yeah, just to give some extra motivation for the exploration part.
We have a small question from the audience. It's relating to the previous step. So could you
of course.
please show the computation for TQ once again?
Of course, I'm just gonna show it here. I was preparing another notebook only with the solutions, but I'm gonna show it here. Yeah, so it's here. Yeah, thanks for the anonymous person who posted your reply. All right, so I'll let you digest it a little bit so you can keep exploring the notebooks. I'm going to post the solutions for both parts here. And in a few minutes, I'll move to the next notebook with you.
Like the formula is correct, but like is your previous right? Like the PQ is you have to. No, forget it. It's okay.
I'm just asking whether we run this training on GPU or CPU. Did we set it somewhere? Because I get this notification from Colab that I'm not utilizing GPU.
For part 1 and 2, you don't need the GPU, no issue. For part 3, it still runs without the GPU, but it can be faster if you use one. So for this part, it's okay.
Let's get back for a second. Yeah, it's that.
do some replacement with like hard. But yeah.
So is this part clear for everyone, part one? Everything we're going to do from now on really looks like this. So many things we're going to implement in parts 2 and 3 look like these two equations, but a little bit more complicated, but in the end it's the same thing. So I'm going slowly in this warm-up, so let me know if there's any blocking point here. It's important for moving on, so don't hesitate to raise your hand. So there's a question regarding a typo in part 2, so I'm going to check it. Yes, there's a typo. I'm going to show it here. Okay, perfect. Perfect start to go through part 2. Now let's start to make things more interesting. So we spent 1 hour with the basics. Because the basics are important to move on, I'm going to start to accelerate a little bit. So my goal now is to have, in 30 minutes, that we go until the end. So part 2 and 3, I'm going to go through the notebook and the solution with you. And in the end, we have 30 minutes for you to try to reproduce the solution and ask questions if you have any. So let's get to it. So first of all, there was the question about the typo. So nice to see that people got here. So yeah, so it's A prime actually in this line here. So I'm going to fix it. If I find it, in itemize, so yeah, it's A prime here. Thanks for spotting the typo. Yeah. So it's A prime. We are maximizing over actions the estimate of the Q function. Okay, so as I told you, if I look again at part 1, let's take a look at the BEM operator again. Sorry for scrolling that much. Okay, so as I told you, the first problem here is, not the first, but one of the problems here is the fact that if the state space is large and we don't know R and P, this gets complicated, right? So one thing that we can do to handle it is to approximate the Q function as a linear function with respect to a set of features. Let me try to highlight it here. Yeah. It's a very poor highlighting, but I think I can point at it, maybe. Yeah, good. So we can approximate the Q function as a linear function with respect to some features. So we define a feature map for the states, and we try to learn or estimate the parameters theta A to approximate the Q function. So we have a vector theta A that, so that if you take the inner product of the state features, it gives an approximation of the Q function. And our goal here is to estimate these parameters theta A. And for that, you can iteratively solve many linear regression problems. So as you saw in value iteration, at each iteration, we are applying the BEM operator to sampling. And then we take the sampling, we apply the BEM operator again, and we continue. Now, instead of applying the BEM operator several times, we are solving several linear regression problems at a time. So instead of applying an operator, we are solving a linear regression. So that's the thing here. So QK plus 1 in the case of value iteration was a BEM operator applied to QK, so here. And now QK plus 1 is obtained by finding the function that minimizes this thing. So there's a regularizer, so you can think of the L2 loss if f is linear. And we are trying to match these targets here, which look like the BEM operator. So as I said, you're going to be seeing several times this reward plus gamma max here. So it appears every time, including in this notebook. And here we are using handcrafted features. And by that, I mean that we are defining ourselves the features here, the features phi used for function approximation. So let me show you how in this tutorial we are defining this function. So the environment again is the same. It's a grid world, but it's larger. It's a larger state space. And to give you some intuition, so we have about, I think, 200, 250 states. So it's still extremely small, but it's larger than the one before. And the thing is, we can use the fact that in similar states, so we have two xy positions in this environment. So the Q function should be similar for points that are close to each other. So the Q function here, so for example, in a state here, I don't know if, yeah, it should be similar to the Q function in a state right next to it, right? Okay, I think I lost the battery from this, no problem. Anyway, the thing is, if two states are close to each other with respect to the Euclidean distance, for example, their value function should be similar. So we can try to construct some features that encode this similarity. So if I take the features for one state, S, the features for one state as prime, they should be close to each other if the states are close to each other. So it should represent this notion of similarity. And here, it's a very simple thing that I'm doing. So I defined for you a feature map. So a feature map is this class that is taking an observation in a state and returning a vector with the feature representation for each action. So if we look at this, so we can create an environment, create a feature map, and to map the state 1 for, so it's the discrete environment, so the states go from 0 to the number of states, so it's an integer representation. So we map this integer representation to a vector in d dimensions, which is this feature example here. And if you want to, if you have a theta, so our value function will now be described by a parameter theta. And here is the dimension of the feature map. And we have a feature for each action, so that we can have a different value for each action. So there's one parameter, one vector, parameterizing the Q function per action. So in practice, if we want to compute an approximation of the Q function for the state 1 and a given action, and for any action, we can compute this matrix product here. So the feature map will have a shape, let me see here, number of actions by feature dimensions, and we multiply by feature dimensions number of actions. No, sorry. So this is just d dimensions, and this is d by number of actions. So we get number of actions features. That's it here. So here's the feature representation, and here it's the, let me check what I'm printing. Yeah, printing the shape of theta here. So theta is the number of, is the parameter. So you have 4 actions, up, down, left, and right. We have 15 dimensions of the features. So yeah, so instead of having one, so if you compare to the tabular case, we have a matrix number of states by number of actions describing the Q function. And here we have a matrix number of feature dimensions, so 15, which is smaller than the states, by number of actions. So we are reducing, we are compressing somehow the Q function into these parameters. And here, the 4 zeros is the value function for each action. So since theta is 0, everything is 0. Well, basically, so what we have here, so summing up, we have features for each state. So we can map from integers to a real vector. And with this real vector, we have a theta that we have to learn to approximate the Q function. And by multiplying those, we get the approximate Q function. All right. So what is learnable here is theta, and what's fixed is the features. So we handcrafted features, as I said. So let me check if I have the implementation here already. No, not yet. So if you run this notebook from scratch, you have all zeros here. And I think I'm going to go through the solutions directly. So I'll not spend much time in this part, because as I said, it's just to give you an intuition of what's going on. Okay. And while I explain, so I'm going to show you the solution. And then show you what happens when we change the features a little bit. And the message that I want to give to you here is that when we have good features, we can accelerate learning and have a more compact representation of the Q function. But at the same time, it's very easy to mess things up. So as long as our features are bad, you see that the behavior of the agent will be very different from what we would expect with good features. So in this part, we had 2 parts, 2 lines of code to implement, basically. So you need to compute the targets for your, so somehow the labels of your linear regression, which, again, is just reward plus gamma maximum over next state. And the difference here is that instead of, so let me put a comment here. I don't know if it's readable. Sorry, I'm going to increase again the size of the text. So the key point is here. So assuming you're getting more and more familiar with this kind of equation. So the main point here is that we are approximating QSA by this thing here. So sorry, yeah. So here we have a matrix, yeah, we have a function of SNA, sorry, S prime here because the next state. Basically, that's it. I'm going to put A prime, so it's coherent with the equation. Yeah. So here, just plug in the linear approximation of the Q function. So if you compare to what we had in Q learning, you had reward plus gamma Q next state maximum. Here we have reward plus gamma, this inner product maximum, right? So I'm going to put it in our solutions notebook, so you can reproduce if you want. So yi, oops, I think it's here, yeah. Then the second part is solving a linear regression. So here the design matrix is implemented for you, so you can check the details of the code, but it's basically a linear regression. So it looks like a linear regression, but every time you need to recompute the labels, basically. Because every iteration you're updating your Q function, so in every iteration you have new labels, so new targets to learn from. And here I'm running once per action, so it's easier. All right, so by now the notebook should be running. So, and then at the end, what you see is the policy learned by the algorithm. So it learns, again, to reach the green flag. And below, I'm showing you an approximation of the value function. And you're going to see why I want to show this. Something very important here are the walls, right? So I told you that we built these features based on the Euclidean distance between states, right? So if you have the state 6, 6, it's close to 6, 5, right? It makes sense. But the Euclidean distance does not take into account that you cannot cross a wall. So if you're not careful with your features, your algorithm can think that it's possible to cross a wall. So if it generalizes too much, its behavior is going to be very bad. So here the solution is working when I put, so we have 200 states, remember that, about 250, something like that. And the feature dimension is 100. So you're not compressing too much here. So let's see what happens if I put 10. Oh, so it's running. So while it runs, I can show you again. So we have very similar to value iteration. You have a number of iterations, but here we have a linear regression instead of the application of the Bellman operator. Now let's see what happened when we decrease the feature dimension. So the agent got stuck here. It's not moving anymore towards the green flag. And let's look at the approximation of our Q function. So it's horrible. Makes no sense because the rewards are here on the top the top right. And in the value function should be high, where roughly around the reward, because that's where we want to go. So let me increase again to 50, let's say, or yeah, 50. Let's see what happens. Sorry?
More than 100.
If the dimension is more than 100?
Yes, we saw that the 100
yeah.
is the best dimension. But what happened if we have more than 100?
So if you have more than 100, you're just getting closer to the number of states. So you can think of the extreme case where your feature dimension is equal to the number of states. So here it's possible because the states are discrete, so it's not always the case. But if you put the feature dimension equal to the number of states, it's basically equivalent to having a table to represent your Q function. So you have number of states by actions features, which is basically the same thing that you need to store the true Q function. It's number of states by actions. So there is no information loss when you are using features. So it's basically almost equivalent to the, it gets very similar to the value iteration. And the difference would be, there will be two differences. So there's this regularization lambda, so for the linear regression, so we could put it to 0 and get rid of this difference. Another difference is the sampling. So the algorithm can also be sensitive to how you sampled the data set of states and actions. So here, what I'm showing you, I think it's a uniform sampling. So we sample n points. Every time you sample a random state, you get the transition from there. But your results can be very sensitive to the distribution of your sample data. So if you're following a random strategy from the initial states, so let me show you here. So if you're following a random policy starting from here, there's a very low chance that you get to the reward. And assuming that you get there, there's going to be many more points here near the initial state than in the other state. So your approximation can be bad due to this effect of sampling. So there are other sources of error compared to the case. So even if your feature can represent exactly your Q function, there is this sampling issue.
Thank you so much.
So yes, so let's see what happens when so when I increase to 50, did it work? Yes, it works. Yeah. But if I put 20, well, I think just to show you that with certain tuning, the agent can hit a wall and stay stuck there, basically. So if you generalize this too much, so if the value function if the value function is assumed to be continuous across a wall, the agent can get stuck hitting the wall, for example. Let's see if it's the case here. Yeah. Well, it got stuck here, but yeah. Yeah, I'll let you play with the feature dimension, but it's basically that. So you can also increase the sigma. Let me put 50 and increase the sigma to 100 to generalize. But anyway, I think you saw the failure cases. So if your features are not good, your agent will get stuck because it's generalized badly or the convergence was bad. So now this is preparing the ground for deep Q learning, right? So here, as you might expect, so we were solving a linear regression in every step. So what's going to change when you go to deep neural networks or neural networks? Not so deep sometimes. What's going to change is that we are not going to take the argmin every time. So we're not going to solve the full optimization problem every time. We're going to take a gradient step. And there are some tricks to stabilize the learning procedure. So it's very tricky because, as you saw, the targets of your linear regression, they are changing every time. So it's like you're trying to learn something, but your targets are moving. So you're bootstrapping what you learned from the past. So if you're not careful, this can lead to a very unstable behavior. So you have to be careful about your function approximation, about how you sample data, about learning rate, and many things. So many things start to get complicated when you start using neural networks here. So just to, yeah, sure. Finally got to show you a case where it gets stuck in the wall. So if you look at the agents getting stuck here, and probably it's because the value function generalized too much. So if you look at the value function, it looks continuous across the wall, but it shouldn't be, right? So the value here should be much smaller, should be almost as high as across the wall. So these very simple examples, you might think, okay, we don't care about grid wars, they are very annoying, let's go to Atari. But even in these very simple examples, you can get interesting intuition. So you can see how a bad feature can lead to this kind of problem. You can see how generalization can help you, so you can really have a more compact representation of your Q function if you can generalize across similar states, and you can see how things break. Now let's move to deep Q learning. So we still have 40 minutes, which is good. So as I said, I'm going to go through the solution of deep Q learning with you, so you have time to copy the solutions yourself and ask questions in the end. Okay, now we have it here. Let's go to deep Q learning. Okay, I don't have my kernel anymore. So I'm going to execute everything again. But okay, so let me start by the equation and comparing to the previous case. So before, you had a very similar thing, but instead of these parameters here, and instead of having this loss, you had a linear regression. And now, as I said, we are taking gradient steps to minimize this loss. And there's, as I said, there was one trick that's very important to stabilize your learning problem. So assume that you have only one neural network for estimating your Q function, right? What's going to happen? So if you try to minimize this loss, you can see that the target depends, so ignore theta minus for now, assume that theta minus is equal to theta. Sorry, I'm going to increase the size again. Yeah, let me see if I have it. No, you don't. Anyway, assume that you don't have this target network. Assume we only have one single neural network approximating the Q function. So we are trying to minimize this loss, and the targets, so the labels that we are trying to match, they depend on theta. So it can be very unstable, right? It's like when you imagine, for example, if you take a classification problem, and in every gradient step that you take, the labels have changed. You cannot really reasonably expect to convert to something. Maybe it will work on some cases, but it will be very unstable and really hard to make it work on real problems. So the trick here is that we keep two neural networks. We keep a neural network with the same architecture, but we keep two sets of weights. We have what we call the online network, which is the one that we use to interact with the environment. So every time we need to sample an action in the environment. In the epsilon grid strategy that I mentioned in Q-learning, so you take a random action with some probability, and you take the best action according to Q theta with 1 minus epsilon probability. So that's why we call it online network, because it's used to be for the online interaction with the environment. So, and then we also keep a target network. It's a network that we're going to use to compute the target, so the Y here, or targets or labels for the regression problem. And how it's going to stabilize the problem. So the target network is not updated as often as the online network. So you only update the target network after the online network parameters had time to converge. So you're going to see you minimize the loss, you change the target, you minimize the loss again, you change the target. So it's a so if you compare to value iteration or fit or linear function approximation that I just showed, it's the same idea, right? You are applying the Biamo operator, then you change the target and you apply it again. So it's very similar. So it's a sequence of supervised learning problems, and every time that you move to the next step, to the next iteration, to the next part of the sequence, you change the target that you're moving, right? And your goal is to converge to the optimal Q function. So here, all the code is set up for you. It's more complicated than should be, the code here, but I wanted to give you something that is general enough so that you can try complex ideas. So if you remember Mihal's lectures, for example, there were losses based on trajectories. So we not only, so if you look at the loss here, sorry, I'm going back again to it. If you look at the loss here, it depends on a batch of states, actions, rewards, and next states. So for Q-learning, only sampling that would be enough. But sometimes you want some trajectories. You don't want just states sampled randomly from your past. You might need to sample trajectories to compute some more interesting losses. So I wanted to give you a code that you can use as a starting point for ZQN, for GPU networks, but that you can also go from it to more complex settings. So what this code is doing, so if you followed the Q-learning part, it's very similar for the interaction with the environment. So all the things are happening in the fit method. We have a loop on time steps. Every time we take an action. So we have a method called actor step, which is implementing the epsilon greedy strategy. So with probability epsilon taking a random action, and with probability 1 minus epsilon taking the greedy action. And notice that this epsilon greedy strategy is only for when you're interacting with the environment. If you're going to apply your policy, like in an evaluation setting, not in a learning setting, you need this policy to not be random. So you put evaluation equals true if you want the policy to be deterministic. So if you're in evaluation mode, you just want to try your policy in the environment, you can put evaluation equals true. But basically, what you have to implement here is the loss. So I wrote everything except for one line in the loss. Let me see if it's implemented here. Yeah, not implemented here. So all you have to do is to implement the loss here. And the sampling is done here. So the loss function is taking the parameters of all networks as input. So by all networks, I mean the online network and the target network that I told you about. And we have batches here. But these batches, they are not only batch size by dimension, as you might be used to. So it's batch size, B, T for something that I call chunk size here, and some other dimension eventually. So the dimension, the dimension of the state space. So here we are trying initially to balance a pole. So the pole is going to be, so you have the position and velocities of the joint. So I think you have a 4-dimensional state space, if I remember correctly. So it would be 4 or 6. And what is T here? So we don't not only have a batch of states or observations, we have the trajectory that was observed following this state. So we have a trajectory here. Of course, I'm flattening it out, so you get something that it's roughly the batch size as input and the rest here. So that's what you're going to need for Q-learning. But if you want to implement multi-step returns, Q-lambda, don't worry if you haven't never heard of it. Those are some improvements that you can test on deep Q networks, on deep Q learning. You might need the time dimension, but not for deep Q learning. So here, what are we observing? So I'm going to code this with you. So here there are two things. So let's forget the Q select for now. It's used for double Q learning if you're familiar with it, but otherwise don't bother. So here we are computing roughly Q of ST80, let's say. Here we are computing Q of ST, sorry, it's for all actions. So you're computing Q for the current state. Here we're computing Q ST prime, so for the next state. So either ST prime or ST plus 1, depending on the notation. Okay, so now let's implement our loss function for the QN. And if you remember correctly, let me show you again the previous solutions. It's going to look a lot like these things. Reward plus gamma, maximum over actions. So let's implement it here. And there is always a bug when I implement this the first time. A practical advice, always check the shapes of things when you're doing your loss, because there might be some implicit broadcasting that, anyway, check the shape. Okay, so what are going to be our targets for our neural network? Any idea? Yeah, you all know that, I hope. It's going to be the reward, so here it's not called reward, it's called RT. Another thing that is different here, I'm storing the discounts at every time step. So the discount is gamma almost all the time, except when you reach a terminal state. So for example, assume that your rocket has landed or that your pole has fallen. So you reached a terminal state, so you don't have a next state. So when you don't have a next state, so let me show you some equation. Yeah, for example here, when you don't have a next state, so when a next state doesn't make sense, you can set gamma to 0, and that's what we're doing basically. So this here, yeah. So this array It just indicates, so it's gamma everywhere except where we reach the terminal state, where it's 0. So it's taken care of here. But basically, it works the same. So we can discount T, so it's gamma, times, so we have to compute Q for the next state. So it's going to be this one. So we have all the Q functions for the next state, and we maximize over actions. So N, so let me call it current Q because it's the current value of the Q network that we want to match the targets. It's going to be what? So it's going to be QT. Well, so if you look at, if you pay attention to it, you see that the parameters here are different. So we have the parameters, so it's the same architecture, so the same apply function in JAX. So the same architecture, but the parameters are different. So for QST, we are using the parameters of the online network. And for the targets, we are using this one for the target network. So I'm going to call it online queue, so it makes sense with online and target network, online queue. So what we want here is to take for the actions that we selected. Yeah. So can anyone see a bug here? Probably an underscore. The underscore is, I think it's fine. Let me check for this one, it's fine. It's actually very subtle. You might think that you're taking the indices here. There's a broadcasting going on if you don't do this. So check the shapes. Shape. Now no broadcasting is going on. So basically the shape of this thing is going to be B times T, so roughly the equivalent batch size. So batch size times the number of time steps in a batch size, because we flattened everything before. All right, so I think it should be okay, unless there's a typo. And the loss is going to be just JAX NumPy. The square loss, mean square loss. You take the values of your online minus target. So it's the square, so we take the mean. Let's see, it's not working. Never works the first time. If it does. By the way, just I didn't mention before, let me open some parentheses here. I'm using, so the tips for the GKN implementation, not necessary, I went through it with you. I'm using this library that we developed in my lab when I was doing my PhD, so I will contribute a lot to this. Its goal is to help you develop reinforcement learning from scratch. So there might be something that you are seeing in the tutorial that come from this library. So the goal of this library is basically to give you tools that allow you to go from debugging to training multiple agents in parallel, and to easily integrate code and agents from other libraries for benchmarking, etc. Because in reinforcement learning, it's very difficult to debug, right? So as you saw in the first notebook, you have a huge plateau when you're doing Q-learning in a tabular environment. So if for a long time you don't receive rewards, it can be a mess. So imagine that you're looking at your loss function, everything doesn't change. It's awful. So it's important to have a clear methodology for debugging. So grid words can be annoying, so these 2D environments can be very annoying and uninteresting. But as you saw in part 2, for example, not here, but maybe here, it allows to visualize precisely what's happening. So if you're implementing some algorithm from scratch, I strongly suggest that you try on grid words first, just to make sure it's running, that the loss is converging to what you want. Because once you move to Atari games, to robotics, it can be very, very hard to debug. So you're going to implement your algorithm. It's not going to work because, well, when does it work for the first time? And then you don't know if the problem is a bug in the code, if the environment is too hard, if the hyperparameters are not good. So it's important to make sure that first the code is running as expected in an easy environment, and visualization is very important for that. So now I think, let me go back to the tutorial. So here I'm using, from this RLberry library, something that is called Agent Manager. So it's basically taking your agent class, some hyperparameters, and running it in parallel. So I'm fitting 2 agents in parallel here. Let's see if it's working. So yeah, and you can follow a little. So there's going to be plots later. No, it's not a good notebook, so yeah. Let me see, I think I didn't run this cell. Yeah, oh, look, of course, forgot to remove this line. Okay, so let me interrupt the cell below. You see, you cannot see loss equals to exactly 0, never happens, maybe. No, don't restart. So I'm gonna run the cell again. Let's see if it works. So of course, so here it's commented some parts where you can fit just 1 agent. I like to have some idea of the variance of things. So 2 agents are not enough, but basically we can increase it if you want. Let's check the loss. Okay, so there's some loss. And then you can, so just to give you some idea, the episode rewards are the rewards that are collected during an interaction with the environment. So you're trying to balance a bar. Let me see if it's here, a poll. So you're trying to balance this poll, and the episode rewards is the amount of rewards that we got while the bar was balanced. So yeah, you get a reward of 1 or -1, I forgot, while the you get a reward of 1, sorry. Every time step that the pole is balanced, you get a reward of 1. When it falls down, you get a reward of 0. So if you try to maximize the sum of rewards, it's balancing the pole, basically. So let's see what's going on. So you see that the rewards in the episodes are not increasing too much, so there's probably something wrong, as usual. Let's try to debug. Yeah. Exactly. Thank you very much. And there's another thing here that's probably that is wrong. So, anyone see another bug here? Live debugging, super cool. Let's go. Remember that I said that the target network was only updated periodically? But yeah, the code elsewhere is updating it. So I think it's, if you look at the fit method, yeah, it's, let me see. It's been done somewhere. It's not the issue. The thing is, we are taking the gradient of everything here, right? So maybe we are taking the gradient also with respect to the target network, right? So how can I prevent gradients being taken with respect to the to these ones from Qt value for the value? There is something missing here, right? There is a stop gradient missing. Because you don't want to take gradients with respect to your targets. Let me run it again. So yeah, so there was a bug here, so it's good to maybe check, even in this case, to check out the loss function. Sorry, the loss. So there's a function here to plot everything. So yeah, so you see that the loss is whatever. Doesn't look nice, right? And the rewards also not increasing, so it's pretty bad. So let's try again with the bug fixed. Oh, how can I, yeah, this. It's here. I'm gonna train only one agent to go faster because there's probably gonna be another bug. And while it runs, I'm gonna show you an interesting library for you. So you might be wondering why I have this weird naming of variables. Not so weird, actually, depends on what defined as weird. But you can look at this relax library by DeepMind. It gives you lots of nice loss functions already implemented for your algorithms. So, for example, if you go to your relax source, so as I told you in the beginning, we are interested in approximation value function. So there is value learning, and you can see Q-learning. So you have the Q-learning loss here, you have double Q-learning, you have variations of Q-learning. So I took their naming convention. So if you want to explore this library with the code I provided, you can. So just a parenthesis while the code is running. Let's see. Yeah, now you see the episode rewards going up. So we got 128. Nice. So it's still running. So yeah, you can see the evaluation rewards. So while it runs, I'm going to start copying the solution to our solution notebook. Okay, where still running. Okay, it's done. Nice, so let me decrease the zoom so we can actually look at the plots. Okay, so now it makes sense. So you might wonder, okay, this Q-loss function is horrible, but actually it's learning something. So you'll see that the rewards are increasing, of course, in a very noisy way. So Q-learning is super unstable. So deep Q-learning is super unstable, even if we did all we did. So there are many improvements that you can try on Q-learning. So what people usually do, I think, in this case, is to do some kind of early stopping. So as long as you reach this high reward, you can stop, for example, your training loop, so that you get something that works. So why is it unstable? Just to give you some intuition about that. So when you are acting on the environment, remember that you are taking a maximum over actions. So for each state, we compute. So we take the state, we pass it through the neural network, and then we take the maximum output of the neural network, right? So you're taking a maximum of something that is being learned in a stochastic, complex way. So the maximum can change quite fast. So from one iteration to another, your policy can change very drastically. So there are ways, there are like some soft Q-learning versions that allow you to do more conservative updates. So instead of drastically changing your policy from one gradient step to another, you can do that more slowly and make sure things are more stable. So basically, there are ways to make this more stable. And there are also policy gradient algorithms that are based on learning the policy directly. And oftentimes, they have explicit constraints on the difference between the updated policy and the previous policy that can make learning more stable. But anyway, so when I look at this kind of curve, so you can see that every peak here is because the target network is being updated. And so I'm also doing a hard update. So periodically, the weights are copied from one network to another. You can do some exponential averaging too, some moving average to update it. So there are things you can do. But I think these peaks are somehow a sign of life that you're getting something from the QN. So often when I start observing these peaks, your implementation is going in a good direction. It gets completely messed up later, but sometimes it's okay. Let's see the video now. So yeah, it's doing something, right? You can improve it. I believe in you. But well, so if you compare it to a random policy, it's already a little bit better. But of course, GQN is able to solve this environment. So if you want a very nice pole balancing, I suggest you do an early stopping, or that you start looking at some multi-step return. So in RLX, you have Q lambda. You may try Q lambda. Lambda, yeah, you have, let me see, Sarsa lambda. Yeah, you have a Q lambda function in RLX. So you have everything here. So let me zoom it. Sorry, probably not readable. So in RLX, so you have all these quantities already. You have Qt minus 1, AT minus 1, RT. So you can use this loss function from RLX if you want to do Q lambda. Yeah, basically that's it. So I'll let you, you still have 14 minutes. I'll let you play with it. And just give me 2 more minutes for me to present the challenge. So you can think, oh, the challenge is not super challenging. It's just a huge grid word, of course. But it's a preliminary step if you want to tackle things like Montezuma's Revenge on Atari. In Montezuma's Revenge, you're trying to move from one room to another. So if you cannot solve this, you cannot solve Montezuma's Revenge. So it's a very important debugging step, as I was saying. Start simple. So here you don't have many representation learning issues. Here representation learning is easy. Your main issue is exploration, so how to collect data to explore different rooms. So basically that was the challenge that I gave for you. So if you want to implement some exploration strategy, so here you can go crazy, you can play a lot. So you can start simple with some intrinsic motivation, random network distillation. I'm going to put some references in the GitHub later. So you can start simple with some baseline intrinsic motivation techniques. You can go crazy. You can put reinforcements. You can put representation learning on top of it. You can put bio explore, as Michal was presenting. So there are many things you can do with this simple notebook. And here, when you make it work for cart pole, you can go to the beginning and also select lunar lander if you want to see the rocket landing. So yes, so I'll display the solution here. Let me know if you have any questions. So for the last 12 minutes, I'll let you try to reproduce what I did, play a little bit with it, maybe balance the poll, and answer questions. And by the way, these things can be quite annoying, right? So you saw that I had to include these indices here. So one thing that's cool about JAX, you can have the loss function assuming that you don't have the bad dimension, then you VMap over it. So the loss functions in RLX, you need to VMap them. I'll post a solution with that later, but so here it's easy because you only have 2 dimensions, but if you start having batch trajectory size dimension, VMap can help you avoid some bugs. And just one last thing for you who like self-supervised learning, representation learning, this kind of things. So if you look at this Q-learning loss, there's some bootstrapping involved, right? So you're bootstrapping a Q function to compute the loss. You see that the loss is somehow not converging to 0. So if you want to think about it, you can try to think about why BYOL that Michal was presenting before, so it's this self-supervised learning method. You can think of why it doesn't collapse, why doesn't the representation collapse. You can try to make a connection between the bootstrapping happening there and the Q-learning loss that you observe here. Might be interesting too.
Amar. There is actually a question in Slido. If you see it, you can
Yes.
probably read it and answer.
Thank you. That's a good question. So when the implementation is not available, well, when you don't, it's always better to start from, if you're comparing your agent, so you're doing your research, you're developing your agent and you want to compare it to a previous paper or another algorithm, I think usually the good practice is to take the code as reported by the authors, so you can compare exactly to what the authors reported. And oftentimes in reinforcement learning research, what people do is when they are trying to build on some existing algorithm, they take the author's code or some standard baseline implementation and they build on top of it. So because implementing from scratch can be quite difficult. So for research, I always like to implement from scratch at least once, just to get an idea of how difficult the tricks are. Then I move to the author's implementation or somebody else's code to make sure everything is working. So if I try to sum it up, I would say that try to implement things from scratch. It's oftentimes not going to work as you expected, but it gives you can learn a lot by implementing from scratch and debugging. And then you can move towards, so there are several cool libraries that I'm going to cite in the GitHub. So there are stable baselines, there are several DeepMind libraries with standard implementations that you can use. And if it's not implemented in these somehow standard libraries, try to use author's code as a starting point. And if not, at least try to compare to someone else's implementation. It's a good practice. But it's tricky. Once I was implementing one paper, I went to the author's GitHub. I was trying to make it work on my own implementation. And in the end, I saw that the hyperparameters in the paper were different from the hyperparameters on GitHub, and that changed everything. So even when you have the code from the authors, it can get complicated. So yeah, it's hard to code in reinforcement learning, but it's doable. And by the way, just to make some sort of publicity again for this library. So the goal of this library is to isolate all the training code inside the fit method. So if you look at the DeepQ learning tutorial, let me show you here. So yeah, there's a fit method where you can put everything. So what we did is that, so sometimes you can really copy-paste an entire implementation from another paper. So you have a common framework to compare your own implementation to other people's implementation. So that was also one of the goals of the library, to make it very flexible to integrate other people's code for research. So you can have your own implementation and every time compare it to another baseline reference implementation. All right, so we have 1 minute 20 left. So if you have any question, let me know. Okay, so I'll just conclude in this last 55 seconds. So here what I try to show in this tutorial is how to go from a very simple grid word towards something that can lead to a more complex implementation. So here, as you see, these things are very similar in the inside. You see, you always have this R plus gamma next state, somehow approximating the Bellman operator. So you're going to see this very often in reinforcement learning. So here, and when you go towards more complex things like DeepQ learning, I provided you a code that is, as I said, a little bit more complex than it would be for an usual DQN implementation, but you can build on top of it towards more complex things. You can put representation learning losses, exploration bonuses, losses, intrinsic motivation. So don't hesitate. So if you're interested to keep exploring this direction, so try to improve the stability of the QN, try to improve exploration, try to include representation learning, and you can send me an email or contact me if you want to discuss more about it. And that's it. So thank you very much.